So I've shared the notebook link with you as well. For those of you who want to follow along, you can have a look at that as well. Okay, all right. So let's start with our first topic then. Okay, so first topic that we are covering today is probability. What is probability? Probability is basically the chance of something happening, right? So for example, we talk about this in our daily life. For example, we say there's a 15% chance of raining. These days it's not raining. There's a chance of bombing today these days, but whatever, chance of something. If you convert that to probability, you would say that's 0.15 probability of raining. Okay, so basically that percentage number, if you write that as a decimal, we say that's probability. We can sometimes refer to that in percentage form as well, but the more conventional way of writing probabilities is that we write it as a decimal number from 0 to 1. The least possible value of probability is 0. The maximum possible value is 1. 0 means something is impossible, and 1 means that something is absolutely certain to happen. Okay. All right. Now, we have this formula for probability, number of favorable outcomes divided by the total number of possible outcomes. What does favorable mean here? Favorable is the outcomes satisfying the given condition. So whatever is the condition that's given, the outcomes that satisfy that condition, we call them favorable outcomes. That's going to be our numerator. And in the denominator, we've got the total number of possible outcomes. Okay, just give me a second. Okay, so that's the probability formula that we've got. Let's take an example. Let's say we've got something like this. We have a fair six-sided dice. Now, what does fair mean? You'll have fair spinners, fair dice. Whenever they say fair, what that means is all the different outcomes that are there in that particular case, they have equal probability, right? All outcomes have equal probability. So we have a fair six-sided dice. What's the probability of getting a factor of 30? Now, we've got 6 possible outcomes, right? Out of them, how many are factors of 6? Only 4 is not a factor of 6. The rest of the 5 numbers, they're factors of 6. So if you were to roll a dice once, what's the probability of getting a factor of 30? Favorable outcomes, that's 5. Total outcomes, that's 6. 5 over 6, that's the probability. Now, if you do something twice, for example, if you toss 2 fair coins, what's the probability of getting 2 heads? How do you think about it? In this case, the outcomes were very simple to list down: 1, 2, 3, 4, 5, 6. But when you have 2 things happening, we have to list down the outcomes for both of them together. For example, when we toss 2 fair coins, the possible outcomes are that both of them are heads. The first is head, the second is tail. The first is tail, the second is head, and both of them are tails. There are 4 possible outcomes in total. If we want to find the probability of getting 2 heads, what would that be? We would say that's 1 out of these 4 cases. So probability is going to be 1 out of 4. Now, when does this formula work? This is very important. We will need to refer back to this when we do combinations later on. Number of favorable outcomes divided by the total number of possible outcomes. This formula only works if each outcome has the same probability. Each outcome needs to have the same probability, then we use this formula. So in these examples, all of these 6 outcomes had equal probabilities. All of these 4 outcomes had equal probabilities. And when every outcome has equal probability, that is when we use this formula. All right. Okay. Now, these were fairly simple examples. A lot of times for calculating probabilities, we need to use some kind of representations. There are 2 major representations that we'll be using. Number 1, a diagram that we call a possibility diagram, or a two-way table, 2-dimensional table. This is used when you have two things happening at the same time. 2 things happening at the same time. So for example, if you have 2 fair dice, you throw them, you roll them. We need to find the probability that the difference between the 2 numbers you get is at least 3. The difference between the 2 numbers is at least 3. Now, how do you think about it? Now, one possibility is that you list down all the outcomes like this, that, okay, the first dice could be 1, the second could be 1, first could be 1, second could be 2, and so on, and then 2, 1, 2, 2, and so on. You list down all outcomes like that. That is one possibility. But since we've got 2 things happening at the same time, we can actually represent this in the form of a diagram, which we call the possibility diagram, or a table like this. On one axis, we represent outcomes from one event. On the other axis, we represent outcomes from the other event. So we've got two dice. On one axis, we've got 1, 2, 3, 4, 5, 6. On the other axis, we've got 1, 2, 3, 4, 5, 6. And in these places in the table, we write down whatever it is that we want to find the probability for. For example, in this case, we're talking about the difference between the numbers. So in the table, we write down the difference between the numbers. Now, when we talk about difference, we normally mean the bigger number minus the smaller number, right? So in this table, for instance, where is this 1 coming from? It's 5 minus 4, right? That's 1. Similarly, this number 2, where is that coming from? It's 5 minus 3. So bigger number minus the smaller number. You list down all the outcomes here like this. And then what's the probability that the difference is at least 3? That means 3 or more. The highlighted numbers that you see here, they satisfy the condition. How many of these highlighted numbers do we have? 12 out of how many? Its total number is 36. 12 out of 36, we say the probability is 1/3. Okay, now where does 36 come from? You could either count all of these numbers, or you could do it directly as well. If you've got two things happening, one has 6 possible outcomes, the other also has 6 possible outcomes. The total number of possible outcomes is going to be 36, which comes from 6 times 6. Okay, and that gives you the result. Okay, now the other diagram that we will be using to calculate probabilities, that is called a tree diagram. Okay, this is another diagram that we use for calculating probabilities. This is something that we can use for any number of events, right? This earlier diagram we could only use for 2 events happening at the same time, a table like that. A tree diagram can be used for any number of events. Okay, let's take this example for this. So generally, a tree diagram works like this. It starts from the left side, and then it works sequentially. So you got these two options in the first go, and then you've got a couple of other options here, a couple of other options here, and so on. It goes from left to right like this. It goes sequentially. What happens first is represented on the extreme left, and then you keep going right from there. Now, let's look at this situation. So they're saying when this person plays tennis, 65% of his first serves go into the correct area. So we can draw a tree diagram that looks like this. First of all, we can say, okay, 65% go into the correct area. Then the remaining 35%, 0.35, they will not go into the correct area. These are the two options that we've got in the first set of branches here. It could either be correct or not correct. Then it tells us, if the first serve goes into the correct area, the chance of winning the point is 90%. So if it went to the correct area, the chance of winning is 0.9, then the chance of losing will be 0.1. If the first serve did not go into the correct area, then it says 80% go into the correct area. The second serve, 80% go to the correct area. If the first one did not go to the correct area, so we've got 0.8 probability for going for the second serve going into the correct area. If that's 0.8, then this number is 0.2. So we've got the next branches here like this. And then they say, if the second serve goes into the correct area, his chance of winning is 60%. So that's 0.6 and 0.4. And if it does not go to the correct area, he loses the point. That means losing probability is 1 here, then the winning probability would just be 0. That's what a tree diagram looks like. Now, you would be required to make this tree diagram sometimes. Sometimes they will ask you explicitly to make the tree diagram in one part of the question, like they've done here. A lot of times they will not explicitly ask you to make a tree diagram, but for doing some calculations, you will do it yourself because it will simplify your calculations. Okay, so you'll start sequentially. The first things that happen, you'll represent them first, and then the next things, then the next things, and so on. Okay, so it goes from left to right like this. Now, how do you do calculations based on a tree diagram? For example, in this case, if we wanted to find the probability that none of his serves is correct and he loses the point. Now, you will find a path on the diagram that satisfies that condition. None of his serves are correct. That means the first is not correct and the second is also not correct. and he loses the point. This is the path that he follows, right? You can just multiply these probabilities, 0.35, 0.21. We multiply these probabilities. Why? Because there's an and between them. The first serve is not correct, and the second serve is not correct, and he loses the point. There's an and between these cases, so we multiply each of these probabilities. Along branches, as we go along branches horizontally like this, we multiply probabilities. So this probability that they're asking about, it turns out to be 0.07. But now, what if they ask for the probability that he loses the point? Probability that he loses the point. Now, that's multiple possibilities on this tree diagram. He can lose the point in this case, and also in this case. So what we do is we find the probabilities of each of these cases. The first case is that his first serve is correct and he loses the point. That's 0.65 into 0.1. That gives us this. Similarly, for the others, we find their probabilities. And then what we say is, let's add these numbers. Let's sum up these numbers. Because it could either be the first case, that his first serve is correct and he loses the point. That's one possible case. Or it could be the second case, that the first serve is not correct, the second is correct, and he loses the point. Or the third possibility is that both the first and the second serves are not correct and he still loses the point. There's an or between these cases. As we go vertically, there's an or between them. So we add these probabilities and that gives us the total. That's 0.247. So when you calculate probabilities, you multiply probabilities horizontally or along branches. There's an and, so you multiply because of that. Vertically, you sum up probabilities. Vertically, you sum probabilities. Why? Because there's an or between them. For any single point on the tree diagram, for example, this point here, this point here, this point here, from any single point, the branches that are coming out of that point, the probabilities on them, they always add up to 1. These probabilities always add up to 1. Okay? So for example, if we know that this is 0.6, we know for sure that the other one is going to be 0.4 because the sum of these probabilities has to be 1. Okay, that's always true for a tree diagram. So that's what a tree diagram looks like. You'll have to make these tree diagrams sometimes and then use them to do some calculations. It's pretty much the same thing that you used to do in O-levels as well. Nothing new. That's what you have to do sometimes as well. Okay. Then there's this concept of conditional probabilities. Sometimes they'll say, find the probability of one event given that another event has already happened. Okay, given another event. Now, this notation is important. In some of the recent papers, they specifically use this notation in questions as well. So you need to be familiar with this notation. So when you have something written like this, A, and then a vertical line, and then B after that, what that means is probability of A, given that we know that B has occurred or B is true. So the probability that we are finding is the probability of A, given is that B has already happened. This is the given event. In short, we can read it like this. It's A given B, probability of A given B. What is that equal to? That equals probability of A intersection B divided by probability of B, or you can remember it this way. In the numerator, you've got the probability of both the things happening together, both events happening together, both A and B happening together. And in the denominator, you have the probability of the given event. In the denominator, you have the probability of what is given. Okay, that's how this conditional probability formula works. In the numerator, both happening together. In the denominator, the probability of the given event. Okay, now we'll come to a couple of questions of that later. But keep this in mind. This is the conditional probability formula that we've got. Then you have this concept of mutually exclusive and independent events. What are they? They're not the same thing. Mutually exclusive is something different. Independent is something different. They're not synonymous to each other. They're different things. Mutually exclusive events, what does that mean? Mutually exclusive means that if one event happens, then the other cannot happen. right? So if one happens, it excludes the probability of the other event happening. That's what mutually exclusive events mean. So if A happens, B cannot happen. And if B happens, A cannot happen. So if you were to think of this in terms of the set diagrams, the Venn diagrams, you can think of it like this. If A happens, B cannot happen, and the other way around as well. What that means is A and B cannot happen at the same time. They cannot both happen at the same time. That cannot be true. That means there should be nothing, there should be no area that is overlapping between them, right? There should be no intersection because they cannot both happen at the same time. So in a Venn diagram form, it will look like this. These are disjoint sets, A separate, B separate. And for proving that two events are mutually exclusive, what we do is we show this probability of A intersection B, that is equal to 0. So if this is true, probability of intersection, that's going to be 0. So that's the condition that we use for proving that two events are mutually exclusive. Probability of A intersection B, that is equal to 0. Now, this is something that you need to memorize. For proving that two events are mutually exclusive, this is the condition that you show there. If you can prove that intersection is 0, then the events are mutually exclusive. Independent events, what are independent events? This is different from mutually exclusive events. This means if one event happens, the probability of the other remains unaffected. That remains unchanged. Whatever it was before, it remains the same. It's different from mutually exclusive because in that case, if one happens, the probability of the other becomes 0, right? Because the other cannot happen. So that was different. This is telling you independent events. If one happens, the probability of the other remains unchanged. That means whatever it was before, it remains the same. For example, if event A had a probability of 0.4, then probability of A given B, that would remain 0.4 if they are independent, because if B has happened, it does not affect A at all if they're independent. So whatever was the probability of A earlier, it remains the same. That is still going to be 0.4, right? That's the idea. Now from this, and using the conditional probability formula that we did earlier, we actually come to this result. We actually reach this result. That the probability of intersection, probability of A intersection B, probability of A intersection B, probability of A, probability A intersection B is equal to the product of their individual probabilities. Probability of A times probability of B, these are going to be equal to each other. This is only true for independent events. It's only true for independent events, that the probability of the intersection, probability of both the events happening at the same time, that is equal to the product of their individual probabilities. If these two are equal to each other, that means the events are independent. So this is the condition that we would remember now to prove independent events. For mutually exclusive events, intersection probability should be 0. And for independent, the intersection probability should be equal to probability of one times the probability of the other. For mutually exclusive events, intersection probability should be 0. That's not the same thing as probability of A into probability equal to 0. No, that's not. These are not equivalent. Intersection should be 0. Intersection should be 0. The intersection and this individual product, they're only equal if the events are independent. Otherwise, they cannot be equal. And if two events are independent, they can generally not be mutually exclusive. So if two events are mutually exclusive, they cannot be independent because they have conflicting definitions. Mutually exclusive means that if one happens, the probability of the other becomes 0. So it is affecting the other. Independent says that if one happens, the probability of the other remains unchanged. That's not affected. So if two events are mutually exclusive, they can never be independent. In general, they cannot be independent. There's an exception, but that's not relevant for our level at this point. Probability of A and B should be equal to 0. Yeah. So intersection is the same thing as saying probability of A and B, both of them happening at the same time, that should be 0. Yes. Okay, so these conditions you need to remember. Okay, so in terms of concepts, that's all that we've got in probability. Finding probabilities using different methods, 2D tables, tree diagrams, sometimes by listing down the possible outcomes, making different cases, and then finding conditional probability, uh, proving mutually exclusive events and independent events. All right, let's have a look at some questions now. Just give me a second. Okay, so you've already shared the notes link here. Okay, sorry about that. Okay, now let's have a look at some questions quickly on probability to understand how those concepts are going to be applied. Let's have a look at this example. So we've got two 12 fair-sided dice. They have these numbers written like this. Now, whenever in questions they just mention dice, you would assume that's a 6-sided dice. If it's any other number of sides, they would always specify that. So in this case, they've said 12-sided. If they just said dice, you would assume that's a 6-sided dice. Okay. Now these are fair. That means all the possible outcomes, they have equal probabilities. So 1 to 12, all of them have equal probabilities. Now the numbers on the sides which land face down, they are noted. Events Q and R are defined like this. Q is the event that the product of the two numbers is 24, and R is the event that both the numbers are greater than 8. Now think about it. We've got two things happening at the same time. Now, what's the representation that we said we could use for such problems? We could use a 2D table. That was one possibility. But if we make a table for this, you've got 12 outcomes on one axis, 12 on the other. That's 144 outcomes in total, right? If you make a tree diagram, again, we've got the same problem. It'll become a very big tree diagram. So sometimes the number of possible outcomes is so big that it's not feasible to make a diagram for that. As in, it'll take too long to do that. So in that case, you would not do that, and you would just think of it logically in your head or by writing it down. In the first part here, they say find the probability of Q. Q is the event that the product of the two numbers is 24. Now, rather than making a whole tree diagram for this or a 2D table, you just think about the possible cases, the possible outcomes that could satisfy this condition that the product is 24. So you just think about that. Using these numbers, when can you get a product of 24? 2, 12, 12, 2, 3, 8, 8, 3, 4, 6, 6, 4. These are the only 6 possible outcomes that will give you 24 as the product. So that's 6 possible outcomes. Out of how many total outcomes? 144. We do 6 over 144. That gives us 1 over 24. That's this probability. Probability of R, both the numbers are greater than 8. How is that possible? You could again think about the possible outcomes. Both the numbers have to be greater than 8. So you could have 9, 9, 9, 10, 9, 11, 9, 12. When you list down the outcomes, do them in a structured way so that you don't miss out in any possible cases. So with the first number being 9, what could the second number be? The second number could be 9, 10, 11, 12. With the first number being 10, the second could be 9, 10, 11, 12. And similarly, we've got 4 possible numbers here for the first digit. We've got 9, 10, 11, 12. And we've got 4 here. On the other axis, 4 times 4, that's 16 outcomes. Out of how many? 12 times 12, 144. So that's 16 over 144. That becomes 1 over 9. But sometimes you have to list down the outcomes like this. Now, based on this, they're asking, are these two events mutually exclusive? Are they exclusive? How do you prove that? Mutually exclusive events, the condition that we've got for that is that the probability of their intersection, that should be equal to 0. Now, how do you find intersection for this? Look at these outcomes that you've listed down and see if there's anything that's common between them. There's nothing common between them. There's no outcome that appears in both. There are no outcomes that appear both in Q and R, there's no overlap. That means the intersection is 0. So you say probability of Q intersection R is equal to 0. That is why they are mutually exclusive, because this intersection turns out to be 0. All right. And then, are they independent? How do you figure that out? Probability of Q is this, probability of R is this. What's their product? You find their product. That's 1 over 24 into 1 over 9. You find the probability of their intersection. That's a 0. Since these are not equal to each other, that means the events are not independent. They're not independent to each other. Okay? So that's how you could approach such problems. Now, you'll have other problems in which you would have something happening with replacement, without replacement. It's the same kind of problems that you see in no levels as well. I'll just show this to you quickly, and then you can have a look at this in your own time. This is an example in which they say there are 8 white balls and 2 yellow balls in box A, and there's another box that has 5 white balls, X yellow balls, and a ball is chosen at random from box A and placed in box B. So you have box A from which you take out a ball and you place that in box B. Now in box A, you've got 8 white and 2 yellow. So white probability is 8 out of 10. Yellow probability is 2 out of 10, right? And then if you take out one ball from box A and put that in the other box you are told has 5 white balls and X yellow balls. Now, if you take out one white ball from the first box and put that in the second box, what happens? The number of white balls, that increases to 6 here. The number of yellow balls is 6x, is still X, and the total becomes X plus 6. You can write down the probabilities of the next branch based on that. This is not with replacement or without replacement. It's a different kind of problem in which you take out one thing from one box and put that in the other box. So the number in the second box is going to change because of that. Similarly, in the second case, if you take out a yellow ball from the first box, what that means is when you put that in the other box had 5 white balls earlier and X yellow balls. It will become X plus 1 yellow ball. So you've got 5 white, X plus 1 yellow. The total number is X plus 6, and you can write down these probabilities based on that. Once you have that tree diagram, you can do the calculations based on that. And that's really straightforward after that, conditional probability and the other calculations. You can have a look at this working. I'll show you another example for conditional probability that we will look at in detail. But this is fairly straightforward. I'll just show you the solution. You can have a look at this in your own time later. Let's have a look at another example. Now, sometimes what happens is they give you tables like this. Sometimes, if in a case, 2 events are not mutually exclusive, will they always be independent? No. So it is possible that 2 events are neither independent nor mutually exclusive. So both of 2 events can be neither mutually exclusive nor independent. That is possible, but they cannot both be both mutually exclusive and independent at the same time, right? So both happening together is not possible, but other cases are all possible. You can have independent, not mutually exclusive and not independent, or none of them as well. That's possible. Now, you'll see other questions in which you will have tables given like this. You'll have tables given like this. Whenever you have a table given, the first thing you should always do is, in probability problems, always find the column totals, the row totals, and the grand total. That will help you in probability calculations. Always find these totals, okay? That's the first thing you should do in problems like these. Now, once you've done this, these calculations become a lot simpler. So they're saying, find the probability of M, where the event M is that the person is male. What's the probability of the person being male? This is the total number, is 618, the total number of males, divided by the total number, the grand total, that's 1281. That will give you the first probability. Again, M and E, what's that? Both M and E, both male and employed. For which case is that? That's this, 412 divided by this, 1281. You can write down that probability directly as well. So once you have those totals, writing down these probabilities becomes a lot simpler. Then they're saying, are these independent events? Justify your answer. How do you figure out if these two events are independent? Their intersection probability, and their individual probabilities product, if they're equal to each other, then they're independent. Otherwise, they're not independent. So what we do is we find the probability of their intersection, male and employed. We found that earlier already. We find their individual probabilities and we find their product and see what that turns out to be. In this case, it turns out that they're not equal to each other. Since they're not equal, we say they're not independent. If the right-hand side and the left-hand side, they turned out to be equal, we would say that they are independent. Okay. Now, this is very important. In the last part, just saying, given that the person chosen is unemployed, find the probability that the person is female. What do you do about this now? Conditional probability problems as well, they become much simpler when you have a table given. You can do these without the formula as well. So they're saying, given that the person is unemployed, which people are we talking about? We are only talking about these people, the unemployed people. So that's given. We cannot go outside this column. So the total number that we're talking about is just this 564. So out of these people, out of the unemployed people, what's the probability that the person is female? 358 divided by this, we could write down this answer directly. And that will be our final result, right? Just 358 over 564. You could use the conditional probability formula as well in this case, but that's going to be much longer. What you would do in that case would be, you would use the formula like this. The formula is probability of A given B. What's that equal to? That's equal to probability of A intersection B divided by probability of B. Probability of intersection divided by the probability of the given event. Female given unemployed, right? That's what we have to find out here. Probability of the person being female. That's what we have to find out. What's given? Given is that the person is unemployed. So this is what we're looking for. That will be equal to probability of their intersection divided by the probability of the given event. We find out each of them separately. Female and unemployed, that is this case 358 divided by 1281. That's the numerator. And unemployed, that's 564 over 1281. You see what's happening? 1281 and 1281, they get cancelled anyway, and you end up with the same thing that we got here, and we get the same answer at the end. So even if you use the conditional probability formula, you get the same result at the end. But in case of a table, it's much easier to just do that calculation directly from the table without even using the formula. All right? Okay. Yes, so we talked about that already. So you're saying if two events are mutually exclusive, then they cannot be independent. Yes, that's true. Okay, let's have a look at another example. Now, sometimes it becomes a bit more complicated. So you've got these three people. We are given the probabilities that they will enter some venues, some ground. Through each of these entrances, A, B, C, D, we've got their probabilities, right? So this is the summary of the probabilities from this situation that's given. We've got three people. We've got their probabilities of entering from entrance A, B, C, and D respectively, right? All of these probabilities. Now, the question says, find the probability that at least two friends will choose entrance B. Now, how do you think about it? So sometimes a tree diagram or a 2D table, they are not feasible, or they are a bit hard to think about. So you can think about these cases directly as well. So for example, in this case, they're saying at least two friends will choose entrance B. How do you think about it? So there are three friends in total. What's the probability that at least two will choose entrance B? How could we think about it? Either two friends choose B or all of them choose B, right? These are the two cases. Now, if we have all friends choosing B, now that's relatively easier. You would say Rick chooses B, that's this probability. Brenda chooses B, that's this probability. And Ali chooses B, that's this probability. You multiply these and you get that case. But if two friends choose entrance B, Which two friends? We don't know about that, right? We don't know which two friends are going to choose B in this case. So we would have to consider cases. This is something that you have to do a lot of times in both probability calculations and sometimes in permutations, and a lot of times in permutations and combinations questions as well, that you have to make multiple cases for a particular situation. So in this case, if two friends choose entrance B, we could have three possible cases. One case could be that Rick chooses B, Brenda chooses B, but Ali does not choose B. Another possible case could be Rick and Ali choose B, Brenda does not choose B. Another possible case could be Brenda and Ali choose B, and Rick does not choose B. We've got three possible cases here. What we will do would be we would find the probabilities for each of them separately and add that to the probability of all of them choosing B. There are four cases in total. We find their probabilities, add them up together, and that gives us the result. So sometimes we have to make cases like this to find probabilities. Now, if you were to do it using a tree diagram, now think about it. A normal tree diagram would become too big in this case. So first of all, for example, if you have person Rick, Rick can either choose A, B, C, and D, and then the next person, Brenda, can choose A, B, C, D, A, B, C, D, A, B, C, D. And then the next person, Ali, you can again choose A, B, C, D. So by the time we reach the last step of the tree diagram, by the time we reach the last step of the tree diagram, it becomes 4 times 4 times 4, 64 branches on the last outcome. That becomes a very big tree diagram. So that's not feasible. If you had to make a tree diagram in this case, how do you do that? You could say, we are talking about the friends choosing entrance B. So all that matters is whether they choose B or not choose B. That's all that matters. So we could club the rest of the cases. So we could say the first case is that Rick either chooses B or does not choose B. And the second case is the second step is that Brenda either chooses B or does not choose B. And then for Ali as well, we've got two possibilities that he chooses B or does not choose B. And then we could say, let's find the possible branches here, the possible paths on this tree diagram that satisfy the condition that at least two friends choose entrance B. In this case, all of them choose B. In this case, two choose B and then the third does not choose B. In this case, first chooses B, the second does not choose B, the third chooses B. And in this case, the first does not choose B and the second and third they choose B. And now you could calculate these probabilities and that would give you the result. Okay. All right. So just you have these four cases. You could do this using a tree diagram as well. For B, you have these probabilities. For not B, you would club the rest. For example, for Rick, not choosing B would be 1 minus 2 over 9. That will be 7 over 9. So for the first branch, you would have 2 over 9 here, 7 over 9 here, and so on. You can calculate those probabilities. You get the same result from like this. So you could either think of in your head like this, make all the cases manually, or make a tree diagram a bit more efficiently like this, not for all A, B, C, D, just for B or not B, and then do calculation based on that. Now in questions, sometimes they will say one thing is happening after another thing. In that case, you will make a tree diagram like this. For the thing that's happening first, you write that first and then the next thing and then the next thing. When they say you've got multiple things happening at the same time, in that case as well, it doesn't matter. We can just start with any of them. If you have multiple things happening at the same time, you will just choose one of them as happening first and then the next on the tree diagram. It does not make any difference in that case. Okay. You can make a similar tree diagram in that case as well. We did not do none will choose B. We said all of them will choose B. At least two means you could have two choosing B or all of them choosing B, all three of them choosing B, right? So these were the four cases that we considered there. All right, so this is relatively more complicated type of problem. And the second part, they say, find the probability that the three friends will all choose the same entrance. What does that mean? They all choose either A or they choose B, or all of them choose C, or all of them choose D. So we do something like this. We've got these probabilities, we multiply these, multiply these, and then plus them, sum them up together, because it could either be this case that all of them choose A, or it could be this that all of them choose B, or all of them choose C, or all of them choose D, and so on. And that gives us the result. Okay. Is my screen lagging for everyone? Okay, so there is something wrong with my internet apparently. Okay, was it fine before? Did it just start happening? Was it fine earlier? Okay, what about now? I think it should be fine now. My LAN got disconnected for some reason. Is it okay now? Oh, annotations were lagging earlier. Okay, sorry about that. I think now it should be okay. I think my LAN was not connected correctly earlier. Now it should be fine. Okay. Okay, let's have a look at this example. So sometimes they will give you probabilities and they'll have some missing information like this. So it says there are two identical biased triangular spinners. So the opposite of fair is biased. Fair means all the outcomes have equal probabilities. Biased means that the probabilities are not equal. Some outcomes will have more probability than others. Okay. So we've got triangular spinners, biased. They have 1, 2, 3 written in them. They're spun. For each spinner, the probabilities of landing on 1, 2, 3 are P, Q, and R. These are the probabilities for 1, 2, and 3. P, Q, and R. Okay. The score is the sum of the numbers on the sides on which the spinners land. You're given that the probability of score being equal to 6 is 1 over 36, and the probability of the score being 5, that is 1 over 9. We need to find the values of P, Q, and R. So you've got probabilities given, as in probability of these scores given, and we have to find those individual probabilities of 1, 2, 3. How do you think about this? These are two things that are happening at the same time, and the outcomes are also not that many. There's 3 outcomes for each of them. So that's a case that we can make a 2D table for like this, right? So we can say on one axis, we've got one spinner. On the other axis, we've got the other spinner, 1, 2, 3. And now, how is score calculated? Score is the sum of the numbers. Score is the sum of the numbers. So in these places, we've written the scores. These are 9 possible scores that we've got, right? 9 possible scores. So what's the probability? What's the probability of getting a score of 6? How many outcomes do we have here that give us a score of 6? It's just one outcome here. However, we are not allowed to do 1 over 9 here. That would be wrong. 1 over 9 would not work in this case. Remember, when we talked about the probability formula in the very beginning, that probability formula was number of favorable outcomes divided by the total number of possible outcomes. That only works if all the outcomes have equal probabilities. Now, if the probabilities of 2 and 3, for instance, are different, then probability of getting a 5 and a 6 here, these two outcomes, they will be different from each other. So we cannot use that simple formula, number of favorable outcomes divided by the total number of possible outcomes. That would not work here. So how do we think about this? We can say a score of 6, this can be obtained if The first number is 3 and the second is 3. First is 3 and the second is 3. That is when we can get a score of 3, a score of 6. Now, what's the probability of getting a 3? That's R. Probability of getting another 3, that's again R. So that means R times R, that should be equal to 1 over 36. That they gave us that this probability is 1 over 36. We equate that to that, equated to that, and that gives us R square equals 1 over 36 and R equals 1 over 6 from that. Similarly, they told us that the score of 5, it has a probability of 1 over 9. Now, how can we get a score of 5? A score of 5 is possible when we either have this or this. That means the first spinner could give you 3 and the second could give you 2. That's one possibility. Or the first could give you 2 and the second could give you 3. These are the two possible cases that will give you a score of 3. So you have to consider both of them. You say a score of 5 can be obtained if the first is 2 and the second is 3, or the first is 3 and the second is 2. Now, in this case, since both of them have equal probabilities, you could just find 1 and multiply that by 2 as well, and that will also work. Because the probability of 2 and the probability of 3, that remains constant, Q and R. You can just find one of those cases, multiply that by 2. But how do you find that? Probability of getting a 2, the question said that this probability is Q. So Q times probability of 3, that is R. That's your first case. Plus the first number being 3, that is R. The second number being 2, that probability is Q. So it's QR plus RQ. It becomes 2QR. The question said that this probability is supposed to be 1 over 9. So we equate that to 1 over 9. We already have the value for R before. We can find the value of Q from that. So this is something that can happen sometimes as well. So we've got R and Q. Okay, so there's another probability that's left. We found R and Q, but then we also have P, right? How do you find that? There were only 3 possible outcomes. If we know what Q and R are, then what about P? P is just going to be 1 minus the other 2, because the sum of all probabilities should always equal 1. If we know the other 2, we can just say the sum of all 3 should be equal to 1. That gives us the value for P as well. Okay, so that's another thing that can happen sometimes, that they give you probabilities for some final score like this, and they ask you to find these individual probabilities. So you work backwards in such cases. Yeah, it's a very unusual question, yes. So you have to work backwards sometimes like this. Okay, so this from a recent paper. A lot of people, they don't remember the notations for conditional probability. They just, remember the general formula that in the numerator you would have when both events are happening together, and in the denominator you would have the given event. But you need to understand the notation as well, because sometimes they will not ask you about this in words. They'll ask you something like this: probability of X given N using this notation. So you have to be familiar with this notation. It says that a college, the students choose exactly one of tennis, hockey, or netball to play. The table shows the number of students in year 1 and year 2 at the college playing each of these sports. In year 1, we've got these numbers, 16, 22, 12. And in year 2, we've got these numbers. Remember, whenever we have a table given, what's the first thing that we do? We find the totals. Column totals, row totals, we find them first of all. Find these totals, and find the grand total. Okay? And then, now they're saying, X represents the student is in year 1. So X represents these 50 people that the student is in year 1. So it could be one of these 50 people. N represents that student plays netball. So this represents netball, these 40 people. And then they're saying, find the probability that X given N, find the probability of X given N. Now, what does that mean? Probability of X given that N is true. Now, if you were to use the table directly, as we discussed earlier, it will become much simpler. What's given? Given is that N has happened. So we have to be inside this column, right? That's given. it has to be a student who plays netball. Out of these 40 students, what's the probability that someone satisfies the X condition is in year one? That's 12. So what's the probability going to be? 12 out of 40 or 3 over 10. You could do it directly like this. Or you could use the conditional probability formula if you wanted. That will make it slightly longer, but it's the same idea. It'll be 12 over 120. Probability would be 12 over 120. In the denominator, you've got 40 over 120, this over 120. 120 gets cancelled anyway. You get the same result at the end. Then they say find the probability of n given x. So they switch that, n given x. Now x is given. So that means you're selecting someone out of these people, year one students. Out of these 50 people, how many satisfy the n condition? How many how many play netball? 12 out of how many? 50. This probability is 12 over 50. That's 6 over 25. Again, using the conditional probability formula would be slightly longer. You can do it directly like this as well. And that gives you the result. And then it says, determine whether or not X and N are independent events. X and N are independent events. How do you do that? We know this probability. We know this condition that if two events are independent, these probabilities have to be equal. X intersection N, you can find that probability. X intersection N, what's that? When both of those conditions are true, year one and netball, that's this number, 12 over 120. That's the intersection. That should equal probability of X times probability of N. What's the probability of X? X is year one students, that will be 50 over 120. And N, that's 40 over 120. Find their product. So that's 50 over 120 into 40 over 120. If they turn out to be equal to each other, we would say they're independent. In this case, they don't turn out to be equal. That means they're not independent. Okay, and that's our final result. That's what you wanted to find out. Okay. Just last two questions. Just give me a second. I want to bring one from here quickly. We haven't done any major conditional probability one. Using tree diagram. Okay, so sometimes you would be asked to find, conditional probability using a tree diagram as well. How do you think about this? Let's consider this situation. So we've got three sets of traffic lights on this person's journey to work. The independent probabilities that she has to stop at the first, second, and third set of lights, they're given like this. We need to draw a tree diagram to show this information. We've done that in the first part, and then find the probability that she has to stop at each of the first two sets of lights, but does not have to stop at the third. What does that mean? It's this path on the tree. Stop, stop, not stop. That's 0.224. That will be the final result. That's also fairly straightforward. Let's look at the third and fourth cases, the third and fourth parts of this. The third part says, find the probability that she has to stop at exactly two of the three sets of lights. Stop at exactly two of the three sets of lights. What does that mean? We have to consider multiple cases here. 2 out of 3, what could that mean? One possible case could be that she stops, not stops, does not stop. Then stop, not stop, stop. That's another possible case. And then the third possible case could be she does not stop at the first one, then stops, and then stops again. These are three possible cases that satisfy that condition. We find their probabilities and add them up together, and that gives us the final result. Now, when you do these calculations, you can do this on the tree diagram. That's perfectly okay. But then when you have a conditional probability formula, afterwards, when you have a conditional probability question after this, then I would recommend that you write down the answer to this part like this, that you don't just write down the numbers, but you write down the exact case that you're talking about. So for example, 0.224, where is that coming from? Stop, stop, not stop. Write that clearly in your working. The second case is she stops, then does not stop, and then stops again. And the third is that she does not stop with the first, and then stops again. These are three possible cases that we've got. We find each one of them, add them up together, and that gives us the final result. But then they're saying, find the probability that she has to stop at the first set of lights, given that she has to stop at exactly two sets of lights. Now that's a conditional probability. The keyword for conditional probability is when they say given something, right? So this given is a keyword that they will use in conditional probability. So it's given that she has to stop at exactly two sets of lights. Find the probability that she has to stop at the first set of lights. Now, how do you write that down? What's the conditional probability formula? This is what the conditional probability formula looks like. Probability of A given B, that is equal to probability of A and B happening together divided by probability of B. Now, if you were to apply that here, they're saying probability that she stops at the first. So first is supposed to be an S, given that she stops at two sets of lights, there are two S in total. So in the denominator, we would have the probability of the given event, that there are two stops in total. And in the numerator, we'll have the intersection. The first is a stop, and there are two stops in total. Now, she stops at exactly two sets of lights. We found that in the previous part. This number, that's going to be the denominator, that's 0.392. But what about the numerator? First is an S, and there are two S in total. So once you've written these cases down like this, that will make it easier for the next part now. Where do you have both of these conditions met? First is an S, and there are two S in total. This satisfies that condition. This also satisfies that condition. First is an S, and there are total two S in this. You input values in the formula. 0.224 plus 0.024 divided by the total, that's 0.392, and that gives you the result that turns out to be 0.633. Okay, so you write down each of these cases individually like this. That makes the next part easier afterwards. Okay. Okay, there's actually Azan going on here. I'll have a 1 minute break. I'll leave this question in front of you to think about the tree diagram. I'll explain that then. So one of you is asking about the tree diagram. But 1 minute break and then we'll resume. Okay, let's just start. So how do you draw the tree diagram for this? How do you think about it? It says the probabilities. So she's passing through three sets of traffic lights, right? The probabilities that she stops at the first, second, and third, they're given by this. How do you draw this tree diagram? Remember, the tree diagram is drawn sequentially. The first thing first, the second thing second, third thing third. She passes through the first set of traffic light. First of all, there are two options that are there. She either stops or does not stop. This is the first set of traffic lights. And then at the second step again, for each of those cases, in the second case, she can either stop or not stop. So we've got stop, not stop here, stop, not stop here. And then similarly for the third step, we've got stop, not stop for the third set of traffic light. We are not going to make it like this, that we have the first set of traffic light, the second set of traffic light, the third set of traffic light. That would not make sense. Because what are the probabilities going to be then? Are we going to assign any probabilities here? 1/3, 1/3, 1/3. That does not make sense. She passes through all sets of lights. It's not that she either passes through one or through second or through third. They have to come one after the other. So first of all, we've got the first set of traffic light. that can either be a stop or a not stop, and then the second, and then the third. So it works like this. Does that make sense? Yeah, that would not make sense, because what probabilities would you put there then? The branches always have probabilities, right? Is there going to be any probability for passing through the first set of traffic light? No. She is definitely going to pass through all of them. So all the probabilities are 1. That does not make sense because that adds up to 3. So the tree diagram cannot look like this. Okay. All right. Now, in this example, we are doing A intersection B. A intersection B is not always going to be probability of one multiplied by the probability of the other, or even probability of one plus the probability of the other. No, you have to think of it logically. You have to think of it conceptually. There isn't one thing that will always work. You have to think about it. Intersection means when both of those conditions are true at the same time. That's what it means. What are the conditions? The conditions are, the first should be an S, and there should be 2S in total. These are 2 conditions. Look at these cases. In which cases are both of those conditions met? It's the first case and the second case. What's the total probability for those 2 cases? You add them up together. That's the total probability. So in this case, we are just finding the probability of intersection, and it happens to be that that probability is the sum of these 2 values. Where are these numbers coming from? These numbers are coming from here, basically. We found this one case by multiplying these probabilities, another case by multiplying these probabilities. Both of these sets of branches, they satisfy that condition. So we consider both of these, we add up their probabilities, and that gives us the result. Okay. So we are not going to always multiply something, always add something. It depends on the context. You have to think of in which case the conditions would be satisfied. Okay, one last example, then you have a break from Maghrib. It's going to be a relatively longer break, and then we come back and do the major topic. That's going to be permutations and combinations. Okay, that's what we do next. And then discrete random variables after that. Okay, so a sports event is taking place for 4 days, beginning on Sunday. The probability that it will rain on Sunday is 0.4. On any subsequent day, the probability that it will rain is 0.7 if it rained on the previous day, and 0.2 if it did not rain on the previous day. Now, sometimes you end up getting problems that are a bit confusing like this. So you need to understand the question statement correctly, slow down a little to make sure that you're not making any careless errors anywhere. So this event is taking place for 4 days in total. It starts from Sunday. Probability of raining is not independent of the previous day. It's changing every day depending on what happened the previous day. So it depends on what happened the previous day. So yeah, so you have to slow down, make sure that you understand the question statement correctly. Otherwise, it'll there's no point of doing something without even knowing what you want to do. So spend some time trying to understand the statement. The S1 paper does not usually have a time issue. You can easily get done with it in time. Only the normal distribution question that sometimes takes a bit of time, or if there's a graph somewhere. But overall, the paper is not that long, so you can spend some time thinking. That's what is going to take more time in this case. So slow down a little, make sure that you understand what they're saying. So this event is taking place for 4 days in total. Starts on Sunday. On Sunday, the probability of raining is 0.4. What's the probability of not raining then? That would be 0.6 for Sunday. And then after that, if it rained on the previous day, on the next day, the probability of raining would be 0.7 and not raining would be 0.3. If it did not rain on the previous day, the probability of raining the next day would be 0.2. Then the probability of not raining would be 0.8. First of all, they're saying find the probability that it does not rain on any of the 4 days. How do you think about it? Now, this is not some standard case that you will see. It's just an example of how they can, come up with new scenarios, which are quite confusing. Sometimes you have to think about them right at that point. So in this case, probability that it does not rain on Sunday, what's that? That's 0.6. And then if it does not rain on Sunday, what's the probability of not raining the next day? That's this case, right? So that will be 0.8, and then again 0.8, again 0.8, and that gives you this answer. In the next part, they say, find the probability that the first day on which it rains during the event is Tuesday. Now, they're talking about first day on which something happens. As we'll see later, it's a common case of geometric distribution, but in this case, it's not geometric distribution because the probabilities are changing every day. They're not remaining constant. In geometric distribution, the condition is that the probabilities remain constant. That's not the case here. Probability that the first day on which it rains during the event is Tuesday. What does that mean? If the first rain is on Tuesday, then on Sunday, there should be no rain. That's 0.6. On Monday, there should be no rain. That's 0.8. And then on Tuesday, there should be rain. So it did not rain the previous day. So the probability of raining the next day, that is 0.2 from here. We multiply these and that gives us the result. That's the result that we get from this, okay? And then it becomes quite confusing. It says, find the probability that it rains on exactly one of the 4 days of the event. So there are 4 days, Sunday, Monday, Tuesday, Wednesday. What's the probability that it rains on exactly one of the 4 days, exactly one of the 4 days? Now you have to consider cases in this, right? Because what one day is it on which it rains? It could be Sunday, it could be Monday, Tuesday, Wednesday. So you consider 4 cases, one in which it rains on Sunday and does not rain on the other days, and then Monday and not the other days, and so on. Now, when it rains on Sunday, what does that mean? Probability of raining on Sunday, what's that? Now, the scenario that was given earlier looked like this. If it rains on one day, the probability of raining the next day is 0.7, not raining the next day is 0.3. If it does not rain on Monday, the probability of raining the next day is 0.2, probability of not raining is 0.8. So the next probability that you write there, that depends on what happened the previous day, right? So now it rained the first day. If it rained the first day, then the next day, the probability of not raining is 0.3. So we write 0.3 here for R. And now it has not rained on Monday. So what's the probability of not raining the next day? Now we're in this scenario. Not raining the next day, that's 0.8. So we've got 0.8 here and then 0.8 again for the next day as well. Similarly, for the next case, if it does not rain on Sunday, what's the probability of that? That's 0.6. Now it did not rain on Sunday. What's the probability of raining the next day? That's this 0.2. And now it has rained on Monday. What's the probability of not raining the next day? That's 0.3 from this. And then now it has rained on Tuesday. What's the probability? It has not rained on Tuesday. What's the probability of not raining on Wednesday as well? That's 0.8, right? So you write down this case. And similarly, the other 2 cases, you find each of those probabilities, add them up together, and that gives the result. So sometimes you have to make a number of cases like this as well, and that gives you the result. So the concepts of normal distribution. Okay, so let's begin with this. Permutations and combinations. This is the next topic that we've got now. Now, first of all, we need to know something that we call the basic counting principle. That's something that will be used throughout this topic. Let's have a look at this example for that. We've got a menu for a restaurant here. We've got starters, main course, and dessert. There are 3 different starter options, 5 main course, and 3 dessert options. It says how many different 2-course meal options are there such that you choose a main course and dessert. How many options would you have in that case? Now you've got 5 main course options, you've got 3 dessert options. What's the total number of different combinations you can have in this case? With chicken, you can have any three of them. With steak, you can have any three of them. So what's the total that you get? 5 multiplied by 3, and that gives you 15. If you wanted a 3-course meal, that means you wanted a starter and a main course and also a dessert. For starter, we've got 3 options. We would say it's 3 times 5 times 3, and that's 45. It will be 45 different options that you can have if you choose a 3-course meal. From this, we basically, this is an example of something that we call the basic counting principle, and that says, if there is a certain number of ways of doing one thing, and if there's another number of ways of doing another thing, then if you were to do both of those things together, or you can say one after the other, they both mean the same thing, that number of ways is going to be their product. So if you have m ways of doing one thing, n ways of doing another thing, the total number of ways, when you were to combine those two things, that would be m multiplied by n. We would be multiplying those numbers. Okay, we'll be multiplying those numbers. Now, keep that in mind. You need to know about the concept of factorial, how factorial is calculated. For example, 6 factorial, that's 6 into 5 into 4, and so on. And so on for the other numbers. 0 factorial is 1. Now, in this topic, we'll be doing arrangements of objects, selections of objects, and so on. Let's start with some examples of that. So first of all, arrangements is a major part of this topic. A lot of questions that you will see on this topic, they will involve some kind of arrangement. Arrangement and permutations, these are synonyms. You can say that arrangement is the same thing as permutation, okay? Now, first of all, let's start with arrangements using factorials. Let's take some examples. Let's say we've got these 5 digits and we want to make 5-digit numbers from this. In how many ways can we do that? How many different 5-digit numbers can we make from this, given that the digits can be used more than once as well? Now, there is one representation that we'll be using a lot throughout this topic, and that's this boxes representation. We will represent the boxes to represent the places that some objects can have. So we've got 5 different digits here. We can say we can place those 5 digits in these 5 places. Okay, now how many options do you have for the first box? There are 5 digits. You can place any of them in the first box. You say it's 5 options. What about the second box then? Again, you can have 5 options for the second box as well. Why? Because the digits can be used more than once as well. You can have repetitions. You can have 5 again. You can have the same number again in the next box as well. So that's also 5. And then for the third, also 5, and so on. Using the basic counting principle, then we can say, if there are 5 ways of filling the first box, 5 of filling the second box, 5 of filling the third box, and so on, the total number of ways is going to be their product. 5 into 5 into 5 into 5 into 5. That turns out to be 5 raised to power 5, which is 3125. Now, if we were to change this slightly, and we say the digits cannot be repeated now. The digits cannot be repeated. If digits cannot be repeated, what does that mean? How many options do we have for the first box? We've got 5 options for the first box, but then if we have placed 1 digit in the first box, how many options do we have for the next one then? Let's say we put 2 in the first box, then we only have the remaining 4 options for the next box. So that's only 4 options for the next one if the digits cannot be repeated. Then 3 for the next, 2 for the next, 1 for the next. We multiply all of them and we get 5 factorial for that. And that turns out to be 120. So logically, it's basically this, that 5 options for this, 4 for this, 3 for this. When we multiply all of them, it turns out that we can write that as 5 factorial as well. That's another way of writing the same thing. And that's the total result that you get, 120. There's 120 different 5-digit numbers that you can get from this, such that no digit is repeated. What about this? We've got 5 digits here, 1, 2, 3, 4, 5. And now we want to make 3-digit numbers from this, 3-digit numbers, given that the digits cannot be repeated. How do we think about this now? Now, this is not going to be factorial because the total number of digits is 5, and we want to make a 3-digit number from that. If you think about it logically, that means we've got 5 options for the first box, 4 for the second, 3 for the third. How many total number of ways do we have from this? 5 times 4 times 3, that turns out to be 60. Or as we will see later, we could also use this permutation notation here. We'll talk about this later, that we have 5 objects. We want to place them in, we want to arrange 3 of them. Out of 5, we have to arrange 3. So that's 5p3, that turns out to be 60. Okay. If the digits can be repeated, then for the first box, we have 5 options. For the second, we've got 5. For the third, we've got 5, because the same number could come again and again as well. And the total number of arrangements, that turns out to be 125, and that's your final result for this. Now, you could do this with letters as well. You could do this with letters as well. For example, you have these letters, M-A-T-H-S, T-H-S, and what you want to do is you want to arrange these 5 letters. You want to find the number of different ways in which you can arrange these 5 letters. And how many ways can we do that? We've got these 5 letters. We can't bring new letters from outside. So that means for the first box, we have 5 options. Now, the letters cannot be repeated here because we can't have, if we put one M here, we can't bring another M from outside. We only had one M. So the letters, all of them have to be different. What we do is we say it's going to be 5 times, 4 times, 3 times, 2 times 1, 5 factorial, and that gives us the result. Okay, and you can see what that turns out to be. That's 5 factorial. Okay, now if you have repetitions, what happens in repetitions? Repetitions means you have some identical objects. In letters, for example, if you have the same letter coming twice, D and D, so you've got this word dad. In how many ways can you arrange the letters for this? You would say 3 factorial, but then you would divide by the factorial of the letter that is repeated. You have 2 D's, you divide by 2 factorial, and that gives you 3 from this. That's the number of arrangements that you get. In this case, there's a logic behind it. We don't need to go to that right now. The idea is, if you have some repeated objects and you want to arrange those objects, how can we do that? In this case, we've got 7 letters in total. In how many ways can we arrange 7 letters? 7 factorial. But then we have 3 i's, but divide by 3 factorial. Because of that, it becomes 7 factorial divided by 3 factorial, and that gives you the result. That's 840. Okay. You could have multiple letters that are repeated. For example, this word statistics, you've got S coming 3 times, you've got T coming 3 times, you've got I coming twice. The total number of letters that you've got is 10. You'd say 10 factorial, but then divide that by 3 factorial because of the S, 3 factorial because of the T's, 2 factorial because of the 2 I's, and that gives you the result. So when you have repetition in arrangement, what you do is you divide by the arrangements of those identical objects to get that result. That's the general rule, right? That's what we discussed. If you have some repeated letters, repeated objects, you divide by their factorials to get the total number of arrangements. Now, that's one thing that can happen. Then there can be different types of restrictions that you will see in problems. For example, let's take this case. You've got 12 books, 6 math, 4 physics, 2 chemistry. Now, all of these books are different books. They're not identical. So math books, for example, they could be P1, P2, P3, P4, and so on, right? These are different books. For physics as well, we've got 4 different books. For chemistry as well, we've got 2 different books. Okay, all of these books are different. Now, in how many ways can we arrange these 12 books? If there are no restrictions, we can say there are 12 boxes and we have to place 12 books in them. That's just 12 factorial, right? 12 for the first one, 11 for the second, 10 for the third, and so on. 12 into 11 into 10 into 9 into 8, and so on, all the way up to 1. That becomes 12 factorial. In the absence of any restrictions, we just do 12 factorial here. But then in arrangements, you could have a number of different types of restrictions. Now, what possible restrictions could you have? For example, you had 6 math books, 4 physics books, 2 chemistry books. If you want the chemistry books to be next to each other, so chemistry books should be together. They should be next to each other. Now, how do you handle that condition? So you had 12 boxes initially, right? You had 12 boxes like this. If you want the chemistry books to be together, the way to handle this is you merge 2 boxes and put the chemistry books in that single box so that the chemistry books would move together. They would not be separated, right? So you had 12 boxes initially. If you merge 2 boxes and put the chemistry books in that, how many total boxes do you have now? 10 other boxes, and then this merged box, right? You made 1 box out of 2 boxes, so that's 1. 10 plus 1, that's 11 boxes in total. In how many ways can you arrange these 11 boxes? 11 factorial ways. But then these chemistry books could also interchange, could also switch places. They're different from each other, right? So their arrangements also matter. So we say 11 factorial multiplied by 2 factorial. Okay, 11 factorial multiplied by 2 factorial, and that gives us the result. You can see what that turns out to be. This is what you get. Okay. Now, if you wanted the physics books to be together, there were 4 physics books. Again, we do something similar. We say, okay, we had 12 boxes initially, like this. We've got 12 boxes. What we do is we merge 4 of them. We merge 4 of them. And in that merged big box, we put the 4 physics books, P1, P2, P3, P4. In how many ways can we arrange this now? We've got 9 boxes in total, 8 remaining boxes, and 1 this big box. That becomes 9 factorial. We can arrange these 9 boxes in 9 factorial ways. But then in how many ways can you arrange these physics books? You can arrange these physics books in 4 factorial ways. You multiply them, basic counting principle. You've got 9 factorial ways of arranging the boxes, 4 factorial ways of arranging this. The total number of ways is going to be their product, and that gives us this. Now, what about this? If all math books should be together, all chemistry books should be together, all the physics books should be together, how do you handle this case? Now, you say you've got 3 big boxes. In one big box, you've got all the math books. In another big box, you've got all the physics books. Another big box, you've got the 2 chemistry books. You've got 3 boxes now. In how many ways can you arrange these 3 boxes? 3 factorial. But then there are 2 chemistry books. In how many ways can you arrange them? 2 factorial. 4 physics, 4 factorial, 6 math, 6 factorial. Since all of the books are different, we just multiply them like this, and that gives us the result. Okay, so that there are no repetitions. Remember, the books are different. There's nothing repeated here. All the books are different. The C's are not the same. The P's are not the same. The M's are not the same. They're all different. Okay. All right. We'll talk about what happens in repetition when we do have identical objects, but for now, these are all different. The books are all different. Now, this is a case that is coming again and again in the recent papers. I'll slow down a little on this. You need to make sure that you understand this well. So the condition is that there are exactly 3 other books between the 2 chemistry books. Okay, that's the condition. So we've got 6 math books, 4 physics books, 2 chemistry books. They're saying there should be exactly 3 other books. They could be any of them. 3 other books between the 2 chemistry books. In how many ways can we have this arrangement that satisfies this condition? We can think of it like this, that we have 1 big box. Since we want 3 other books between the 2 chemistry books, that makes it 5 books in total. So we make a big box that has these 5 books. Chemistry books on the sides, okay? And in the middle, in these places, we could have 3 other books, okay? Now, how many boxes does that leave us with? 1 big box, 2, 3, 4, 5, 6, 7, 8. That's 8 boxes. In how many ways can we arrange these 8 boxes? 8 factorial ways. Okay, we can arrange these 8 boxes in 8 factorial ways. Now, these 2 chemistry books, since they are different from each other, they could also switch places. If they were identical, we would not do their arrangement, but in this case, they're different. So we'd have to arrange them as well. C1 and C2, they could switch places with each other. In how many ways can they do that? 2 factorial. And now what we've done is we've arranged these boxes, this big box, along with the rest of the boxes. The only problem is we do not know which books are going to be in these places between the 2 chemistry books. Which books would we have in these places? How do you do that? You could say you've got 10 remaining books. Apart from the 2 chemistry books, you have 10 other books. You could think of it like this. For this box, you've got 10 options. For this box, you have 9 options. For this box, you have 8 options. And that becomes 10 into 9 into 8. And that gives you the result. The outer boxes, we have already arranged. So we don't have to do that again. We don't have to arrange the books outside again. We've already arranged those boxes. That's already incorporated in 8 factorial. Only the inner part, this was not done. this part. So we can do it like this. We can say that's 10 into 9 into 8. Or another way of thinking about that could be, we've got 10 books. Out of those 10 books, we have to arrange 3 in these places. So we could do 10p3 instead of 10 into 9 into 8 as well. That's the same thing. We have to arrange 3 out of those 10 books in these places. Okay. Now this is one method. This is one method that, yes, 10p3 is the same thing. Yes. This is one method that would work. This is one method that would work if the remaining objects had no repetitions. Okay. So you had 2 chemistry books. Now the remaining books that we had, the physics books and the math books, they were all different. They were all different, right? If they were all different, we could use this method and this would work. However, if there was any repetition here, then we would have a problem. If there was any repetition amongst these books, then we have a problem, because then we would not know which books are here, because if you have the repeated books inside, then outside we could have some repetitions here. For example, let me give an example. So let's say the physics books, let's suppose they were identical. Let's suppose they were all identical. Now, in that case, we would have to know how many physics books are inside here and how many physics books are outside, because we would have to divide by their factorials in the denominator. And that would be a problem. That would be a problem, because you'll have to make a number of cases for that. You'll have to make cases like this, that one possibility is that you have one physics book inside, 3 outside, another that you have 2 inside and 2 outside, another that you have 3 inside and 1 outside. And that will be too many cases to make. For that, we have another alternative. We are considering that these 3 books could switch places. This is permutation. That permutation handles that, right? Permutation is considering their arrangements. We are arranging 3 out of those 10 books. So that switching is incorporated here, and also here when we multiply them, we're doing arrangements. That is already incorporated in this, okay? All right. What if we have repetitions? In that case, this method is not going to work. The more general method that for such problems is going to be this. That we think of it another way. We think of it like this. We say, again, we have one big box. We have one big box. And in that big box, we've got the chemistry books on the sides. Okay. And inside, we've got the 3 other books. Okay. And now we do not consider arrangements of the outer boxes. We do not think about boxes in this case. We think about the letters, the objects that are inside. So how many objects do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 places for these 10 objects. 10 places, 10 objects. And how many ways can we do that? 10 factorial. For the remaining 10 books, those 10 books, we can just do 10 factorial, 10 factorial. Since they are all different, we don't have to divide by anything as well. But if there was repetition, we could handle that here now. So if the 4 physics books were identical, let's suppose, we could just divide by 4 factorial here, and that would, take care of it. In this case, they're all different. So let's just understand it using this example first, and then I'll show you another in which there is repetition. So 10 factorial for those letters, and then 2 factorial for the chemistry books switching places with each other. But notice, until now, we had this box fixed in this one place. This box could also move. This box could also move. This box could either be here on the left side. This box could either be here on the left side, or there could be another possibility that there was one box on the left side, one smaller box on the left side, and then that big box. And then 1, 2, 3, 4. There are 7. So we could have 6 boxes on the right side. This could be another possibility, that the big box is in this place. Then another possibility could be that you have 2 boxes on the left side and 5 on the right side. That could be another possibility, and so on. How many cases like that do we have? Let's count them. One possibility is that it is in its current position. That's one possibility. Then how many other cases do we have? This is what these arrows represent. It could remain in its current position, or it could come here. That's 2. Its original position, and this, that's 2. 3, 4, 5, 6, 7, 8. You multiply this by 8, that big box could be in these 8 different places. Okay, that big box could go in these 8 different places. You have to know both of these methods. You have to know both of these methods. This is more general. That will work for almost all problems like this. The first one only works if there is no repetition. So you would only use this when the remaining letters, when the remaining objects, are not identical. Any of the remaining objects are not identical. Okay. Let's take another example of that. So what I'll do is I'll just get rid of these arrows for now. Let's consider this now. Now, in this case, the first method is not going to work, or if it is going to work, you have to make a number of cases for that. That makes that very inefficient. Let's consider that same method using this example. I'll do that again. How many different arrangements are there of the 11 letters in this word requirement, in which there are exactly 3 letters between the 2 R's? Exactly 3 letters between the 2 R's. How do you think about it? Now, these are letters. Letters, if there are 2 same letters, they're identical to each other. Okay. So what we can do is we can say, okay, there are 3 letters between the 2 R's. So we have one big box that has 2 R's on both sides. And then in the middle, in between those 2 R's, we've got 3 other letters. Okay. Now, let's think about these places: 1, 2, 3, 4, 5, 6, 7, 8, 9. In these 9 places, you would have these 9 letters, right? In how many ways can we arrange those 9 letters? We can arrange those 9 letters in 9 factorial ways. But then, how many of them are identical? 3. We divide by 3 factorial because of that. So for now, all we have done is we have arranged the letters inside the empty boxes. We have arranged these letters, these 9 letters in these 9 boxes. That's this 9 factorial divided by 3 factorial because of the 3 E's that we had there. But then this big box, this is one position in which it could be, that it could be on the extreme left. Another possible case could be that you have one box to the left of it and the others are on the right, and so on. You could have 2 boxes on the left and you have others on the right. You could have 3 boxes on the left and you have others on the right. So the idea is, how many different positions do we have for this big box? In how many other places could this big box be? It could be in its current position, or it could be here, such that this smaller box is on the left of it. So that's another possible position. Another possible position would be that it's here with 2 small boxes on the left and the remaining on the right. So that's 3 in total. 1 original, and then these 2, 3, 4, 5, 6, and then finally 7. This big box could come in 7 different positions. So we multiply this number by 7. It's equivalent to saying you've got 9 factorial over 3 factorial. That's one case in which this big box is here. Another case would be in which that big box is such that there's one small box on the left side, another case where you have two small boxes on the left side. So you have to add up all of these cases how many times? 7 times. So you can just multiply that by 7, and that gives you the total. That's 423360. You can doing this using the first method is very inefficient. That'll take too long. You'll have to consider cases. You'll have to consider cases like this, that there's no E inside, and there are 3 E's here. Then you can consider another case. You have 1 E here and you have 2 E's here. Another case, you have 2 E's inside, you have 3 E's, you have 1 E outside. Another case where you have 3 E's inside and 0 E outside. You'll have to consider 4 cases. That will become too long. So I would not recommend that you do that. Okay, that will be too long. For 3 marks, that's a lot of work. You'll have to make cases in that case. You cannot do that directly because unless you know what is inside, you would not know what to divide by, whether to divide this by something or divide this by something. It would not be possible without making those separate cases. So that's why I'm saying knowing this method is important. Otherwise, it will become too long there. Why are we just multiplying by 7 and not 7 factorial? We have already considered the arrangements of these boxes. It's already done when we did 9 factorial. In 9 factorial, we have already arranged those letters, right? The 9 letters in these 9 boxes. We have already arranged them. If you do 7 factorial, that would again arrange these outer boxes. That will be double arrangement. We don't have to do that. We've already taken care of them. The outer 6 boxes, they're already considered, their arrangements are already considered when we did 9 factorial here for these letters. These 9 letters come in these 9 places. So 9 factorial takes care of their arrangement. The only thing that is left is the possible positions of this big box. So this big box, this is the only thing that we are arranging now. We're not touching the rest of the boxes. This big box could go in 7 different positions. One its current position and 6 other positions. That's 7 positions in total. You multiply this by 7. Okay. All right. Let's move on. That's another case that you have to consider here. The rest of the questions at the end. Okay. Let's have a look at another case now. In how many different ways can we arrange these letters given that there are no restrictions? In how many different ways can we arrange these letters given that there are no restrictions? So we've got this word, Mississippi. If there are no restrictions, that's fairly straightforward. We say we've got 11 letters. That's 11 factorial. Divide by the factorials of the repeated letters. 4 factorial, 4 factorial, 2 factorial. That gives you the result. But then what if they say the 2 M's and the 2 P's and the M, they have to be next to each other. So 2 P's and M, they should be next to each other. They should be together. So what we do is whenever we want something to be some objects to be next to each other together, we put them in a single box. So we put the 2 P's and the M in a single box like this. Okay. Now what are the remaining letters? The remaining letters from that word are 4 I's and 4 S. In how many ways can we arrange this now? So in this case, we've got letters. So these are identical. These are identical. What's the number of arrangements that we get here? There are 9 boxes in total. That's 9 factorial divided by 4 factorial because of these 4 I's, 4 factorial because of the 4 S. That's the arrangement of these black boxes. But then inside this bigger box, we've got PPM. That's 3 letters in total. 3 factorial divided by 2 factorial because of the 2 P's that we've got here. We divide by 2 factorial because of that. Okay. And that gives us the result. You can see what that is. That's 1890. So if it was not books like before, if it was letters, then there's repetition. So we have to take care of the repetitions as well in this case. Now come the other kind of restrictions. Sometimes they want the objects to be separated. Sometimes they want the objects to be separated from each other. Again, the same scenario. We've got 6 math books, 4 physics books, 2 chemistry books. All of them are different. What we want to do is we want to arrange all of these books such that The chemistry books should not be next to each other. Chemistry books should not be next to each other. There are two chemistry books. We want to separate those two chemistry books. Now, how can we do that? One way to do that is that we say, let's find the total number of arrangements without any restrictions. That's 12 factorial because all of those books were different in this case. There's no repetition in this case. Subtract from that the case when the chemistry books are together, because once you subtract that case, in all the other cases, the chemistry books would not be next to each other. So we subtract the chemistry books together case from the total, and that will give us the result when the chemistry books are not together. Now, how do you find this, that the chemistry books are together? Remember, we did this earlier. There were 12 boxes initially. We merged two of them. That leaves us with 11 boxes. So that's 11 factorial. And then the chemistry books can be arranged in 2 factorial ways. We multiply them and we get the result from that. So that's what we do here. We subtract from the total 11 factorial into 2 factorial, and that gives us the result. Now, this is one way of doing this. You have to know this method. It's necessary for you to know this method. For separating two objects, we have another method as well. And that's something that you also have to know. You could also do it another way. And how's that? That is done using this method that we call the dashes and stars method. Okay. Now, what is it that we wanted to separate? We wanted to separate the two chemistry books. The two chemistry books had to be separated. And the remaining books, there were 10 books in total, right? Let's call them non-chemistry books. There's no condition on them. We don't want to separate them. We want to separate chemistry books, and we do not want to do anything to the non-chemistry books. Another way to think about that same question is that you have a representation like this, that you start with the dashes. The objects that you do not want to separate, let's start from them and make dashes for them. I'll summarize this later on as well. Start from the objects that you do not have to separate. So that's non-chemistry books. How many books are there? 10. So you have 10 dashes for them like this. You can make boxes here if you want. You can make dashes there. Making boxes separately, that's going to take time. So that's why we just use dashes in this case. In how many ways can we arrange these books? 10 factorial. 10 books, 10 places, that's 10 factorial. But now the chemistry books had to be separated. What we do is we say the chemistry books could come in these gaps between these books. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 gaps between these 10 dashes. There are 11 gaps in total. So now what about the chemistry books? The first chemistry book comes. How many choices does it have? How many options does it have? It has 11 choices, right? It has 11 options. So we multiply by 11. Then once one of those chemistry books is placed somewhere, for example, let's say this is C1, then the next chemistry book comes. How many options does that have? 10 options. So we multiply 11 and 10, and that gives us the result. That's the same thing as saying, when we do permutation notation later, you would realize it's the same thing as 10 factorial times 11 places. Arrange two books in those 11 places. That will be 11p2. So either of them, that will give you the result. That's the number of arrangements in which the chemistry books are not together. You have to know both of these methods, because sometimes you'll have to use the first one, sometimes you'll have to use the second one. In this particular example, both of them work. When you have to separate two objects, you can use the total minus together method. You can use the dashes and stars method. For two objects, both of them will work. Okay. However, let's consider this situation now. We had 6 math books, 4 physics books, 2 chemistry books. If the question says, not all physics books should be next to each other, what does that mean? Not all physics books should be next to each other. Not all? What does that mean? There were 4 physics books in total. What that means is, all of them cannot be together. All of them cannot be together. However, it is okay if we had 3 books together. That's okay. There's no problem with that. It's also okay if there were 2 together and another 2 together, or 2 together and the other 2 separated. It could be any of those. That's okay. The only problem is You don't want all 4 together. How do you find this? You find the total number of arrangements. Subtract from that the arrangements in which all the 4 physics books are together, and that will be 9 factorial into 4 factorial. Okay, so that will give it the result. Total minus together, that will work in this case. Okay. But if it was different, if instead of not all, they said none of the physics books should be next to each other, what does that mean? None of the physics books should be next to each other. That means all of them have to be separated. All of them have to be separated. Even 2 cannot be together. Okay. Even 2 cannot be together, 3 cannot be together, 4 cannot be together. What about this now? Now, in this case, we cannot use the total minus together method because we'll have to find this, this, and this, subtract all 3 of them from the total. And finding this is relatively straightforward, but these 2, they're actually quite complicated to figure out. 3 physics books together, exactly 3 together, and exactly 2 together, they become quite complicated. So total minus together is not feasible here. If we want to separate all the objects, in this case, we use the dashes and stars method. How do we use that? We want to separate the physics books. So non-physics books, the remaining 8 books, they do not have to be separated. We start from those books that we do not have to separate. That's 8. So we make 8 dashes for them. 1, 2, 3, 4, 5, 6, 7, 8. In how many ways can we arrange them? 8 factorial. But then we've got 9 gaps between them. We had 8 dashes. Between those 8 dashes, we've got 9 gaps. In those 9 gaps, we have to now place those 4 physics books. Now, the first physics book comes, how many options does it have? 9. The second one has 8. The third has 7. The fourth has 6. And that gives us the result. Alternatively, you could say that's the same thing as 8 factorial times 9p4. That we have 9 places, arrange 4 physics books in them, 9p4. And that will give the same result. That's how you separate all objects like this. So in the previous case, when it says not all should be together, we use total minus together. In this case, where we have to separate all of them, we have to use 8 factorial into 9p4. Yes, that's equivalent to that. So 8p8 and 8 factorial, they are the same thing. So in general, npn is the same thing as n factorial, as we'll see later in a few minutes. So yes, you could do 8p8 as well instead of 8 factorial. That's the same thing. Okay. So how does this method work? You make dashes for the objects that you do not have to separate, and then make stars for the objects that you do have to separate in the gaps between those dashes. And you should know when to use which method. When it says not all should be together, when it's more than 2 objects, and we want that not all should be together, we do total minus together. When it says none of them can be together, in that case, we use dashes and stars method. For 2 objects, both of them work. For separating 2 objects, both of them have the same meaning and they work. But for more than 2 objects, you have to be careful. You have to know for sure whether this would work or this would work. You have to think about that. Okay. Not all means total minus together. None of means you use dashes and stars method. Okay, let's have a look at this now. Again, the same books. If the chemistry books have to be together and none of the physics books can be together. So now they can sometimes combine both the conditions as well. Some books have to be together and some other books have to be separated. Some objects have to be together and some other objects have to be separated. How does this work now? So none of the physics books can be together, right? None of the physics books can be together. So what we do is we say, okay, physics books is what we have to separate. What is it that we don't have to separate? The remaining books. That's 8 books in total. So initially, we could make 8 dashes for them like this, right? 1, 2, 3, 4, 5, 6, 7, 8. However, we want the chemistry books to be together. If chemistry books are together, what we can say is let's merge two of these dashes so that we can place the two chemistry books in that single dash so that they remain together. Okay. In how many ways can we arrange this now? We've got 7 dashes. That's 7 factorial. Then these two chemistry books could switch places. That's 2 factorial. And then we've got 8 gaps between these dashes. 1, 2, 3, 4, 5, 6, 7, 8. So in these 8 dashes, we have to arrange 4 physics books. We can say 8p4, or we could also say for the first one, we have 8 options, then 7 options, then 6 options, then 5 options. You multiply all of them, and that gives you the result. Okay. So you have to know this dashes and stars method. Okay, let's consider that. That example is coming most likely. Let's have a look at this now. Now this is a bit complicated now. So why did I say that having 2 out of 3 or 3 out of 4 together is going to be difficult to find? Let's understand that using this example. Find the number of different ways in which the 9 letters of the word green cage can be arranged if exactly 2 of the G's are next to each other. Now, how many G's do we have in total? We've got 3 G's here. 1, 2, 3. We've got 3 G's. If we wanted all G's together, that would be straightforward. We would put those 3 G's in one box, and then we could just find that, right? Like we used to do earlier. If they want exactly 2 G's together, that's a bit problematic. Why is that? Because if you were to, there were 9 letters in total, right? So you can make 9 boxes initially. So you have 9 boxes like this. And now, if you put the 2 G's in one box, you can say, let's put 2 G's in one box like this. Now, then you could say there are 8 boxes in total. So that's 8 factorial. Divide by any repetitions. E's are coming thrice, so we can divide by 3 factorial, and then for the G's inside, we could say whatever the arrangements are, they can't be arranged. So we could do something like this, but that would be wrong because the problem here is the total number of G's in this case is 3. If we do it like this, that we put 2 G's in one box, that's not going to give us the number of arrangements in which exactly 2 G's are together, because if we put them in one box, there is a possibility that the third G ends up coming next to them, and that would make 3 G's together, and that's not what we want. So putting exactly 2 G's together like this is not going to be as straightforward as this. Now, one way of thinking about this could be, we could say there are 3 possible cases that we could have. 1, we could have all G's together. Number 2, we could have 2 G's together and 1 separated. Number 3, we could have all of them separated. We want the number of arrangements for this middle case where exactly 2 of them are together. So one possible way of doing this could be, which is slightly longer, I will discuss a quicker way after this. But one way to think about this could be that you say, find the total number of arrangements. That's 9 factorial over 3 factorial and 3 factorial, because we've got 3 G's there and we've got 3 E's. This is what we get, the total arrangements. Subtract from the total arrangements when all G's are together. Subtract this case. Subtract this case. We have done that before. And subtract this case when the 3 G's are all separated. I'm sorry, I should have written them with a gap like this. Where the 3 G's are all separated, subtract this case. All G's together, all G's separated. Find these 2, subtract them from the total, and that will leave you with this middle case, and that will be what you're looking for. Total minus together does not work because total minus together also leaves you with this option, right? Where all G's are separated. That's not what we want. We want exactly 2 G's together. We want exactly 2 G's together. So we can't have all of them separated. So that would not work. Okay, All right, so this is one way of doing this. We subtract from the total. We subtract from the total. How does this make sense? Because there are only three possible cases. We've got this possible case, all G's together. Second possible case, two G's together and one separated. Third possible case, all G's separated. These are the only three options that we've got. If we find the total, and we subtract from that this case and this case, what are we left with? The middle case, and that's what you want, right? We've got three possible cases. We know how to find two of them, but we want the third one, so we can subtract the two that we can find from the total, and that gives us that middle case. That's one possible case, the possible way of doing this. Now, another direct way of doing this would be like this. So what we want is, we want exactly two of these together. We want exactly two of these together. So we've got the word green gauge. We want exactly two G's together. Now think about the G's here. Think about the two G's here. The three G's here, sorry. The word is green gauge. We've got three G's and these six remaining letters. Right? We've got three G's and the six remaining letters. Now we want exactly two of these three G's together, and the one should be separated. So we can consider it like this. We could say, let's put two G's in one box and put the third G in another box. And now, since we want only the case where exactly two G's are together, we want to make sure that the third G does not come next to these two G's, because that would make all three G's together. So we put two of these G's in one box and one in another box. And now what we want to do is we want to separate these two boxes. How can we do that? These are the letters that we do not want to separate. R, E, E, N, A, E. We make dashes for them. 1, 2, 3, 4, 5, 6. That's 6 factorial. But then we've got three E's that are identical here. We divide by 3 factorial because of that. So for these 6 letters, we've got 6 factorial over 3 factorial number of arrangements. And now, how many gaps do we have between them? 1, 2, 3, 4, 5, 6, 7. In these 7 gaps, we can arrange these two boxes in 7p2 ways, and that will give you this directly. That's 5040. That's another way of doing this, much more efficient. That's what you could do here. So if you want exactly two G's together, you put two G's in one box, put the third G in another box, and then you say you want to make sure that these two boxes do not come next to each other. And that will ensure that you have exactly two G's together and not three G's, and you will get that case like this. Okay. Other questions at the end? I'll answer that once we're done with them. This method will always work. This will always work. When you have three objects and you want to separate two of them, this should work. If you had 4 objects and they wanted that 2 are together and another 2 are together, you could make 2 boxes like this and separate them. If they wanted that 2 are together and the other 2 are separated, you could make 3 boxes like this and then separate them. Okay. We did not exclude the third G. That's also coming somewhere, but it's just not coming next to the other 2 G's. So for example, we could have a case like this where 2 G's come here and third G comes here. We have another letter in between them, one of these 6 letters. So that ensures that we don't have all 3 G's together. We have only 2 G's together. 4 from 3? What does that mean? Okay, there's a Zan going on here. We'll have a 1-minute break. Other questions, I'll be answering them at the end. Let's move on after this. Keep a note of your questions. I'll answer them towards the end, okay? Okay. Why are we not dividing by the repetitions? There's no repetition here. This box has 2 G's in it. This has 1 G in it. These are different boxes. These are different objects. This is a different object. This is a different object. So we don't have to divide by anything. If we're talking about arrangements of the 2 G's, that doesn't matter. They're identical to each other. So why would we arrange them? These are identical to each other. Even if we were to arrange them, we would say 2 factorial, but then both of them are identical. We divide by 2 factorial. It doesn't make any difference. Now, within box, of course, they're identical, so they're not going to be arranged. Yes, so if both of the objects were identical, so if we had, for example, a G and another G, then yes, we would have to divide by 2 factorial in that case. Or if we had a box like this and another box like this, then we would divide by 2 factorial as well. But these boxes are different from each other, so we don't have to do anything. Okay, all right, let's move on. Let's look at this example. This is pretty straightforward. So you talked about most of the cases that you would get in arrangements. Let's have a look at a couple of questions on this. Then we move on to permutations, combinations, notations. Let's say you've got this word Argentina. It includes the 4 consonants R, G, and T, and the 3 vowels A, E, I. Find the number of different arrangements of all the 9 letters. That's fairly straightforward. But then the number of arrangements in which we have a consonant at the beginning, then a vowel, then another consonant, and so on alternately. Again, another case that you will see frequently in the recent papers. Consonants and vowels are coming alternately. So the first has to be a consonant. They said that you have a consonant at the beginning. If they had not said that, we would have to consider 2 possibilities. It starts from consonant or starts from vowel. In this case, they have told us that starts from consonant. So that means this has to be a consonant, this has to be another consonant, then C3, C4, C5. And in the gaps between them, we've got the vowels. There are 4 vowels in total, V1, V2, V3, V4. Now, in how many ways can we arrange the consonants? There are 5 of them, 5 factorial, but then 2 of them are identical, n and n, we divide by 2 factorial because of that. And then the vowels, there are 4 of them, that's 4 factorial, but A's are identical, we divide by 2 factorial because of that. Multiply them, and we get the result from that, that's 720. Okay. All right, let's move on to the next one. That was part 2. Okay, so this is a case now where you have to make this is an example now where you have to make multiple cases sometimes. So let's look at this example. It says, find how many different 4-digit numbers can be made using only the digits 1, 3, 5, and 6 with no digit being repeated. Now, the first part is fairly straightforward. That's just 4 factorial, that's 24. The second part, I'm just going to focus on that. The second part of this, find how many different odd numbers, what I'll do is just get rid of this here. Find how many odd numbers greater than 500 can be made using some or all of the digits 1, 3, 5, and 6 with no digit being repeated. Now, how do we think about this? We've got 1, 3, 5, 6. These are the 4 numbers that we've got. They cannot be repeated. The number has to be greater than 500 and it should be an odd number. Now, how do you think about this? Greater than 500, it could be a 3-digit number, it could be a 4-digit number. So we have to consider both of those possibilities, 3-digit and 4-digit. Now, let's start with 3-digit first of all. If it's a 3-digit number, if it's greater than 500, then the first number, the first box, so we have 3 boxes, right? The first box could either be a 5 or it could be a 6. Only then the number would be greater than 500. And it has to be an odd number. So the last digit, it has to be either a 1 or a 3 or a 5. But now we've got a problem. Because if you have 5 in the first box, if the first box is a 5, then the last box, how many options would that have? Only 2 options. If the first box is a 6, then the last box would have 3 options. So depending on what you have in the first box, the number of ways that you have for filling the last box, that changes. So we cannot do it directly. There's no way to do it directly. We would have to make multiple cases for this. Okay, because there's ambiguity. So if we say there are 2 options for the first box, there are 2 ways of filling the first box. What about the last box? We have to first fill the boxes that have some conditions in them. So what boxes have conditions? The first box, because that will ensure that the number is greater than 500. If the first number is, the first digit is 1 or 3 in a 3-digit number, the number would be less than 500. We don't want that. So for the number to be greater than 500, the first digit has to be either a 5 or a 6. So we have two ways of filling the first box. But then if it's an odd number, how many ways do we have for filling the last box? Now, it depends on what we have in the first box, because if we have 5 in the first box and the last box has only 2 options, 1 and 3. If we have 6 in the first box, then the last box has 3 options. That's 1, 3, 5. So what we have to do is we have to break it into 2 parts, make 2 different cases for this. One case in which we say the first digit is a 5. In that case, the last digit could either be a 1 or it could be a 3, so that the number remains an odd number. That's one possible case. So in how many ways can you do this now? Now 5 is fixed. We can't change that. For the last box, we've got 2 options, and then we have 2 digits left. They could come in the middle box. So 2 times 2, that is 4 for the first case. You start from the box that has some condition on them. You start arranging those objects or those places that have some condition. So condition is on the first box and the last box. So first of all, you have to arrange those boxes. First is a 5. That's only one option, right? Last could be 1 or 3. So we've got 2 options for that. Once we fill the last box as well, for the middle box, we have 2 options left. That becomes 4 in total. The second case would be that the first digit is a 6. In that case, the last digit could either be a 1 or a 3 or a 5. So that means in this place, we have 3 options. And then we have 2 left for the middle box. That's 2 into 3. That becomes 6. These are 2 possible cases. And the third possible case would be that you have a 4-digit number. If it's a 4-digit number, that's necessarily going to be greater than 500, right? It will always be greater than 500. So there's no condition in the first digit then. The only condition is on the last digit. The last digit could either be 1, 3, or 5. We've got 3 ways of filling that. And then once we have done that, for the remaining 3 boxes, we've got 3 digits, 3 boxes. That's 3 factorial, or you could say one of them has 3 ways of filling, the other has 2, and the other has 1. That's 3 into 2 into 1. That's equivalent to 3 factorial. And that gives us 18. Add all of them up, because it could either be this case or this case or this case. There's an or between these cases. We add all of them up and get the total result from that. So sometimes what we have to do is we have to make cases like this. Okay, we cannot do it directly. We have to make cases like this. Makes sense? Makes sense? Yeah, this is tricky. It requires a lot of practice, a lot of practice. Of course, you have to, these are standard methods that we're doing. But then once you've done all of these, then out of the 10 marks, 7, 8 marks generally are going to be fairly straightforward. Once you have practiced these enough. In permutation combinations, enough practice means like 70, 80 questions. Right? So you should have done at least that much until now in total before the exam. Why can't we take 6 in the first box? We considered that option, right? We had to make that as a separate case. Okay, let's move on. Okay, so we've been talking about arrangements. The topic name is permutations and combinations. what are permutations? What are combinations? We haven't even talked about them. Permutations, as I said, is another name for arrangement, right? So now we used factorials until now for all of those arrangements. Where do permutation notations come in? Let's think about this. So permutations is another word for arrangement. Let's consider this scenario. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. How many 6-digit numbers can we write using these 9 digits so that no digit is repeated? Now, earlier we could think of it like this. That it's a 6-digit number. So the first box could have 9 options, right? Any one of these nine digits could come in this place. The second has 8 options. The third has 7 options. The fourth has 6 options. The fifth has 5 options. And then this one has 4 options. You multiply all of them and you get 60,480 from that. Alternatively, you could do it directly like this. You could say there are 9 objects. You want to arrange them in 6 places. That's 9p6, and that gives you 60480. You could do it directly using permutation notation. So what does this notation mean? 9p6 means arrange 6 out of 9 objects. In general, we could say NPR, that means arrange R out of N objects. That's what this notation means in general. Okay. This is the formula for this, but that's not very important for now. Let's consider this situation. We have 15 people who walk into a room with 9 chairs. How many different seating arrangements are possible for them? We've got 15 people, 9 chairs. We have to arrange those 15 people, arrange 9 out of those 15 people. That's just 15p9. If we have 9 people and 15 chairs, so it's the other way around now. 9 people and 15 chairs. And we have to arrange these people. We just change our perspective. So earlier we were thinking of it like this, that for the first chair, you have 15 options. For the second chair, you have 14 options. For the third chair, you've got 13 options, and so on. So that becomes 15 into 14 into 13, and so on, all the way up to 7. That's 15p9 directly. Out of 15, arrange 9. This is just the other way around. You are thinking of it like this. The first person has 15 options. The second person has 14 options. The third has 13 options, and so on. This also ends up being the same thing. That's 15p9. Now, I won't go into detail about this. You can find that in one of those videos in which I've explained this. But the takeaway from this discussion is, whenever you are arranging objects, so let me just show you the results from this directly. We had 15 people, 9 chairs, 15 objects, and 9 places. 15p9 is the number of arrangements that we get from that. If we switch that, the number of people, the number of objects, if that's less, and the number of places, that's more. Again, if you want to arrange them, whatever is the bigger number that comes here, whatever is the smaller number that comes here, that's also 15p9. If that number is equal, 15 people walk into a room with 15 chairs, and that means just 15p15. And that's equivalent to saying 15 factorial. That's equivalent to 15 factorial. When the number of places and the number of objects that's equal to each other, you could use factorial as well in that case. So the result from that is, whenever the number of objects and the number of places are equal to each other, in that case, we can use 9 factorial. For example, if we have 9 objects, we want to arrange them in 9 places, we say 9 factorial. We've got 7 objects, we want to arrange them in 7 places, that's 7 factorial. We could also say NPN, right? We could say 9p9 for the first example that I said, 7p7, they're the same thing. In this case, you could use any of them, factorial or this permutation notation. However, when the number of objects that you're arranging is not the same as the number of places, when these two are not the same, in that case, we use the permutation notation. We say NPR. Whatever is the larger number that comes on top, whatever is the smaller number that comes here, and that gives you the result. Okay. So when this is not the same, in that case, you use this permutation notation. You've done this before. in the examples that we looked at earlier in arrangements. For example, here, for instance, we had 8 places for these physics books, 9 places for these physics books, and we had 4 of these books. We just said 9p4, right? That gave us that result directly. So that's the idea. You can use permutation notation. You can use permutation notation to calculate this directly like this using NPR notation. Okay. Now, there's a logic behind it where this comes from. So this is the formula. NPR is n factorial to n minus r whole factorial. So when you multiply those individually, like we did here, 9 into 8 into 7 into 6 into 5 into 4, this permutation notation actually does that exactly same thing. You end up with the same result as that, but you can just put this on a calculator directly as 9p6 and you would get the result. You would not have to do all of this manual work in that case. Okay. But again, that's out of the scope of revision right now. The second thing is combinations. How many permutation questions come in the exam? Sometimes one big question, sometimes 2 relatively smaller questions. You can say 10 to 12 marks. 10 to 12 marks. Sometimes the probability question that you get, and that as well, you can use combinations, although it's not required. There are going to be alternatives as well, but the simpler way of doing those questions sometimes is going to be using combinations. So you can say 10 to 12 marks minimum 10 to 12 marks. Okay, out of which 7, 8 are going to be relatively easier. For the remaining, you would have to think more. But 7, 8 are generally going to be relatively easier if you have covered all the basic concepts, all these standard methods. If you know all of these standard methods, these are all standard methods that you would need to know. Then 2 out of those 3 parts are generally going to be fairly straightforward. If you have done all of these efforts before, then they're going to be straightforward. And then for one part, in some very difficult questions, you would have to think a bit more. That you have to do in the exam. That will depend on how well you've practiced and how well you understand the concepts. But 7, 8 marks generally going to be relatively easier to figure out. The second thing is combinations. Now, combinations is when you are selecting some objects and the order is not important in that case. So we're not arranging them. We're just selecting objects without caring about the order. Okay. Now, the keywords that you would see in this case would look like this, that you have to select objects, you have to choose objects, you have to make a group of something, you have to make a team of something. All of these mean you're talking about combinations, because in this case, in these cases, arrangements don't matter. Okay. Let's take some examples. Let's say we've got this. How many different teams of 2 people can be made from 3 people, A, B, and C? We just say 3C2. In this case, that gives us 3. Now, what's this notation? NCR, this means select R out of N objects. Select R out of N objects. Now, if you were to arrange them, that would be 3P2, and that's 6. Those 6 arrangements would be like this: AB, BA, AC, CA, BC, CB. But when you're selecting objects, the order does not matter. So these 2 are going to be the same. These 2 are going to be the same. These 2 are also going to be the same. So in combinations, you only have these 3 cases. There are 3 different possible selections that we've got for this. Okay, so for that, we do 3C2 like this. Now, this is something important. This is the relation between permutations and combinations, how they're connected to each other. NPR, that means arrange R out of N objects. Now, while it works, it basically does 2 things. When you say arrange R out of N objects, that means you have to select R out of N objects and then arrange those R objects that you've selected. So we could say NPR, therefore, is the same thing as NCR, that you select R out of N objects, and then you arrange those R objects. Arranging R objects as just R factorial. So that's the relation that we've got between permutations and combinations. Why is it important? Because sometimes you will see, as we'll see in some examples, you have to do arrangement, but you end up having to use combination there as well for arrangement. Why would that be? Because there would be some condition on selection that they would have applied. For example, if there are 10 people and there's some condition on selection that there are two brothers who should both be selected or should both not be selected. Now, if there's some condition, then you have to, in condition on selection, you first have to apply combinations to select applying those conditions. And then if you had to arrange those selected people, you would do arrangement separately. So sometimes it's an arrangement problem and you have to do combination first of all, and then do arrangement afterwards because of that extra condition that might be there sometimes. I'll show you some examples of that. Let's have a look at this. How many different teams of 3 people can be made from 4 people, A, B, C, and D? That's fairly straightforward. We want a team of 3 people. There are 4 people, 4C3, that turns out to be 4. Now, if it says a delegation of 3 boys and 4 girls is to be selected from a class consisting of 10 boys and 15 girls, how many different delegations can possibly be selected? Again, we're talking about selections, that's combinations. We want 3 boys out of how many boys? Out of 10 boys. So that will be 10C3. 4 girls out of 15 girls, that's 15C4. So this turns out to be 10C3 times 15C4. Multiply these two and that gives you the result. That's 16, 163,800. Okay. Select 3 out of 10 boys and select 4 out of 15 girls. You multiply both of them. Let's have a look at this now. There's a group of 12 people, 8 boys and 4 girls. We need to arrange 3 boys and 2 girls from this group in a straight line. In how many ways can this be done? Now you see there's a condition. There's a condition that there have to be exactly 3 boys out of those 8 boys, and there are 2 girls out of those 4 girls. Now we cannot directly do this. It's arrangement. Arrangement means we're talking about permutations or factorials. We have 12 people. We have to select 5 and then arrange them. 12p5 would not work because that would not ensure that there are 3 boys and 2 girls. 8p3 times 4p2 would also not work because that would mean you are arranging the 3 boys separately and the 2 girls separately. That also does not work. They don't want them to be arranged separately. Those 5 people have to be arranged together. So how do you deal with this? Now, first of all, you take care of that condition that's given. The condition is you want 3 boys out of 8 boys, that's 8C3. And you want 2 girls out of 4 girls, that's 4C2. Once you have selected these 5 people, this is how you select those 5 people. Once those 5 people are selected, then you have to arrange them. In how many ways can you arrange 5 people? 5 factorial, you multiply by that. So it was an arrangement problem. However, there was some condition on selection first of all. So we first handled that condition using combinations, and then we multiplied them. Okay. Yes. So when there's an or between cases, we add them. When there's an and, we multiply them. Make sense? Okay. Let's move on. Let's consider this now. There are 5 people, A, B, C, D, E. You need to select 3 of them for a competition. What's the probability that a randomly chosen team would have B in it? Now, sometimes they ask you for probability like this as well. Now, we have done probability already. That's number of favorable outcomes divided by the total number of possible outcomes. Probability can come with permutations and combinations as well. In this, the formulas would look like this. If it's permutations, we can say number of favorable permutations divided by the total number of possible permutations. If it's combinations, we could say number of favorable combinations divided by the total number of possible combinations. So we can find probability in combinations and permutations like this as well. Let's look at this example. There are 5 people, A, B, C, D, E. You need to select 3 of them for a competition. Now, 5 people, they're all different. We have to select 3. That's just 5C3. Okay. If there was no restriction, the possible selections would be 5C3. Now they're saying, find the probability that a randomly chosen team would have B in it. So that means B should be selected. B should be selected. What does that mean? B must be selected. If B must be selected, we can say there are 3 places in the team. 3 people have to be selected. So there are 3 places. If B has to be there, then 1 place is already occupied by B. How many options do we have for the remaining people now? We've got 4 people left. Out of those 4 people, we have to select 2. So that's 4C2. And that turns out to be 6. So the number of possible teams in which there is B, that is 6. What's the probability going to be? 6 divided by the total, which is 5C3. That's 10. 6 over 10, that gives you the result 3 over 5. That's the probability that we were looking for. So you can find probability like this as well. Find the number of favorable combinations, the combinations that satisfy the condition, divide by that by the total number of combinations, and that gives you the result. Sometimes it can become a bit more complicated. For example, what if you've got this? In how many ways can you select 3 letters from A, B, C, D, E? Now, in arrangements, when we had repetitions and we had to do arrangement, we used to divide by the factorials to, handle those repetitions. So in this case, if we had to arrange this, we would say 6 factorial divided by 2 factorial. We used to divide by factorials to handle repetitions. In combinations, there's no direct way of handling repetitions. In combinations, whenever you have identical objects or repeated letters, you always have to make cases. You have to make multiple cases for the repeated letter. For example, if they want you to figure out the number of ways in which you can select 3 letters from A, B, C, D, E. Now, the problem is the A's are repeated here. We cannot directly do 6C3. That would not work because we haven't got 6 different letters here. These are 4 different, and then there are 2 identical. Okay, that would not work. In repeated, that combination notation only works if all of these objects were different. So what do we do then? We have to make cases for this. A's are repeated, so we consider the possible cases for A. One possible case could be that there is no A, and we have to select 3 letters. So out of the remaining 4 letters, we have to select 3. That's 4C3. That turns out to be 4. The second possible case would be that there is 1A. So 1A is selected. Now for the remaining 2 places, we've got 4 options. So 4C2, that's 6. And then the third possible case could be that we have 2 A's. So we have 2 A's here. And then for the third place, we've got 4C1 option. That's 4. It's either the first case or the second case or the third case. We add all of them up, and that gives us the result. That's 14. And that's our final answer. Okay. So in combination, when you have repetitions, you have to make cases. You cannot do it directly. Sometimes you can have multiple letters that are repeated. For example, like this. You've got A, B, B. You've got 2 letters, 2 objects that are repeated like this. You have to select 4 letters from this. Now you have to make cases for both of them. You have to make cases for A and B. Both of them are repeated here. So what would be the total cases? Figure out what happens if we have 0A, 0B. 0A, 0B is not possible because in that case, you only have 3 other letters left, right? C, D, E. We can't have 4 letters out of 3. So that would not work. So we want at least one of them. So one possible case would be with 0A, you can have 1B, you can have 2Bs. With 1A, you can have 0B, 1B, 2B. With 2A's, you can have 0B, 1B, 2Bs. These are all the possible cases that we've got. These are all the possible cases that we've got. Okay. Now, for the first one, we say there has to be 1B. So 1B is already there now. It doesn't matter which one of them is there. It doesn't matter which one of them is there because the letters are identical, right? So it doesn't matter if it's this B or this B. It does not matter. It could be any of those Bs. So we don't have to select the Bs out of this in this case. For the remaining letters which are different, we say that's 3 letters remaining. We have to select 3 of them. That's 3C3. All right. Then If you want two Bs, then you have two remaining places. Out of the remaining three letters, we have to select two. That's 3C2, and so on. We have all of these cases. For example, here we have 1A, 2Bs. That means we've got 1A, 2Bs already there. For the one remaining place, we have three options, CDE, 3C1. That will be this. Find all of these cases like this, add them up together, and that gives it the result. That's 18 total different selections that are possible from this, in which we have four letters. Okay. Now, for the identical letters, we don't choose from them because it doesn't matter whether it's which A it is. It doesn't matter. When we're finding number of selections, that does not matter. Okay. So in combinations, identical objects cannot be handled directly. We need to make multiple cases for the identical object to find the total number of possible combinations. We cannot handle them directly like we used to do in arrangements or permutations. In combinations, that's not possible. Let's consider this scenario. This is another possible case, that possible type of question that you will see. So Jeff wishes to plant 25 flowers in a flower bed. He can choose from 15 different geraniums, 10 different roses, 8 different lilies. He wants to have at least 11 geraniums and also the same number of roses and lilies. Find the number of different selections of the flowers that he can make. So in a lot of combination questions, you have to make cases like this as well. You've got 25 flowers in a flower bed. You've got 25 flowers. Okay, so you have to plant 25 flowers. You've got 15 geraniums, 10 roses, 8 lilies. Okay. Now, the total number has to be 25. There should be at least 11 geraniums. So now you have to make the different cases that are possible for this. So one case is we've got 11 geraniums, and then the number of roses and lilies, they have to be the same. So the remaining are 14, 25 minus 11, that's 14. So these are 7 and 7, that's one possible case. Another possible case would be that you've got 13 geraniums. 12 is not possible because if we have 12, then the remaining are 13. They cannot be equally divided. We want the same number of roses and lilies. So 12 is not possible. We have 13 geraniums. In that case, the others will be 6 and 6, 15. The others will be 5 and 5. And now we say the first case is out of the 15 geraniums, we have to select 11. Out of 10 roses, we have to select 7. Out of 8 lilies, we have to select 7. That's 15C1 into 10C7 into 8C7, and that gives us the result. Similarly, you do the next one and the next one. In this case, all the flowers are different. So we have to select from all of them, right? We have to select from all of them. In the previous case, we were talking about letters, and letters, these were identical letters. So we did not have to choose for them. Okay, they could be, their selection would not matter because they were identical to each other. Okay. So we'd have cases like this as well, in which you have to, make a table-like structure like this and then find the combination for them. No, the question says that it has to be the same number of roses and lilies. That's the condition in the question. Okay, all right. If there was no condition, then of course we would consider that as well. Let's consider this. 5 of the 11 letters in the word requirement are selected. How many possible selections contain at least 2 E's and at least 1 R? Okay, how do we think about this? Again, we're talking about selections, combinations. We've got repeated letters here. Some letters are repeated. So we have to make cases for whatever are the repeated letters. Which letters are repeated? R's are repeated and E's are repeated. So we have to make cases for them. Now, the condition is at least 2 E's and at least 1 R. What are the remaining letters which are not repeated? These letters, there are 6 of them. Q, U, I, M, and T. Okay, so what are the possible cases now that satisfy these conditions? 2 E's, 1 R, that's one case. So we have 2 E's and 1 R already there. We have to select 5 in total. We have 2 places left. Out of the remaining 6 letters, we say, let's just select 2, that's 6C2. Okay, and that gives us a result. And then for the second case, another possible case could be with 2 E's, you could have 2 R's. That's 4 letters already selected. For the remaining one place, you have 6 options. So 6C1, that gives you another value. Similarly, for the rest of the cases, 3 E's, 1 R, 3 E's, 2 R's, add all of them up, and that gives you the result. You can see what that is. Okay. Now in this question, so this is the general way of doing this. This is the general way of doing this. Okay, that will work for any question like this when they talk about number of possible selections. When they talk about number of possible selections, this is the general method that would work in such problems. But in this particular case, for those of you who are who have practiced well and are good at this topic, there could be a more efficient way of doing this in just one single step. Since combination does not work when you have repeated letters, in this case, the conditions are like this. They're saying there should be at least two E's. Okay, so we have 5 letters that we have to select. We've got 5 letters that we have to select, right? 1, 2, 3, 4, 5. They're saying there should be at least two E's. That means two E's have to be there no matter what. At least two E's have to be there. And at least one R has to be there. So at least one R has to be there. Now, if we get rid of two E's and one R from this total number of letters, what are we left with? Two E's and one R. So we have R, E, Q, U, I, M, N, T. Right? I've gotten rid of two E's and one R. And that leaves me with this. Now, all of these letters you see in this case, in this particular case, are different. These are 8 letters in total. Out of these 8 letters, now since we know that these 3 have to be selected, out of those 8 letters now, we have to just select 2. We could directly do 8C2 here, and that will give us 28. That will be a 4-mark question. You just do this, 8C2, 28, and that's it. That's your final answer. But that only works in this case because of the condition that's given. The condition is such that when we have 2 E's and 1 R, the remaining letters are all different. So we could just use combination directly on this. So yeah, that will work. That will be, I think, at least a 4-mark question. You could write that directly like this, and that will be fine. Okay. If you get that, that's great. Otherwise, this is the general method that will work for every kind of question like this. You make cases for the repeated letters. Okay. Now, this is important. A very similar question, but we do it differently. In the previous case, we were talking about number of possible selections that contain at least 2 E's and at least 1 R. Number of possible selections. Now, in this case, we're saying, find the probability that the selection contains at least 1 O and at least 1 R. Okay, now how do we think about this? 4 letters are selected at random from these 8 letters in the word tomorrow. Find the probability that the selection contains at least 1 O and at least 1 R. Now, 4 letters. What could be the 4 letters that you could select? The problem here, let me just quickly tell you about the logic behind it. Then if you understand it, that's good. Otherwise, I'll tell you what to remember. One possible selection of the letters could be satisfying this condition. You could have T, O, M, R. This is one possible selection. Okay. Another possible selection could be T, O, O, M. Now, these are 2 different possible selections. Their probabilities are not the same. Their probabilities are not the same. Why are the probabilities not the same? After permutation and combinations, it'll take, I think, around 15 more minutes, 15, 20 more minutes. After that, we'll have a break. Okay, so consider these 2 possible cases. Possible selections, TOMR and TOM. Okay. Now, these 2 do not have equal probabilities. Why? Because we've got 3 O's. So probability of getting 2 O's is more as compared to getting some other letter twice. Since some letters are repeated, probability of selecting an O from this 8-letter word is more as compared to selecting a W, for instance. Probability of each outcome is different. Since the probability of each outcome is different, if we were to do it directly like this, the probability formula, remember, that would not work. The number of favorable outcomes divided by the total number of possible outcomes, that formula, as we discussed in probability, assumes that each outcome has equal probability. So we cannot do it like this, that we find the number of selections like we did here in the previous case. Divide that by total number of selections. That would not give you the correct result. So how do you handle this? Whenever you have a probability problem, whenever you have a probability problem, in order to use that formula, number of favorable outcomes divided by the total number of possible outcomes, the condition is the outcomes need to have equal probabilities. In this case, because of these letters being repeated, some letters have more probability of selection as compared to other letters. So what we do is, whenever we have probability and combinations and there is repetitions, whenever these three conditions are met, you have to memorize this now, okay? Whenever you have probability, combinations, repetitions, okay? Probability, combinations, and there is something repeated in that set of objects, set of letters, you treat all letters as different. You treat all letters as different so that you equalize their probabilities. So you consider it like this. So this is O1, this is O2, this is O3. This is R1, this is R2. So treat all of them as different objects, okay? Then you handle it like you handled this flower case earlier, right? So you do it like this, you say, okay, if all of those letters are different, then we could just use combination notation directly. 8C4, out of 8 letters, we have to select 4, that's 70. That's the total number of possible selections that we can get in this case. 8C4, that's 70. And then how many of them satisfy the condition? We make cases for them. There are 3 O's. Remember, we're considering all of them as different. We're considering all of them as different. There are 3 O's. There are 2 R's. And there are 3 remaining letters. Let's merge them together as well. They're T, M, W. They're all different. That's the third category of letters that we've got. Now, what's the condition? We want at least 1 O and at least 1 R. So make cases for them. Total number should be 4, 1, 1, 2, 1, 2, 1. Now, do it in a structured way. Fix one and then change the others. For example, you could do something like this. With 1 O, what are the options that you can have? 1, 2, 2, 1. And then with 2 O's, what are the possibilities? 2, 1, 1, 2, 2, 0. With 3 O's, you could have 1, 0, right? These are all the conditions, that's all the possible cases that satisfy both of these conditions. You find their number of selections. Now, in this case, you see what's happening. We are doing 3C1. We're doing 2C1 as well, because we are treating these letters as different. So we have to select those letters as well. In probability, in combination problems, you have to select those repeated letters as well. When we just find number of selections, in that case, we don't do this. Okay. So you find all of those cases, add them up together, that gives you 50. 50 divided by the total number of possible combinations, that's 50 over 70, that's 5 over 7. That's the probability that you get from this. This is coming a lot in recent papers. You need to remember this condition. Probability, combinations, repetitions. When these 3 conditions are met, treat the letters as different categories. Okay. All right, let's move on. So hopefully we'll be ending in 10-15 minutes, inshallah. Hopefully around 10 minutes. Okay, so that's a lot. I hope you've gone through this earlier already, and it's not the first time that you're doing this. Just then it will be a lot of work over the next few days then to practice this as well. Okay, let's have a look at this now. We have some people who are taking a photograph. The members will stand in 2 rows with 5 in the back row and 4 in the front row. And how many different ways can 9 members be divided into a group of 5 and a group of 4? We want to divide people into groups. What's that? That's combination, right? We're making groups of people. Order does not matter here. How can we do that? There are 9 people in total. How many groups can we make out of them? How many possible different groupings can be there? We can say out of 9 people, make a group of 5, that's 9C5. And then out of the remaining 4 people, select 4, that's 126. Now, once you have selected 5 people, it's understood that the remaining 4 people are going to go into the other group. So if you just do 9C5 in this case, that will also give the same result. 4C1 is just 1. So that's 126. You could also do the other way around. It doesn't matter. You could say 9C4, make the 4-member group first. And then the remaining 5 people, you put them in the other book, and the other group. That's also 126. You can start from any of the groups. It doesn't matter. Okay. Then it says, for a random division into a group of 5 and a group of 4, find the probability that Raman and Sanjay are in the same group as each other. So these are 2 people. What's the probability that they are both in the same group? Now we have to make cases for this, right? If they're in the same group, we are not sure which group. They could be in the five-member group. They could be in the four-member group. So this is the five-member group. This is the four-member group. One possible case is that they're both in the five-member group. If they are here, then we want to find the probability, right? Probability that Raman and Sanjay are in the same group as each other. Okay. Now we already found the total number of groupings. That's 126. What are the number of groupings that satisfy this condition? So one is in which R is R in the first group. That means for the remaining 3 places, we've got 7 remaining people, 7C3, and then the remaining 4 people, 4C4. That gives us 35. If Raman and Sanjay are in the second group, if they are here, what about this now? We've got 2 places left in this group and 5 places here. We could say out of the remaining 7 people, apart from Raman and Sanjay, we've got 7C5 here, and then 2 people left, that's 2C2. And that gives us the result, that's 21. It's either the first case or the second case. We add them up together, and that gives us the total result. That turns out to be 56. And that's our final answer. Makes sense? This is not the final answer. This is the number of selections satisfying this condition. And what's the probability? I think I forgot it when I copied this. What's the probability going to be? That would just be 56 divided by the total number of groupings. That's 126. And that will give the result. You can see whatever that is. Okay. But now let's look at this. In how many different ways can the 8 children be divided? So it's some other different question. In how many different ways can 8 children be divided into 2 groups of 3 and 1 group of 2 to go on the roller coaster? Okay, so how do we think about this now? We've got 8 people. We have to make 2 groups of 3 and 1 group of 2. So we can say those 8 people are A, B, C, D, E, F, G, H, right? We can start from any of the 3 groups. We can say, let's select a 3-member group, 8C3. Then we have 5 people left. Select another 3-member group, 5C3. We have 2 people left. That's 2C2. Now, generally, that's what we would do in this case, just multiply these. However, there's a complication here. And that complication is, there are 2 groups that have the same size. There are 2 groups that have the same size. They are both 3-member groups. What does that mean? If you have one grouping in which you have 2 people here, GH, ABC here, and DEF here, and another possible grouping in which you have DEF in the first group, ABC in the second group, and GH in the third group. These 2 are actually same groupings. It's the same groups. There's no difference between these groups, between these 2 groupings, right? We've just switched them. The order does not matter. These are both the same. This will be counting these 2 groupings as different groupings. So we have to get rid of this double counting. In how many ways can these groups be arranged? 2 factorial, we have to divide by that to get rid of that double counting. Otherwise, it will be counting these 2 groupings as different. In the previous example, we had one 5-member group and one 4-member group. We did not have this problem in that case. They were both different size groups. In this case, it is selection. That is why the order does not matter. The order does not matter, right? This is selection. The order should not matter. But what this is doing is, what 8C3 into 5C3 into 2C2 is doing is, it is considering these 2 as different groupings. These 2 as different groupings. Okay, it's considering these 2 as different groupings. So these are not different because they're both identical. There's no difference in them. So we have to divide by 2 factorial because of that. You can try this with a smaller example. So for example, think of making 2 groups of, we have A, B, C, D. Make 2 groups of 2 people each, right? Write them down. If you do it directly, that will be 4C2 into 2C2, and that gives you 6. But when you actually start writing them down, what are the possible groupings that you can have? You can have AB and CD. You can have AC and BD. You can have AD and BC, and that's it. There's no other grouping that you can think of. Even if you try writing something down, for example, you can try BC and AD. Isn't that the same thing as this? You can try BD and AC. That's the same thing as this. You can try CD and AB. That's the same thing as this. So in actual, we only have 3 different groupings because these 2 are identical. These 2 are identical. And these 2 are identical. These 2 are identical. So actual different groupings is only 3 different groupings. This is giving us 6. We have to divide this by 2 factorial because these 2 are the same. To get rid of that double counting, we divide by 2 factorial, and that gives us 3, and that's the actual answer. We've got only 3 different groupings here. So whenever you have groups like this, in which the size of the groups is the same, you have to get rid of that double counting like this by dividing by 2 factorial. Okay. Just 2-3 more examples quickly. So in the previous case, we did not have equal size groups, right? In this case, we did not have equal size groups, so we did not have to do that. In this case, we did have equal size groups, so we have to divide by 2 factorial because of that. Okay. Now, sometimes, we've already discussed this before. I said, let's just do the first part of this. We've got 2 identical cans of green tea, 2 identical cans of orange tea, and 3 identical cans of cola. Find the number of arrangements if the first and the last cans are the same type of drink. Same type of drink, what does that mean? It could be both colas, it could be both green tea, it could be both orange juice. So we consider 3 different cases, one in which we've got C's at the ends, G's at the ends, O's at the ends. Now, when you fix them, again, this is happening a lot in recent papers, they fix some object somewhere. So in this case, the first and the last are the same kind of drink. Now, in the first case, we are saying this is a cola and this is a cola. Now, these are fixed. We don't have to worry about them. We don't have to arrange them anymore because they have to be at those extreme positions, right? At the end and in the beginning. We only have to arrange these middle objects. That's all that we have to arrange. In how many ways can we do that? 5 factorial over 2 factorial and 2 factorial for the first case, and similarly for the others, add all of them up, you get the total result. So when they fix something like this, you don't have to arrange those fixed objects, only the rest of the objects. Okay. Okay, one last example. And I'll show you that one last one after this. You can just have a look at this, look at that yourself. And yeah, we're just ending. We'll have a break in a few minutes. Just one last question I'll explain. Just a couple of parts of this, and then we stop after that. So there are 9 cards, each of a different color. 9 cards, each of a different color. They are to be arranged in a line. How many different arrangements of the 9 cards are possible? Now that's really straightforward. That's 9 factorial. How many different arrangements do not have the pin card next to the green card? You can use the dash and stars method or total minus together because you only have to separate 2. So both methods would work. You can do that as well. Just focus on the 3rd, 4th, and 5th parts. Consider all possible choices of 3 cards from the 9 cards, with 3 cards being arranged in a line. What does that mean? All possible choices of 3 cards from the 9 cards. So from the 9 cards, we have to select 3 cards. Okay. And now those 3 cards are to be arranged in line. In how many different ways can you arrange those 3 cards? Now, out of 9 cards, we have to arrange 3. We could directly do 9p3 for that. Or we could also say, let's select 3 cards and then multiply by 3 factorial, and that gives the same result as well. Any of them would work. You can do any of them. Okay. But now it says, how many of these arrangements contain the pink card? What about this now? Now we've got a problem. Because now we've got a condition. If we have a condition, and the condition is that there should be a pink card there. So that means you have to split it into 2 parts. You cannot do arrangement directly. This would not work anymore because there's a condition on selection. And this condition is that there has to be a pink card there. Okay. Now, if there has to be a pink card, in how many ways is that possible? You say there are 3 cards that you need. One of them has to be a P. So the selection is only supposed to be done for the remaining 2 objects, remaining 2 places. There are 8 remaining cards. Out of those 8 remaining cards, we have to select 2. So that's 8C2. And once you've selected those 2 cards, then you have to arrange all of these 3 cards together. That's 3 factorial. You multiply them, you get 168 from this. You cannot do it directly. In this case, they're talking about arrangements. However, since there's a condition that you want a pink card, you cannot do arrangement directly unless you first satisfy or fulfill that condition that is there on selection. So you have to do it separately, do selection separately, and then do arrangement of that. Then it says how many different arrangements of the 3 cards in part 3 do not have the pink card next to the green card. How many arrangements of these cards do not have the pink card next to the green card? How do you think about this? Pink card should not be next to the green card. How do you think about it? Now, there could be multiple cases. If pink and green card are not next to each other, if they're not next to each other, what does that mean? One possibility could be that the 3 cards that are selected, they do not even have both the cards. So one possibility is that the pink card is not selected and the green card is selected, then they would not be together. Another possible case would be that the pink card is selected and the green card is not selected. In that case as well, they will not be together. Another possible case would be that both of them are not selected. In that case as well, they will not be together. And the fourth case would be that both of them are selected, but still they're not together. They are separated. That's too many cases. It's only 2 marks. Can we make it more efficient? We could say we have found the total number of possible arrangements already. The total number of possible arrangements of the 3 cards, what was that? That was 504. That was the total number of possible arrangements, 504. Out of them, how many have the pink card next to green card? Can we find that case? We can find the difference and that will give us the result. Okay, find the arrangements in which the pink and green cards are next to each other. How can we do that? We could say, first of all, both the pink and green cards have to be selected. Okay, so from amongst the 3 cards that we've got, three cards that we've got, one has to be a P, the other has to be a G. We only have one choice left. So from the remaining 7 cards, we have to select one. So that's 7C1. Once we have selected that one card, now after that selection, we've got 3 cards like this in which we want these 2 together. So we put them in a single box. In how many ways can we arrange these 2 boxes? 2 factorial. We multiply by 2 factorial because of that. But then P and G could switch places with each other as well. That's 2 factorial. And that gives us 28. That's the number of arrangements where P and G are together. We want that they are not together. If they are not together, we subtract this number from the total that we found in part 3, 504 minus 28, and that's 476, and that's the final result that we get from this. Make sense? So you have to break it down sometimes in combinations and arrangements separately. Whenever there's a condition in combination, you do that first, and then you do arrangement afterwards. Then there's this other question, this will take a lot of time to explain now. You can have a look at one of those difficult permutations, combination questions videos on my channel. You'll find that question solved there. But I'll just show you the solution quickly. You can have a look at this in your own time. These notes are available with you as well. And you can watch the recording slowly as well to go through this if you want, and just scroll down. It's a good one as well. Okay, so that's it in permutations and combinations. Let's start with this representation of data. So in representation of data, first of all, you need to be able to find different measures of central tendency and measures of dispersion. Central tendency are three types of measures: mean, median, and mode. They give you one value that is supposed to give you the average of the whole data. It should represent the whole data. Okay, these are called measures of central tendency: mean, median, and mode. First of all, how do you calculate them from ungrouped data? Mean is straightforward. For mean, you just add up all the values, sigma x divided by the number of values, and you get the result. That's really straightforward. Median, you just sort the data, and the middle value in that sorted data, that's going to be the median. If it's an odd number of values, then it's going to be one value from the data itself. If it's an even number of values, then you would get two values in the middle, and you take their average, and that gives you the result. Now, for ungrouped data, we can use this formula n plus 1 over 2, n plus 1 over 2 to find the position of the median, n plus 1 over 2. For example, if the number of values is 7, you say 7 plus 1 divided by 2, that gives you 4. So the fourth value is going to be the median. In the data, the fourth value is 5, that's the median. Okay. If the number of values is even, for example, if you've got this set of values, n is equal to 10 in this case, 10 plus 1 over 2, you get 5.5 from that. Now, there's not any 5.5th value, right? It's the position has to be an integer. So what we do is, this is 5.5. We say the median is going to be the average of the fifth value and the sixth value, right? And they are 34 and 36. So I find the average, and that turns out to be 35. That's how you find median in this data. Mode is just the most repeated value. So in this case, for instance, you have 5 coming twice, so that's your mode. That's 5 basically in this data. Sometimes you can have multiple modes as well. If you've got multiple values that are coming coming the same number of times, and that's the highest number of times, you can have multiple modes sometimes as well. But central tendency measures are not the only measures that are used to describe a data. For example, in this case, you have two sets of data. Both of them have the same mean, the same median. However, they're actually different from each other because the variation in the data is very different, right? These points are very different as compared to these values. These are not that different. If you just remove that from here, these values are very different from each other. These are all very close to each other, right? So even though the mean and the median for these turn out to be the same, the variation is not the same. So we need another type of measure to be able to describe variation in the data as well. So we have some measures that we call measures of dispersion. The other names for these are measures of variation, measures of spread. There are 4 of them that we need to know about: range, interquartile range, standard deviation, and variance. Range is just maximum value minus the minimum value. But it's not a very good measure in practice because it's affected by extreme values. So if you had, for example, another data point here that was 150, then the range of the upper data, that is going to be 35. Range of the lower data, that's going to become 150 minus 18, and that's 132. And that's affected by this extreme value, even though most of the values are very close to each other. But that one extreme value affects the range. So range is affected by extreme values, but that's one measure that you can sometimes use. But a better measure than range is interquartile range. Now, what are these measures supposed to do? They basically give you how much variation is there in the data, right? So looking at these values, you could say that, okay, data for A is much more varied as compared to data for B. But how do you quantify that? These measures are used to quantify that variation. One is range, another is interquartile range. How is interquartile range found? It's the upper quartile minus the lower quartile. Now, in ungrouped data, there's a specific method that we use to find interquartile range. You need to make sure that you use these formulas. Do not use formulas here. In interquartile range, do not use any direct formulas for finding lower quartile and upper quartile. They will not always work. Sometimes they will work, sometimes they won't. You would not know in the exam if you're getting the correct answer or not. Those formulas, 3n over 4, n over 4, they do not work. How exactly do you find this interquartile range? Let's say you've got this ungrouped data like this. These are 11 values in total. First of all, for finding interquartile range, you find the position of the median first of all. Where is the median going to be in this? 11 plus 1 over 2, that's the sixth value, that's 20. 20 is the median, so this value is the median in the middle. Now, median divides your data into two parts, one on the left side, one on the right side. On the left side, the median of this part, that is going to give you the lower quartile, and the median of the right side in ascending data, and data that's sorted in ascending order, the right side, the median of that part is going to give you the upper quartile. Okay. And that's how you find interquartile range. Then interquartile range is upper quartile minus the lower quartile. So for ungrouped data, do not use formulas. They do not always work. Okay. Now, in this case, the number of values was odd. What if it was an even number? What happens in that case? For example, you could have a data set like this, n is equal to 12 in this case. You've got 12 values. In this case, if you find the median position is going to be 6.5. That means the average of sixth and seventh value. Now, this is the sixth value, this is the seventh value. Median is going to be between them. Median is going to be in the middle of them. Now, on the left side of the median, you have these six values. On the right side, you have these six values. You have to consider 20 and 25 on these sides as well. Now, the median of the left side, what's that? That's the average of 5 and 11. That's 8. That's the lower quartile. Median of the right side, that is average of 31 and 40. So the upper quartile is 35.5. Find the difference and you find the interquartile range from that. That's the process. That's the method that we use to find interquartile range for ungrouped data. Do not use formulas here. Then we got standard deviation. Standard deviation is another measure that's the most widely used measure in practice. We use this to find variation in the data as well. The idea in this case is it gives us the average distance of the values from the mean. That's a rough interpretation of this. That's not the exact interpretation. It's the rough interpretation. It's the average distance of the values from the mean value. Now, how is it calculated? Let's say you've got a set of values of x, 13, 5, 21, and so on. You find the mean first of all. Mean is 15. Now, one way to calculate standard deviation is this, that from each x value, you subtract the mean. Each value, you subtract the mean. So you find x minus x bar, and then you square those values. You square all of those values, add them up together, sum of all of these values. We say that's sigma x minus x bar whole squared. That's going to be your numerator. And in the denominator, you have n, which is 6 values in this case. Take square root of that, and that gives a standard deviation. That's one formula that we got for standard deviation. Sigma x minus x bar whole squared divided by n. Okay, so you subtract from each value the mean. You add up all of those values. That becomes the numerator. And then after squaring, you add them. And then you divide by n, take square root, that's the standard deviation. This is one way to calculate standard deviation. Another way is this. Both of these formulas are given in the formula sheet. This is sigma x squared over n minus x bar whole squared. We will mostly be using the second formula for standard deviation because that's simpler, that's more efficient. This is the one that we will be using. These are equivalent to each other, but mostly the second formula is going to be simpler. So we'll be using that. So the same data, if you wanted to use the second formula, how would you do that? You have sigma x squared here. You evaluate x square values for each of them, add them add them up together, that gives you sigma x squared. That's going to be your numerator. Divide by the number of values, which is 6 in this case, minus the mean squared, mean is 15, and that gives you the standard deviation, that's 6.66 as well. Both of these formulas work every time. When you have data given in this form, you should use the second formula. That's much more efficient. The first formula is normally only going to be used for ungrouped data when the question gives you this information. Instead of giving you values, instead of giving you individual values, if they give you this information in the question themselves, then in that case, you would use this first formula. But if you've got raw values like this, then using the second formula is more efficient. Okay, all right, let's move on. So that's standard deviation. The number that you have inside the square root, in this case, 44.333, that's called variance. That's another measure that we've got for variation or spread or dispersion. Variance is just the square of the standard deviation. So if standard deviation formulas are these, then if you just remove square root from these formulas, you get variance from that. Variance is given by these two formulas. Variance is square of standard deviation. These are 4 measures of dispersion that we've got: range, interquartile range, standard deviation, and variance. Now that's for ungrouped data. What about group data? Group data is when you have values in the form of a frequency table, right? Frequency table, that's called group data. Let's say we've got some data like this. We've got information about the number of pets owned by some families, and we've got, so we collect some data like this. We've got some families for which we have this information, the number of pets they own. So there are 6 families in the data that own 0 pets, 20 families that own 1 pet, 7 families that own 2 pets. And we want to find, let's say, the mean of this data. How do you do that? We've got this information inside the table. The formula for mean that we have is sigma xf divided by sigma f. There's a logic behind it where this comes from, but we'll not go into that. It's given in the formula sheet. Sigma xf divided by sigma f. All you have to do is, in the table, add another row to the data, x times f. So you just multiply these two numbers, x and the frequency, add them up all together. That gives you sigma xf. Sigma f is the sum of all frequencies. Divide them and you get the mean from that. Okay, sigma xf divided by sigma f. For ungrouped data, the formula was sigma x over n. For group data, in place of sigma x, we've got sigma xf. In place of n, we've got sigma f. The total number of values is now given as sigma f, the sum of all frequencies, right? Similarly, for standard deviation as well, the formulas that we had in ungrouped data, they were these, right? In group data, they convert to this. Again, these formulas are given in the formula sheet as well. So what happens is you have frequency here in the numerator multiplied by this, and in the denominator, n is replaced by sigma f. And in the second case as well, x squared is multiplied by frequency, and in place of n, we've got sigma f. These are the grouped tables formulas for standard deviation. Frequency tables formulas, both of these are given in the formula sheet. In this case as well, it's often more efficient to use the second formula rather than the first one. Okay, so how would you use that? In an example, let's say you've got that same data set as before. The formula that we will be using for standard deviation is this: sigma x squared f divided by sigma f minus x bar whole squared. You add another row to the data. You already need the mean of the data for this, right? So you have to find the mean. For mean, you need x times f. You have that row in the data already. That gives you sigma xf. Add another row to the data that represents x squared times f. That's another row. Once you have these values, sigma xf, sigma x squared f, all you have to do is input them in the formula. Find the mean first of all. The mean turns out to be 1.633. Put that mean here along with sigma x squared f and sigma f, and that gives you the value for standard deviation. That's how you calculate standard deviation for group data. Mode is just the value that has the highest frequency. So if you've got that data, what's the mode value? 10 is the highest frequency, so mode is 1. Okay, mode is not 10. Mode is the value of the variable corresponding to that highest frequency. That's going to be 1 in this case. What about the median? For median, and interquartile range, etc. In this case, you can use formulas. In this case, n over 2 works as well for median, n plus 1 over 2 works as well. Both of them will give you the same results. In this case, they will give you tables in a format in which n over 2 and n plus 1 over 2, both of them will give you the same results. So in this case, if you have to find median, how do you do that? You've got sigma f equals to 30. So in place of n, you've got 30 here. The number of values is 30. Divide that by 2, that gives you 15. 15th value is going to be the median. And now we count from the beginning. We've got 6 values until this point, right? So from 1 to 6, we've got these. Then from 7 to 16, the next 10 values up to 16, they are ones. So where does the 15th value lie? 15th value lies in this interval. So the median in this case is also supposed to be 1 for that reason. Okay, what about interquartile range or range? Range is just the maximum value minus the minimum value. Maximum value in this case is 5, minimum value is 0. 5 minus 0, that turns out to be 5. What about interquartile range in this? Let's think about that. In this case, for group data, we can use formulas. They work n over 4 and 3n over 4, right? The formulas work in this case. Or you could also use n plus 1 over 4 and 3n plus 1 over 4. Those formulas are going to work for group data. Okay, there's Azan going on here. We'll have a 1-minute break and then we'll see. Okay, so how do you find interquartile range in this case? In this case, you are allowed to use formulas n over 4, 3n over 4. In ungrouped data, you could not use formulas. Now, n is 30 in this case, so you can say 30 over 4, that's 7.5. That means the average of 7th and 8th values. Now, in this case, what would happen would be both of these values are going to be in the same interval. They will give you tables in that format. Upper quartile, that's 22.5th value. That's the average of 22nd and 23rd value. Now, let's think about this. Let's think about the table. The first 0 has a frequency of 6. So from 1 to 6, we've got these values. The next 10 values up to 16 are ones. So 7 to 16, we've got these values. And then plus 7, 16 plus 7, that's 23. 17th value to the 23rd value, we've got this interval and so on, right? Now, the lower quartile is going to be the average of 7th and 8th value. Both of them are in this interval. So that's 1. Average of 22nd and 23rd, both of them are in this interval. And this, both of them are here. So the upper quartile, therefore, is 2. Find their difference, and that will give you the interquartile range. Yes, in this case, n plus 1 over 4, n over 4, they will both give you the same result. They will give you the tables in that format in which both of them are going to give you the same results. Okay. So in group data, you can use these formulas: n over 4 for lower quartile, n over 2 for median, 3n over 4 for the upper quartile. N here is the same thing as the sum of all frequencies, sigma f. Now, then you can have data in the form of intervals as well. The only thing that's different here is when you're calculating the mean and standard deviation, you use the midpoints for these calculations. You use midpoints for calculations of mean and standard deviation. So you would say, if this is the interval 2 to 3.5, the x value in the formula is going to be the midpoint of that interval. What's the midpoint of 2 and 3.5? 2.75. For this interval, we've got 4 and so on. How do you find midpoints? Find the average of these numbers. 2 plus 3.5 divided by 2, that's 2.75. Similarly for the rest of the numbers. The rest of the intervals, you have the midpoint. So now you have these x values. And you have these frequencies. This is what you will be using for your calculations: x values and frequencies. Evaluate x times f, evaluate x squared times f, and input values in the formulas, and you get the result. Now, this is very important. Sometimes they will ask you in the questions, why are these values of mean and standard deviation? They are estimates. Why are these estimates? These are not exact values. These are estimates because we are using midpoints for our calculations. We're using midpoints for our calculations. Now, the actual values in the data could be anything. For example, if there are 8 values between 2 and 3.5, it is possible that all of them were maybe 2.05, 2.1. All of them were small numbers. It's possible that all of them were large numbers. We are just using 2.75, which is the average of this interval. It's not necessary that the actual average of the values that you have is 2.75. Since we don't have any other information, any more information, the best we can do is we can just use the midpoint. So we would say these values are estimates because we do not know the actual values. We do not know the actual values. We're just using midpoints in our formulas. So the values of mean and standard deviation. So the values of mean and standard deviation that we would get from this calculation, they're going to be estimates. Okay, so we'll say that we do not know the actual values, we're just using midpoints. So that's why these are estimates. Now, in case of intervals as well, they can ask you to find the modal class. How do you do that? Just the class or interval that has the highest frequency. In this case, that's 5.5 to 7. That's your mode. Interval in which the median lies, exactly the same process, n over 2. That gives you 52nd value, and then figure out where the second value lies. 34th to 61st values, they are in this interval. So this is the interval in which you've got the median, 4.5 to 5.5. Okay, that's pretty basic stuff. Then in case of range and interquartile range, when you have intervals given, they often ask you for the greatest possible value of range and the least possible value of range. So they will not ask you to find range directly in a question that involves intervals like this. They will ask you to find the maximum possible range or the minimum possible range. Now, how is range defined? Range is defined as the maximum value minus the minimum value. If you want to maximize this, remember the concept of upper bound, lower bound in O levels as well. If you want to maximize this, you would want the positive value to be as big as possible, minimum value to be as small as possible, so that the difference becomes maximum. So greatest possible range, that's the maximum value minus the minimum value. Now, maximum value is going to be in this interval, minimum value is going to be in this interval. If we want the greatest possible value of the range, what we would do would be, we would use 9 from here and 2 from here, right? The extreme values on both sides, and that's 9 and 2. That's going to give you 7, okay? Now, similarly, for the least possible range, the maximum value should be as small as possible. The minimum value should be as large as possible. Now, we know there are some values in this last interval. There have to be some values here. There are 12 values there. And there are some values in the smallest interval. The least possible range would be if all the values in the first interval, they were 3.5. And all the values in the last interval, they were 7. So we would want the maximum value to be as small as possible, minimum value to be as big as possible. So what are those values going to be in this case? We say they are 7 from here and 3.5 from here. These are the values that are going to give us the least possible value of the range. That's 7 minus 3.5, and that gives you the result. That's 3.5. Okay, so that's how you find the maximum possible range and the minimum possible range. Class width, there's no point of finding class width here. Class width is only needed for histograms. We'll see that later. In this case, there's no logic of using class widths. Okay, let's move on. Interquartile range as well. For interquartile range as well, they will ask you to find the maximum possible value of interquartile range and the minimum possible value of interquartile range. Okay, how do you do that? You first of all find in which interval the lower quartile is and in which interval the upper quartile is. You can use n over 4 and 3n over 4. n over 4 is 26. 3n over 4 is 78. 26th value lies in this interval. 78th value lies in this interval. Okay, so these are the two intervals that we've got. These are the intervals in which you've got these values. Now, This is one interval, this is the other interval. Upper quartile is going to be in this interval, lower quartile in this interval. What's the maximum possible interquartile range? Interquartile range is defined as upper quartile minus the lower quartile. For greatest possible interquartile range, we would want the upper quartile to be as big as possible, so that's 7. Lower quartile to be as small as possible, that's 3.5, and that will give us 3.5. For least possible interquartile range, we would want the upper quartile to be as small as possible and the lower quartile to be as big as possible. Then the difference will become minimized. So that's 5.5 minus 4.5, and that gives you the result that is 1, and that's the least possible value of the interquartile range. Okay, so in case of intervals, they can ask you for greatest and least possible values of range and interquartile range like this. Now, the interval data could be in other forms as well. In this case, we had dashes between them, and there were no gaps between the intervals. They can give you intervals in this form as well when you have inequalities. So from 0 to 5, 5 to 10, and so on. Again, the idea remains the same in this case as well. Since there are no gaps between values, we would just find the midpoints, and these are the frequencies. Add another row to the data, xf and x square f, and use them to find the mean and standard deviation. So that remains the same. However, if you get some data that looks like this now, in which there are gaps between intervals, So from 1 to 25, 26 to 35, 36 to 45, now there are gaps between intervals. These are gaps, right? So in this case, you should first ideally adjust the intervals. Now, in this case, it would not make a difference, and because the midpoints, if you were to find them directly from this or from true class boundaries, they will turn out to be the same. But I'll show you another example in which it does make a difference. So what you generally do is find the true class boundaries, like you do for histograms. You want to eliminate the gap between values. How would you do that? You can say 25 is where the first interval is ending, 26 is where the next interval is starting. The actual boundary is going to be at the midpoint of these two values, and that's 25.5. Okay. Similarly, here it's 35.5, 45.5, 55.5, and using the same pattern, you can adjust on the sides as well. This is 90.5, this is 0.5. These are the actual class boundaries. We call these true boundaries of this variable, because it's time. Time can be in decimals as well, right? So what if it was 25.3? How do you know which interval to put that in? It rounds off to 25. It's less than 25.5, right? So we put that in the first interval. So that's why we need these true class boundaries. They're going to look like this. And then using these boundaries, what you can do is you can find the midpoints, find the values of x like this. You have frequencies, find xf, find x square f, and then do these calculations like you would normally do. Now, in this case, as I said, finding midpoints from the actual data or from this data, that's not going to make any difference in this particular example. But what if you had something like this? It's slightly different from that, in that I've changed the first value here such that it becomes 0 to 25. So the first interval starts from 0 to 20. It goes from 0 to 25. Now, when you adjust the intervals for this, what happens is, this is 25.5, 35.5, 45.5, 55.5. You adjust the sides on the same pattern as well. So you adjust the right-hand side. On the right side, you have 90.5 here. But on the left side, you had 0 here already. You had 0 here in the original data. Now the variable is time. Time cannot be negative. So we cannot say that the first interval starts from minus 0.5. That would not make sense because time cannot be negative. So the first interval in this case will have to start from 0. Now, that means the midpoint of these two values is going to be 12.75. If you were to find that midpoint from the original value, 0 and 25, that will turn out to be 12.5, and that would be wrong. So in this case, if you had to find the mean and standard deviation, their values will turn out to be wrong if you find the midpoints from this, because the midpoint of the first interval is going to be 12.75 from the true class boundary. So you should first adjust this and then do this. Normally, this problem is only going to be when you have this extreme value on the other side, that is 0. Otherwise, you can do it directly as well. But when you have an interval that starts from 0 and you cannot adjust on that side, but on the other side you are adjusting, that means there's going to be a problem and you have to use true class boundaries. In that case, adjust these intervals first of all, and then find the midpoints after that. Okay. Now, sometimes what happens is they give you cumulative frequency table. And the questions, rather than giving you a normal table, they give you cumulative frequency table. So they give you this table. Okay. And using that, you have to find the mean of the distribution, the standard deviation of the distribution. How would you do that? You would convert it to a normal table, first of all. Normal table that has two-sided intervals. How do you do that? Less than 40, you can say, let's make intervals like this, 0 to 40. And then the next one is going to be from 40 to 50, 50 to 60, and so on, using these values as the upper boundaries, upper limit for each interval. These are the intervals that you end up getting from this, right? 0 to 90 like this. Now, find the corresponding frequencies. 0 to 40, you've got 0. Less than 50, you had 12 values in total. There was 0 value less than 40, so that means all of these values are going to be between 40 and 50. So this frequency is 12. And then similarly for the next values, if less than 60, you've got 34 values in total. Less than 50 were 12 values. How many do you have from 50 to 60? That's only 22. You basically find the difference 34 minus 12. So it's the opposite of cumulative frequency curve. We are doing the opposite. So we'll subtract these values like this. 34 minus 12, that gives us 22. 64 minus 34, that gives us 30. 92 minus 64, that's 28. 144 minus 92, that gives you 52. And this way you find your standard table. And now you've got these intervals, you find the midpoints. The midpoints turn out to be 20, 45, 55, and so on respectively. So now you've got these X values, you've got these frequency values. These are the ones that you will now be using to find the mean and standard deviation. The rest of the process remains the same. You find XF, you find X square F, input them in the formulas, and you get the result from that. Okay, so this is possible as well, that they give you a cumulative frequency table, and you have to find the normal table from that, and then do those calculations. Another concept that you have here is linear transformation. It's also called coded data sometimes, or linear transformation. Now, what's this? This is the next concept that we have now. Let's consider two variables. Let's say there's one variable that is X, and there's another variable that is Y. And they are related like this, that Y is equal to X plus 7. Y is equal to X plus 7, right? For every value of X, if you add 7 to that, you get the corresponding value for Y from that. Now, when you have two variables that are related like this, linearly, if you were to find the mean for one, mean for the other, you would notice that the relation between their means is also going to be the same. So if Y is equal to X plus 7, then Y bar is going to be equal to X bar plus 7. Okay. And what about standard deviations? Both of them have the same spread, because all we're doing is we're just shifting the data by 7 units to one side. When we do that, the variation is not affected, right? The distances from the mean, they remain the same as before. So standard deviation for both Y and X, that is going to be the same. This is the general result that we get from this. If you have any two variables, Y and X, and they're related linearly like this, that Y is equal to X plus some constant or minus some constant, then the mean is also going to have that same relation. And the standard deviations for them, they're going to be equal to each other. Okay. Now, how is that used? Let's look at this example. You are given sigma t minus 35, that equals minus 15, and you're given sigma t minus 35 whole squared equals 82.23. Whenever you have expressions like this, sigma, and then inside brackets, you have some variable plus something or minus something, that's a linear transformation. What you would do in such problems would be, they're asking you, for example, in this case, to find the mean and the standard deviation of the times. Times are represented by t. So we want to find the mean of t and the standard deviation of t. The information that we're given is not for t, that's for t minus 35. What we do is we use a substitution in this case. We say, whatever is inside the brackets, just replace that with another letter. Substitute that with another letter. So this would become y equal to t minus 35, y equals t minus 35. And then you do your calculations in terms of y. So let y equals t minus 35. If y is equal to t minus 35, we know from that concept that we did that the means are going to have the same relation as well, and the standard deviations are also going to have the same relation. And the standard deviations are going to be equal, and the means are going to have that relation. And now what you do is you are given information in terms of y. You're given that sigma y is minus 15, sigma y squared is 82.23. You find the mean of y, that turns out to be this. You find the standard deviation of y, that turns out to be this. And now you know the relation between their means. Using that, you can find the value for t bar. And the standard deviations are equal. So standard deviation of y, if that's this, standard deviation of t is also going to be the same. Okay, so that's how we can use this. Let's look at another example of this. We have speeds given. They are represented by x kilometers per hour. They're represented by x for 70 cars, and we're given that sigma x minus 60, that is equal to 245. Sigma x minus 60, that is 245. We want to find the mean speed of the 70 cars. That means we're looking for x bar, right? Speed is x. We want to find the mean of x. How do you do that? Whatever is inside brackets, you replace that with another letter. So you can say it becomes y equals x minus 60. If that's the case, we know the relationship between their means is going to be this, and the standard deviations are going to be equal to each other. And now we do our calculations in terms of y. So we can say sigma y is 245. That's what we're given. Find the mean of y. That is 3.5. And now we know that y bar is equal to x bar minus 60. From that, you can find the value of x bar as well. Okay. Now they're saying his friend Sachin used values of x minus 50 to calculate the mean. Find sigma x minus 50. Again, you can replace this with another letter. I've used p here for that. We need to find sigma p, right? So that's another substitution that we can use now. P is equal to x minus 50. Now, if p is equal to x minus 50, what that means is the relationship between their means are also going to be the same. So what we can do is, we know the value for x bar already from the first part. We can find p bar from that. P bar turns out to be 13.5. If p bar is this, use the formula for mean here. Sigma p over n, that should equal 13.5. And we find sigma p from that. That's what we were looking for. Sigma p was x minus 50. So sigma x minus 50 is 945, right? So using a substitution, it becomes fairly straightforward. Standard deviation of the speed is 10.6 kilometers per hour. Calculate sigma x minus 50 whole squared. Now, how do you think about this? Again, you can use a substitution. You can say p is equal to x minus 50. You have to find sigma p squared from this. Now, standard deviations are going to be equal, right? When you have linear transformations, standard deviations of all of these variables are going to be equal to each other. We are given that this is 10.6. So what we can do is we can say standard deviation of p, that is equal to sigma p squared divided by n minus p bar whole squared. Right? Just input values in this. If the standard deviation of the speeds is 10.6, standard deviation of p is also going to be the same. That's going to be the same. That does not change in linear transformation. So that means the standard deviation of x, that's the same thing as the standard deviation of p. Use the formula, you'll find the value of sigma p squared, and that's the result that you were looking for. Okay, so you can use substitution like this to do these linear transformation problems. Now, sometimes they ask you whether in a particular situation, mean is a good measure or median is a good measure. How do you figure that out? Generally, for most of the data sets, mean is the most appropriate measure because it uses all data points. It uses every single value in its calculation. However, there is one case in which mean is not going to be appropriate, and that is when you have extreme values in the data, when you have outliers in the data, in these cases, mean is not an appropriate measure. So for example, if you have a data like this, if you have two data sets like this, or is it the same data? Yeah, it's the same data. You've got a data set like this. It has an outlier. That's 450. Mean from this turns out to be 77.6. Median of this data, when you sort it, after sorting, the median turns out to be 16. Now, which is a better representation of the data? 16, because most of the data points are close to 16. Mean 77.6, that does not really represent this data in any way. Why is that not very helpful in this case? Because of this outlier. Because of this outlier, the mean is going to be inflated and it's not going to be reliable. So when they when a data set has outlier, remember, mean is not going to be an appropriate measure. Okay, mean would not be appropriate when there's an outlier in the data. In that case, you would use median. Now, mean and median, they're both used for discrete data as well as continuous data. Mode is only used for discrete data. It's not used for continuous data, right? So if you can have any decimal value in the data, in that case, mode is not going to be an appropriate measure. It's only used for discrete data. Now, in mode, you'll sometimes get problems in which you have very small data sets. For example, just have these 8, 9 values like this, and you would be asked to find out whether the mode is not a very good measure in that case. Generally, mode is not a good measure when the data is very small, because a lot of times what happens is, by coincidence, one value might be repeated. For example, in this case, 2 is coming twice and the mode is turning out to be 2. Now, 2 is not really a good representation of this data, because 2 is actually the lowest value in the data. So that's not an average of the data in any way. It's coming twice in this data because it's small data, 5, 7, 8, 9 values. If something comes twice, that becomes the mode. It can be because of some coincidence as well. That's, some values repeated. It might not have any practical significance as such. So for small data sets, mode is not going to be very reliable, because in some cases, it can turn out to be the lowest value, the highest value that will not represent the average of the data. If you have a large data, for example, you've data about shoe sizes, and then you've got like 5,000 shoes. And in that large data, there's some value that's coming a lot of times. For example, 1,500 is the highest frequency in this data for size 9. That has some significance, because that's telling you that the size 9 is the most common size that is sold in a particular store, or maybe it's the most frequent stocked size that they have. So that has some significance, because it's repeating 1,500 times. It's very unlikely that it's just by coincidence that some value is repeated so many times. But in small data sets, if something is repeated just twice, it can just happen by accident, by coincidence as well. So in this case, we say mode is not a good measure when the data is small, because it could be the smallest value or the largest value in the data sometimes as well. Okay. All right. Then you've got some diagrams. There are 4 diagrams that you have in your syllabus: stem and leaf, box and whisker, histogram, and cumulative frequency curve. Now, what about stem and leaf? First of all, you've got this data. Let's say you want to draw a stem and leaf diagram. Stem and leaf diagram looks like this. You've got 2 columns. One column represents the stem, the other represents the leaf. Now, how do you represent it? It's going to be sorted like this. You'll have numbers written in sorted order in stem like this, in ascending order like this, in stem. And in the leaf, you'll have the remaining digits. Now, how would that work for this data? These are the data points that you've got. You would first look for the smallest value in the data. That's 34 in this case. Largest value in the data, that's 91 in this case. So 34 to 91. These are the values that you have to represent on this diagram. In the leaf, you can only have a single digit. You can't have multiple digits in a leaf. So you know that this is the only thing that you would have in the leaf then. Okay, 4 and 1. So what about stem then? The 10th digit, they will go in the stem, 3 to 9. You would write down these values from starting from 3, ending at 9, with no value being skipped. Even if, for example, you had no data in 60s, for instance, if this value did not exist, we would still write 6 here. We would not skip that. Okay, we have to write all values from 3 to 9 here, and then their corresponding leaves based on the data. This is 34, this is 35. You write 4 here, you write 5 here, and so on. Okay, for the rest of the data. You will do it like this. You'll start from the smallest values, mark the values in 30s, and then you sort them. That, okay, 34 should come first, and then 35, and then you cancel them out, so that you know that you've used them. That will make things quicker. Then look for 40 values in 40s. There are 45, 44, and 41. And then you sort them first, write 1 first, and then 4, and then 5, and that's this part done, and then move on like that. Always do it with a pencil. Do not use a pen for this, because a lot of times what happens is when you're writing these things down, you realize later that you've ended up missing a value. Then crossing out in a diagram is not a good idea. Never do it with a pen. Always draw this with a pencil. It's a diagram. Okay, so do it with a pencil so that in case you need to erase something, you can do that. Now, there's some properties of the stem and leaf diagram that are important. You always have to write down a key for the stem and leaf diagram so that you can understand how to read this diagram. So in this case, if you write something like this, 5, 2, you can say this represents 52 in this case. Okay, this represents 52. If there's any unit that's appropriate here, you should also use that. You should also write that in the key here. In this case, there's no unit. It's just the number of tickets. So there's no unit, but you would write a key like this. So this represents 52, stem here and leaf here, and that's the key. Now, there's some properties that are very important for a stem and leaf diagram. The rows should be sorted. The rows should be sorted. Okay, everything should be sorted. In every row, the data points should be sorted. You have to represent the key. The vertical line between stem and leaf, that's very important. You always need to have that. Leaf can only have one digit. You can never have multiple digits in the leaf column. Okay, for one value, you would only have one digit for each value in the leaf column. In stem, you can have multiple digits. In leaf, you cannot. There should be equal spacing between the numbers that you've got. Now, this is extremely important because it's a diagram. You don't just write down numbers as it is. Its representation is important. The values should have equal distances between them, right? These gaps between the values, they should be standardized, okay? And they should be standardized in a way that all of these first values, they're vertically aligned. These are vertically aligned. These are vertically aligned. This is important. If you don't do this, you lose marks because of that. And there should be no commas or dashes that you use in the stem and leaf diagram. No commas, no dashes, no decimals. You don't have any of that in a stem and leaf diagram. You only have numbers with gaps between them. Okay, you only have numbers with gaps between them. Now, this is ungrouped data. Even in the form of a stem and leaf diagram, this is ungrouped data. So if they want you to find the median of the data, for instance, you use the method that you use for ungrouped data. What's that? N plus 1 over 2, right? For interquartile range as well, you'll use that method in which you find the median. Median divides your data into two parts, one part on the left side here and one part on the other side here of the median. Find their medians, they will be lower quartile and upper quartile, right? So you have to use the ungrouped data methods on this for finding median and interquartile range. Now, let's look at some examples of this. If you had data like this, 345, 366, 342, and so on. Now, the leaf can only have one digit, right? So how do you figure this out? How do you figure out what to put in stem? Look at the smallest value in the data, that's 342. Largest value in the data, 363. So you have to draw this diagram for values between 342 and 363. How do you do that? In the leaf, you can only have the last digit. That means the first two digits, they will come in the stem. So 34, 35, 36, this is what you have in stem here. And then you can write down the corresponding leaves. And then you write down the key for that as well, that this represents 358, for instance. Okay, that's what the stem and leaf diagram would look like in that case. If you have decimals like this, for instance. What about this? Again, figure out the smallest value in the data, the largest value in the data. Decimals cannot be shown on the diagram. It's starting from 2.3, ending at 5.8. The leaf can only have one digit. So the rest is going to go to stem. So you write 2, 3, 4, 5 here. Do not skip any value. Even though we don't have any value that's 4 point something, we still have to write 4 in stem. And then you have 2.3, 2.7, 2.8, and so on. In the key now, you would represent how to read this. So 3.5, for instance, that means 3.5. Decimal will not be represented in the diagram. It will come in the key. Okay. Now, you can have back-to-back stem and leaf diagrams sometimes as well. You have two sets of data in which one set of data is represented on the left side, the other on the right side. That's also possible. The data on both sides has to be sorted. So on the right side, it's sorted this way. Values close to the stem they are smaller, and values away from the stem, they are bigger. On this side, the data is sorted in this direction, right? So it's ascending from right to left in the other case, on the left side. Sometimes you will have numbers written on the sides like this in brackets. In the questions that they would give you, they would represent the number of values in each row. So the first row has 2 values, the second has 4 values, and so on. And that's helpful generally when you're finding the median and interquartile range. Generally, we don't have to count them ourselves. We can just look at the number of values written on the sides. So that's what that would represent. Now, what about the key for this? It's going to be a single key. Don't write 2 separate keys for this. It's a single stem and leaf diagram. There has to be a single key for this. Stem in the middle, 1 value on the left side, 1 value on the right side. And the 3 numbers that you choose for the key, they should all be different. Otherwise, there will be ambiguity. You can't say something like this, 8, 2, 8. That's not acceptable because 8 is coming twice. There will be ambiguity whether you're talking about this 8 or this 8 when you write it on the side. All of these 3 numbers, they have to be different numbers. Okay. And then you can say this whole thing represents 85 kilograms. Unit is important for P and 83 kilograms for Q. And that's what your key is going to look like. Okay, so that's the stem and leaf diagram. These are the important ones to remember. This is only used for ungrouped data. It's only used for ungrouped data. Some benefits of stem and leaf diagram. Sometimes they ask you for this. They ask you, what are the benefits of stem and leaf diagram? Just a simple question, 1, 2 mark question like this. One benefit is that it shows all data. It shows all the data in the diagram, which other diagrams don't. So in case you wanted to go back to the original data, you can do that. From this, it shows you all the data that is there. Number 2, you can see how the data is distributed. So for example, just by looking at this diagram, if you've drawn this correctly with equal spacing, you can see that most of the data for P, for instance, is concentrated here in 90s. And for Q, most of the data is concentrated here. And then it becomes lower on the sides. And for P as well, it's lower on the other sides. So just by looking at the diagram now, if you just had numbers written, that would not make it clear where the data is concentrated. But in this diagram, you can see clearly that, okay, most of the data for P is in 90s, for Q, it is in 70s. So it tells you the distribution of the data, how the data is distributed. Okay, that's the other benefit of stem and leaf diagram. You need to memorize these. You sometimes just have to write these down as it is. Okay, let's move on. The next diagram is box and whisker plot. In box and whisker plot, you need 5 points. 5 points. And these 5 points are minimum, lower quartile, median, upper quartile, maximum. These are the 5 points that we have to draw for in a box and whisker plot. Okay. Now, this is an example. They've given you some values, lower quartile, upper quartile, minimum, maximum, etc. They gave you interquartile range in this question, and they also give you the upper quartile. First of all, you have to find the lower quartile. You can use this formula to find that. The values are in hours and minutes. So you first convert them to minutes, all of them, and then you just use this formula to find the lower quartile. Then they say, represent this information by using a box and whisker plot. Now, how do you do that? You will get a grid on the paper for this. For S1 is the only paper in which you get these graph grids for cumulative frequency curve, histogram, and box and whisker plot. You'll have the space and given in the question paper. Always use a pencil for this because otherwise, if you do it with a pen and do get something wrong, you won't get an additional paper for this, right? In the additional page at the end as well, you don't have a graph paper. So don't make a mess of it. Do a pencil. You use a pencil for this. Do not use a pen. Okay, so how do you draw a box and whisker plot? Only one axis is important here. Horizontal axis, generally, you can draw, you can mark points on this horizontal axis. Then what you have to do is choose any line here. Choose any particular line here. It doesn't matter because the vertical axis does not represent anything here. So you can choose any line here and mark those points. You've got the minimum point, that's 30. And then the lower quartile, 54, median, 216, upper quartile, 282, and the maximum value. You can mark these points. And now the points on the sides, they will be joined with lines like this. From lower quartile to upper quartile, you would have a rectangle. Now, the width of this rectangle does not represent anything. You just have to make sure whatever is the number of values that number of boxes that you have gone on the upper side, in this case 5 boxes, that should be the same number of boxes that you go on the lower side, 5 boxes. Okay, 5 up, then 5 down. Use the same number of boxes so that the graph remains kind of symmetric from the side, that this line is exactly in the middle of that rectangle. Okay, and then in the middle, and at the median, you draw another vertical line, and that completes your box and whisker plot. On the sides, it's your choice if you want to draw these vertical lines, small vertical lines like this. They're not necessary though. Only these lines are necessary. If you want, you can draw those vertical lines at the sides as well, and that completes your box and whisker plot. Okay. So that's what it looks like. Using this box and whisker plot, you can see again how the data is distributed, how much spread, how much variation is there in the data. If there's any skewness in the data, for example, in this case, median is on one side, the data is skewed. Okay, the data is skewed in this case towards one side. This is how you draw it. Make sure that you label this for all the diagrams that you make. Always make sure that you label them appropriately. On the horizontal axis here, you would say that this is time in minutes. Use the units there as well. Sometimes you have to draw 2 box and whisker plots in the same diagrams. This is the same example that we saw above, in which we had the stem and leaf diagram given. But now, let's say we had to draw a box and whisker plot for this. Now, and firstly, they want us to find the median from this and the quartile weights. That means lower quartile and upper quartile from this. I told you how to do that. Find the median. The median will divide your data into 2 parts. Median is here. That divides your data into 2 parts. This blue part on one side, the green part on the other side. Find the medians of those parts. They will give you the lower quartile and upper quartile, and that will give you the interquartile range. Okay, so you can find that. Now, in the second part, they've given you the lower quartile, the median, and upper quartile for the other country as well. You can find the minimum maximum values from the data. This is the minimum value for P. The maximum value is 105. The minimum is 74. Similarly, you can find that for Q as well. And you would have these values, the 5 values, minimum, lower quartile, median, upper quartile, and maximum for both P and Q. And then you can draw those diagrams like this. Select any line on the vertical axis, at which you would mark the points for P. Select any other line for Q. It doesn't matter. So the gap between them does not matter because the vertical axis does not represent anything. So you just draw those points, mark those points here, and draw a diagram that looks something like this. Make sure when you do this, both the box and whisker plots, the rectangles that you have there, they have the same widths. Do not use different widths, since the vertical axis does not represent anything. You have to make sure that you're consistent. Whatever width you're using for one, it should be the same width that you use for the other. Okay. So if it's 3 boxes up and down for Q, it should be the same for P as well. And that gives you 2 box and whisker plots in the same diagram. And then they will sometimes ask you to make some comments on the weights, comments on the data. Now, when they ask you to make some comments, those comments are generally going to be on central tendency of the data and the dispersion of the data. In this case, this only measure of central tendency that you can find from a box and whisker plot is the median. And for dispersion, you can use either interquartile range or range. Both of them can be found from this. Now they're asking for 2 comments. When they ask for 2 comments, that means one comment has to be on central tendency, the other has to be on dispersion. On central tendency, we can say, look at the median. On average, we will say something like this. We have to contextualize our comment with the information that's given here. It's data about weights of 17-year-old males in 2 countries, right? So we have to refer to that on average, these are the averages. 17-year-old males in country P, they have more weights as compared to those in country Q, right? That's the kind of comment that you can make on central tendency. On average, weights of 17-year-old males in country P are higher as compared to those in country Q. What about dispersion? If you look at interquartile range, that's not very different. So there isn't really much that you can say from the interquartile range. That's your first preference. But if you can't differentiate based on interquartile range, the other possibility is range. You can clearly see the range of Q is much bigger as compared to P. So how would you write that? You would not just say that the range is bigger. That's not what you say. You would say the variation in the data, right? Range represents variation in the data. You would say the variation of weights for people in country Q is more as compared to the variation in weights for people in country P. Something like this, the variation in weights in country Q is more as compared to the weights in country P. Okay, so that's two comments that you can make on this. So for median, we say on average, we say something like this. We don't write median values. We have to, write this in words like this. And for variation, we say the variation in weights. We don't just say standard deviation is this, range is this. We have to use statements like this, general statements like this. Okay, then you've got histogram. This is something that you've done in O-levels before as well. How to draw histogram? Whatever data that you're given, first of all, you have to make sure that you eliminate the gaps between them. So in this case, we've got gaps 20 and 21. There's gap between them. You find their midpoints and find the true class boundaries, as we saw before as well. Find their true class boundaries. Find their true class boundaries. In this case, they turn out to be this. Okay, these are true class boundaries. And then in a histogram, on the vertical axis, you would always have frequency density. In A-levels, you would always have frequency density on the vertical axis. Okay, frequency density on the vertical axis, you have to label that appropriately. On the horizontal axis, you have whatever the variable is, that is marks, the number of marks in this case, that's what you have in the horizontal axis. Now, how do you calculate frequency density? Frequency density is frequency over class width. Now, for that, we need class width. What is class width? Class width is the upper boundary minus the lower boundary. Now, how do you find that? You are not just going to do 20 minus 1. That will be wrong. That's 19. That's wrong. The class boundary, the class width is going to be calculated after you have first found the true class boundaries. So you have to find true class boundaries first of all, and then use those true class boundaries to find the class widths. 20.5 minus 0.5, that's 20. 30.5 minus 20.5, that's 10, and so on for the rest of the data. And then frequency density is calculated as frequency over class width. You can use that to find frequency densities. And then you've got these frequency densities. And you've got these intervals, the true intervals, the actual intervals. These are the ones that you would draw there on the diagram now. You can draw them here like this. Your in this case, since the intervals are 0.5, 20.5, 30.5, it's often a good idea to start your axis in such a way that you have those values coming on these major lines. So start at 0.5 on the horizontal axis, so it becomes 10.5, 20.5, 30.5, and so on. It'll make it easier for you to draw that histogram. If you start from 0, then your bars will have to be passing through the midpoint of boxes. That's more difficult. You can do that as well if you want, but it makes it easier if you start at 0.5 like this. On horizontal axis, you can do something like this, and you start from a different number. But vertical axis, that always has to start from 0. Vertical axis cannot start from any other number. It always starts from 0. Vertical axis always starts from 0. So then you would just make bars like this, make sure that there are no gaps between the bars. Sometimes they ask something like this as well, that they give you some chart and they ask you what's the problem with this. If for example, they will give you a histogram and it would have gaps between it. So you would say it cannot have gaps. That's one problem. Sometimes they will give you something in which on the vertical axis, it would be frequency. You would say on the vertical axis, there has to be frequency density, right? So you'll find a couple of questions in the past papers where they ask you to identify what are the mistakes in this histogram, right? So there should be no gaps. And on the vertical axis, you need to have frequency density. That's what it would look like. Now, sometimes what happens is they give you a histogram again, and they want you to find some missing frequency. So they might have this histogram that's given, and some frequency here might be missing. For example, this might be missing. We don't know this, let's say. How do you find that? From the histogram, the areas of the rectangles, they represent frequencies, right? So for each rectangle that you have here, its area represents the frequency of that interval. Why? Because you can see that here, frequency density is calculated as frequency over class width, right? Frequency density is frequency over class width. So frequency would be frequency density into class width. So that's this base into height. Frequency density is the height. Class width is the base. When you multiply them, you get the area of the rectangle. That's frequency. So area of these rectangles, they give you frequencies. Okay, area of rectangles on a histogram, they give you frequencies. Then the last diagram is cumulative frequency curve. That's the last diagram that you've got. How do you draw this? You'll have a table like this. Okay, you've got this table, and you're given frequencies here. First of all, you have to convert this table to a cumulative frequency table. How do you do that? If 1 to 20, the frequency is 10, then less than or equal to 20, what's the total frequency? That's 10. Then less than or equal to 40, that's 10 plus 32, 42. Less than or equal to 50, that's 104, 62 plus 42, right? And so on. You find the cumulative frequencies from this, first of all. Once you have them, you have to plot these values now. The upper limit, the upper boundary, and the cumulative frequency curve. It's a very common error to end up plotting midpoints here on the graph. You don't plot midpoints here for cumulative frequency curve. You have to plot the upper boundary and the cumulative frequency. So 20 and 10 for the first point, and then similarly for 60 and 154 for this one, upper boundary and the cumulative frequency. Plot all of those points and you would join them. Make sure on the vertical axis, you clearly show that it's cumulative frequency. On the horizontal axis, you write down whatever the variable is, that's number of rooms, and then you can just, plot those points, draw a curve through them. It should touch 0 here at the bottom. It should touch the x-axis, and your vertical axis has to start from 0 like this. That's what the cumulative frequency curve looks like. Now, one very small point. In this case, the variable is number of rooms. Number of rooms is a discrete variable, right? It cannot be in decimals. The number of rooms, it has to be an integer. So in this case, the interval that's given, that's 1 to 20, right? So we could just say in the cumulative frequency, it's going to be less than or equal to 20. But if it was some other variable, that could be continuous, for example, if it represented length of something. Now, length is a continuous variable. If for length, you were given this data, you would first have to adjust it. You have to find true class boundaries, because length can be in decimals as well. We have to basically figure out what to do with values between 20 and 21 in that case as well, because we can have decimal values as well. So in that case, the boundaries that you would use for this curve would be less than 20.5, less than 40.5, less than 50.5, 60.5, 70.5, and 90.5. In that case, these would be the numbers that you use if it was a continuous variable. In this case, it's a discrete variable. So that's why we're just using the values as it is, because they cannot be in decimals. The number of rooms cannot be in decimals. But if it was some variable that could take decimal values, in that case, we would have to adjust the intervals. And in the graph, then, these would be the values that we use. Okay? These would be the values that we use in the graph, then, in this case. Okay. So if it was length, for instance, which is a continuous distribution, then you would have to use these values instead of the actual values. Okay. Number of rooms is a discrete variable that can only be an integer. Length or any other variable that's continuous, you have to use the true class boundaries. So the true class boundaries would be 0.5 to 20.5 and then 40.5 and so on. So the upper boundaries will actually come from there. So that's a small detail that you need to be aware of. Let's have a look at this. Sometimes what happens is you get multiple cumulative frequency curves. Okay, I'll answer that at the end. So when you have multiple cumulative frequency curves, in fact, let's go back to that. Now, from this graph, you'll have to do some calculation. For example, they will ask you to find the median of this data. So you have 200 here. How do you find the median? You would divide 200 by 2. That's 100. Corresponding to 100, you would have the median. So whatever value you have on the x-axis here, that will be the median. Similarly, they can ask you to find the lower quartile, the upper quartile. How do you find them? Lower quartile is n over 4. Upper quartile is 3n over 4. You would find that those values on the vertical axis and find the corresponding values on the horizontal axis, right? Sometimes they can ask you to find percentiles like this. For example, 30th percentile. How do you do that? 200 into 30 over 100, that gives us 60. So corresponding to 60 on the vertical axis, you can see whatever value you have on the horizontal axis, and that will give you that value. Now, this is the more tricky part of this. Sometimes they say something like this: estimate the number of days on which more than 80% of the rooms were booked. So this data represents number of rooms and the frequency, the number of days at which each of these number of rooms were booked. So if you want to find out the number of days on which more than 80% of the rooms were booked, first of all, let's find the 80%. What's the total number of rooms that we've got? Total number of rooms, the maximum number of rooms that you see here is 90. Okay, what's 80% of 90? 80% of 90 is 72. So what that means is we are looking for the number of days on which more than 72 rooms were booked. Now on this axis, you can see this is 72. More than 72 means you're looking at the right side of this part. Okay, this part. Now, on the graph, that corresponds to this shaded part. So what's the number of days corresponding to that you get? That's from 186 to 200. This interval. So what's the number of days? 200 minus 186. It would not be 186 because 186 is the number of days for which less than 72 rooms are occupied. We want more than 72 rooms occupied. Okay, so we were here. We want more than 72 rooms occupied. What that means is that's from 186 to 200. That's 14 rooms. Okay, you've done these problems in O-levels as well. That's how you would do that. Sometimes what happens is they give you multiple graphs, multiple curves on the same diagram. And then they want you to do something based on that. So you've got these two curves. One is for one data, that's country A. Another is for the other data, that's country B. We've got information about 900 babies and we've got their birth weights. Okay, we've got their birth weights for 900 babies in each of these two countries. We've got their cumulative frequency curves. They're saying use suitable data from these graphs to comment on, to compare the central tendency and spread of the birth weights of the two sets of babies. Central tendency is mean, median, mode. On a cumulative frequency curve, the only measure of central tendency that you can find is median, right? So you can find the median and compare them. 50th percentile, the total number of values, the total number of babies was 900. Half that gives you 450. So corresponding to 450, you've got 3.85 for one, 4.5 for the other. So you can say, no, sorry, 3.85 for one and 2.05 for the other. You write down their medians and you compare them. Okay, 3.85 for B and 2.05 for A. We'll comment on that in a moment. So that's the median. That's one thing that you can comment on. And then for spread, you can use interquartile range from this data. 75th percentile, 25th percentile, find their difference, upper quartile minus lower quartile, and that gives you these interquartile ranges. And then you comment like this, you say, on average, the birth weights in country B are more than those in country A. That's one comment on central tendency. And the variation in birth weights is also more in country B as compared to country A. Okay. So that's what you can comment. You make these two comments based on these calculations. That's a 6-mark problem. So you have to do these calculations first of all, median interquartile range, and then based on that you make these two comments, one on central tendency and the other on dispersion. The only measure of central tendency that you can find from this data, from this graph, is median. So you use that. And for spread, you could either find range or interquartile range. If you can find interquartile range, that's a better measure. So that's what you would use. Compare them and you get the result. Okay, so that's all the concepts that you've got here. Let's have a look at just a few questions quickly and then we end. Okay, so we've got this data. These are amounts of money spent close to the nearest $10 by 27 people. Construct a stem and leaf diagram for this. Now, let's think about this. Remember, in the stem, in the leaf, you can only have one digit. In the leaf, you can only have one digit. Now, what's the smallest value in the data? That's 10. Largest value in the data? That's 570. Right? These are the smallest and the largest values. How do we think about what to put in stem and what to put in leaf? If you say the last digit only is going to come in leaf, then in the stem, that means you have data from 1 to 57. That's a lot. 1 to 57. You'll have to write down all of those values: 1, 2, 3, 4, 5, 6, all the way up to 57. And notice all of them are zeros here. So leaf is not going to be very interesting because it will just be zeros there. The last decimal is 0 for all of them. So what do we do then? These values are given corrected to the nearest $10. So that is why the last digits are all zeros. So using 1 to 57 as stem is not going to help in this case. We can think of it like this. This is 0, 1, 0, right? The 100 digit is 0 in this case. 0, 4, 0, 0, 6, 0, 0, 8, 0. So we're basically going from 10 to 570. 10 to 570. So in the stem, what we can do is we can use 0 to 5. In the leaf, we can have the tens digits. And since the last digit, the unit digit is all zeros, we can just represent that in the key that we would write. Okay, so we make a stem and leaf diagram that looks like this here. We start from 0 and at 5. We write down these values in the leaf like this. For example, 10, 40, how do you write them? 1, 4, 6, 8. Similarly, for values in 300s, for instance, you've got, okay, let's look at values in 200s, for instance, these values. In the leaf, you have 0, 1, 5, 7, 8. Because in the leaf, you cannot have multiple digits. You can only have one digit. So you write 0, 1, 5, 7, 8 in the leaf like this. And then what you do is, in the key that you draw, and the key that you mention, you say something like this: 2 and then vertical line 3, that represents $230. So that 0, the last 0, that will come in the key here. That will be represented here. Okay, so that's the more complicated type of stem and leaf diagram that you would see sometimes, in which it becomes a bit confusing what to take as the leaf. Then you have to find median and interquartile range. We've talked about that before. In the third part, it says, an outlier is defined as any data value that is more than 1.5 times the interquartile range above the upper quartile, or more than 1.5 times the interquartile range below the lower quartile. Now, this is not a general definition that's only given in this particular question, right? And for this particular question, we can use that as the definition of an outlier. We have to list down the outliers. How do you do that? You've got this data. We are given the definition of an outlier in this question. More than 1.5 times the interquartile range above the upper quartile. What does that mean? Wherever the upper quartile is, you have to be 1.5 times the interquartile range above the upper quartile. And upper quartile plus 1.5 times the interquartile range. If any value is greater than this, that's an outlier. Similarly, let me just show that to you first. So upper quartile plus 1.5 times the interquartile range. If any value is greater than this, that's an outlier. So greater than 315, that's an outlier. And any value that's more than 1.5 times the interquartile range below the lower quartile. What does that mean? Lower quartile, subtract 1.5 times the interquartile range from that. Any value that's lower than that, that's also an outlier. So you can understand it like this. You've got median in the middle, right? You've got lower quartile here, upper quartile here. So if you go 1.5 times the interquartile range to the right of the upper quartile, this region is going to be an outlier. And then you go 1.5 times the interquartile to the left of the interquartile, to the left of the lower quartile. This region is going to be outlier as well. So we understand from this, any value that is less than 35, any value that's less than 35 or greater than 315, that's an outlier. So we look at the data and spot any values that satisfy those conditions. 10 is less than 35, 570, 450. These are greater than 315. So these are the three outliers that we've got. Based on this definition, we say the outliers are $10, $450, and $570. Okay, that's how you interpret that. Okay, let's have a look at this. Now, just a few simple examples, and then we end. Find the mean weight of the 27 birds. We've got this data for some birds and their mean and standard deviations given for some turkeys and some geese. We want to find the mean of all 27 birds. We've got data given for them separately. How do you find mean? Mean is given by sigma x over n, right? Sum of all values divided by the total number of values. What's the sum of all values going to be? Mean of this data is 7.1, and there are 9 of them. What will be the sum of these values? 9 into 7.1. What will be the sum of these values? 18 into 5.2. So the sum of all values is going to be these two things added together, divided by the total number of values, that's 27, and that will give you the mean like this. Okay. Then they say weights of individual turkeys. They are denoted by xt, and for individual geese, we have xg. We want to find sigma x squared for both of them, and then find the standard deviation of all 27 birds. Now, what's the standard deviation formula? Standard deviation formula looks like this: sigma x squared over n minus x bar whole squared square root of that. That's the standard deviation formula. Now, for this, we need the value for n. We know that that's 27. Mean, we have found that in the first part. That mean was 5.83. So we've got those two pieces of information, but we do not know sigma x squared. Sum of all x squares. How do you find that? We've got information given for them individually like this, for turkey separately and for geese separately. What we can do is we can use the standard deviation that we have for them. We can use the standard deviation that we have for them to find their sigma x squares individually, right? So we know for turkeys, the mean is 9. For geese, it's 18. That's given. No, there's something wrong here. Mean, that's the number of values, sorry. Number of values for turkeys is 9. Number of values for geese is 18. We've got their means given, 7.1 and 5.2. And we've got their standard deviations given. So we've got this information given in the form of the table above. If the standard deviation of turkeys is 1.45, we can use this formula to find sigma xt squared. Similarly, for geese, we can use that same formula to find sigma xg squared. So you find sigma x squared for turkeys, sigma x squared for geese. What's the overall sigma x squared going to be then? Just add them up together, and that will give you the overall standard deviation. This is the total sigma x squared divided by the total number of values. That's 27 minus mean squared and square root of that. And that gives the standard deviation of all of those keys, right? So sometimes they give you problems like these in which they split the data into 2 parts. And you have to find the overall mean of the overall standard deviation. You can find the individual sums and then add them up together, individual sigma x squared, and then add them up together to use in the formulas. Okay. Okay, just a few more examples. Let's have a look at this now. We've done something very similar before as well, by say. This is linear transformation. Sigma x minus 45, that's equal to this. Sigma x minus 45 whole squared is equal to this. In these problems, I told you, you can use a substitution. You can say, let this equals y. So then sigma y is equal to 1 minus 148. Sigma y squared equals this. Find the mean and standard deviation of the 36 values. Which 36 values? Values of x. So what we can do is we can find the mean and standard deviation of y, right? Find the mean and standard deviation of y. Mean of y turns out to be this. Standard deviation of y turns out to be this. Standard deviation of y turns out to be 80. Oh, there's something wrong somewhere. It's not supposed to be 80, I think. 3086 minus that. The square root of that, because both of them have to be equal to each other. 100 minus that. Okay, so this value is also 8.3. Okay, so what we do is we find the value of the mean of y, the value of the standard deviation of y, and then we say if y is equal to x minus 45, then the means are going to have the same relation. If we know y bar, we can find x bar from that. And the standard deviations are going to be equal. If the standard deviation of y is this, standard deviation of x is also going to be the same. Now it says one extra value of 29 is added. Find the standard deviation of all 37 values. How do we think about this now? We have another additional value that's 29 that is added to the data. Standard deviation of all those values. Now we need the mean for that as well. Now earlier we knew that the mean was 40.88, right? That was the earlier mean. Can we find the sum of all values from that? 1471.68 sigma x, we can find that. Now there's another value that's added, that's 29. It becomes, the new x bar becomes sigma x, the new sigma x, earlier sum, plus 29 divided by the total number of values, that's 37, and that gives the result for the mean. We do the same thing for standard deviation as well. We've got the old standard deviation. Earlier, the standard deviation was 8.30 that we found there. Use that to find sigma x square. That will be old sigma x square. Now for the new standard deviation, you can say the sigma x square now is going to be this number plus the square of this number that was added. That's 29 squared. That's what you put in the numerator here, minus mean squared divided by n, and that will give you the result, which turns out to be 8.41. Okay. So you have these questions in which sometimes they add another value or remove a value. You need to be able to work with these problems as well. Okay, let's have a look at this. We've got this data that represents time after opening. That represents the number of people entering a store after a certain number of minutes that the store is open. For example, in the first 10 minutes, you've got 210 people, and so on. Afterwards, first of all, they say find the values of A and B. How can we do that? We know the total cumulative frequency, that's 540. So the sum of all these values has to be 540. So that gives us the value for B. And then this is missing, this value for A. What do we do for that? What information do we have? Okay, so what we can do is we can say this is 540, or we can do it this way as well. This is 422. Add 72 to that. That will give you this cumulative frequency. That's the value of A. That's pretty straightforward. The first part, you have to draw a cumulative frequency curve that looks like this. That's what the curve looks like. And then median time, again, that's also fairly straightforward. The total number of values was 540. 540 divided by 2, that's 270. You can find the corresponding value to 270, and that will be the median. So the first three parts are fairly straightforward. What about part 4? Calculate the mean and standard deviation. You've got this information that's also fairly straightforward. You've got midpoints. You can find xf, x square f, and find the mean and standard deviations from that. You've got these x values, and you've got xf, x square f. The only difference is that these values are given in the form of a column table here. Earlier, normally we have row columns. In this case, just in the form of a column. Earlier, and we have row tables. In this case, we have a column table. That's the only difference, but the process remains the same. This is the last part that I wanted to actually talk about. Use a graph to estimate the number of people entering the store between m minus half s and m plus half s minutes after opening. What does that mean? M is the mean, S is the standard deviation. Now we have found the values of m and s in the previous part. So they turn out to be this, 18.2 and 14.2. M plus half s and m minus half s is input values there. You get 11.1 and 25.3. Now, you want to find the number of people who enter the store between these time intervals, within this time interval, 11.1 to 25.3. Go to the graph. This is 11.3 and this is 25 point something. On the vertical axis, you get 230 and 385. So the difference between them, that will give you the number of values. which turns out to be 385 minus 230, which is 155. And that's the result that we got. Okay, it turns out it wasn't that difficult. Yeah, so let's have a look at this. You've got some data points here. This is ungrouped data. Don't think that it's a table, so it's grouped data. There's no frequency here. These are ungrouped values. This is raw data. So use the first formula, sigma x over n and sigma x squared over n minus x bar whole squared to find the mean and standard deviation. And you can do that. That's pretty straightforward. What about this? They say state with a reason which team has more consistent scores. What does that mean? More consistent scores? The one that has less variation in the data. That has less variation in the data. Now, look at the data and see which data has less variation. Now, they have not made you find the standard deviation for the other data. They've only made you find, okay, they actually gave you these values. So they gave you the values. You found the standard deviation for X as 83.14, and they're telling you that the standard deviation for B is 29.63. Now, they've also given you the mean value for this, although that's not going to be used anywhere. That's just for confusing you. Consistent means the one that has less variation. Consistent means more consistent means less variation. So you compare the standard deviations, you say B is more consistent because the variation in these numbers is less. Okay, team B has more consistent scores because it has a lower standard deviation. Okay, the variation is less, so that means the consistency is higher. Okay, let's have a look at this. So the first part is straightforward. You have to find mean and standard deviation given this information. But then what happens is one person leaves the group and the mean age of the remaining 17 people is exactly 41 years. So in the first part, we found the mean, that's 41.39, standard deviation 13.16. We need to find the age of the person who left and the standard deviation of the ages of the remaining people. Now, how do you find that? They're saying that the new mean is now 41. New mean is now 41. Now, what was the sum of values earlier? 745. If one person is left, let's call the age of that person as A. Let's call that A. What's the sum of values now? 745 minus A, right? Divided by the number of values. It was 18 people earlier, now it's 17 people. Divided by 17, that should equal 41. And that should give you the value for A. Once you have that, you can find the standard deviation for that new data. That's not that complicated after that. So you can have some value removed from the data like this, and you might have to find the new means, new standard deviation, or some other missing information from the data like this. Okay, one last example. These were pretty straightforward examples, most of them actually. Summary of 20 values is given. Sigma x minus 30 is this, sigma x minus 30 whole squared is this. Again, this is coded data, linear transformation. A summary of another 25 values of x gives this and this. So you've got two sets of values. One has 20 values and the other has 25 values. We need to find the mean of all 45 values of x. How do you think about it? Use a substitution. You say y equals x minus 30. Then we can say sigma y is this, sigma y for the other one is 470. What's the mean for all of them? You add up both of them, divided by 45. That gives you the overall mean for y. And then you know that y bar is equal to x bar minus 30. Just use that to find the mean for x as well. Similarly, standard deviation for all values of x, do the same thing again. Sigma y squared is this for one, for 20 values. For the other 25 values, sigma y squared is this. You find the sum of them to find the overall sigma y square. That's going to be the numerator here, divided by 45 minus the mean squared and square root of that, and that gives you the result. And that's it. This is all that you need to know about representation of data. I hope that was helpful. It's been 2 very long sessions, but we're going to stop here now. If there's any problem, you can let me know. Okay, children, let's resume. This is the next topic that we're starting. Discrete random variables. It includes binomial distribution and geometric distribution as well. So let's begin with this. First of all, we need to understand the difference between discrete variables and continuous variables. What are discrete variables? Discrete variables are variables that can only take some specific values. For example, if you consider any interval, for example, let's say I have this number line on which I have 7 and 11. So I have an interval from 7 to 11. If I have a variable that represents, for example, shoe sizes. Now, shoe sizes normally they are at an interval of 0.5 at max, or sometimes in some stores 0.25, but not more than that. You can't have a shoe size generally of 7.35723, right? You can't have something like that. That's generally not possible. So there are only specific values. There are only specific values that are possible. In the interval, we can't have like 8.35237, right? Something like that. This is a discrete variable that can only take some specific values. You can count how many values are there inside a particular interval. So from 7 to 11, you can count how many values exist. Compare that with the continuous variable that can take any real value. It could be any decimal value. For example, if we talk about height of a person, now, depending on the accuracy level of the measuring tool you have, you could go to as many decimal places as you want. So if I were to ask you how many different possible values of height are there between 5 feet and 6 feet, there are infinitely many possible values, right? There are infinitely many possible values, right? You could have any decimal number between 5 and 6. That's a continuous variable, right? Because there's no restriction as such of the number being integer or anything. Now, in your syllabus, the discrete variables that you would see, they would mostly be integers. They would not even be decimals like this. Now, in this topic, we'll be talking about discrete variables. In normal distribution, we'll be talking about continuous variables. Now, first of all, you need to be able to draw probability distribution table in this topic. Now, what are they? So basically, let's consider this example for that to understand that. Let's say you have a scenario like this, that you have a spinner, and the spinner has 3 numbers written on it. One is number 1, then 2, number 3. And they have different probabilities based on the angles that are there on the spinner. Let's say the probability of getting 1 is 45 over 360, of 2 it's 90 over 360, and 3 is 225 over 360. Now, if you were to write down these probabilities in the form of a table like this, that in the table, there's one row that shows you the x values and the other row that shows you the corresponding probability values. This table is known as the probability distribution table. So it's a table in which you list down all the possible values of x and the corresponding their corresponding probabilities. Okay, that's called a probability distribution table. Now, using this table, you need to be able to find two things: expected value of a variable, that's given by sigma xp. This is given in the formula sheet as well, under the discrete random variables headline. You can see this formula written: expected value of x, that is equal to sigma xp. Variance is given by sigma x square p minus expected value of x whole square. These are two formulas for discrete random variables that you can use. Now, expected value, there are different names that you have for this. There are different notations that you have for this as well. This is one notation, expected value of x. This is actually just another name for mean of a variable. So we can also write this as mean of x. This is also written as x bar. This is also written as mu. All of these are different notations for the same thing: expected value of x, mean of x, x bar, mu. Okay. So these are two formulas that you need to be able to use. How do you find mean of variable then? You add another row to the data. So this is x, this is p. Add another row to the data that represents x times p. Evaluate these numbers, add them up together. That gives you sigma of xp. That will be the value for the mean. Add another row to the table for variance. That's x squared times p. How do you calculate x squared p? You can square x and then multiply that by probability. Or you could also think of it like this to make this calculation easier. when you have XP already calculated, you could just say it's X times XP, right? So multiply these two numbers, that will become X square P, and write down these numbers and see what the total turns out to be. That's sigma X square P. Just input that in the formula for variance. You will get the value for the variance from that. Okay. If you have to find standard deviation, that will be the square root of this number. Now, these formulas actually come from the same formulas that you saw earlier in representation of data. So it's the same formulas, it's just the concept of relative frequency. This is relative frequency that can be written as probability, and you get these formulas. Right, that's just an additional thing. These formulas are going to be given in the formula sheet. You just need to be able to use them. That's one thing that you need to be able to do, that for a given situation, you have to make a probability distribution table, and then using that, you may have to find expected value or variance of that variable. Now, probability calculations, they are going to be the same as what you did in the probability topic earlier. So it'll be very similar to that. You'll have to use the same ideas. You'll have to make tree diagrams. You'll have to make 2D tables, 2D matrix, which we call possibility diagram. And sometimes, in some cases, you would have to use permutations and combinations as well to find probabilities. We discussed that as well, that when you have combinations, for example, you can find probability by finding the number of favorable outcomes, the number of favorable combinations divided by the total number of possible combinations. So for finding probability, you just have to use the previous topics, but the questions here tend to be a bit more complicated as compared to the simple probability questions that you'll see. Let's have a look at some of these examples. Let's say you've got two fair dice that are thrown. There's a random variable X that is the smaller of the two scores if the scores are different, and the score on one of the dice if the scores are the same. Again, the most important thing here is to understand the question statement correctly. Okay. So X is the smaller of the two scores if the scores are different, and score on one of the dice if the scores are the same. Copy and complete the following table to show the probability distribution table for X. So we're throwing two dice. Whenever you're throwing two dice, it's often a good idea to make a 2D table to represent that information. So you've got 1, 2, 3, 4, 5, 6 here, 1, 2, 3, 4, 5, 6 here. How is score calculated? If the scores are different, it's the smaller score. If the scores are the same, it's just that same score. So on the diagonal, it's the same score, 1, 2, 3, 4, 5, 6, because on the diagonal, the scores are the same. And the rest of the values, for example, here, you just find the difference. No, you just use the smaller of the two values. So this is coming from 4 and 2. The smaller value from this is 2. You use 2 here. And so on. For example, this number 3, where is this coming from? This is 5, this is 3, the smaller number is 3, so the score is 3. So this table represents all the possible scores, and then you have to just make that, complete that table. You just count these values, 36 values in total, write down the probabilities by counting the number of ones, number of twos, number of threes, etc., and you get the result from that. And then you have to find expected value, add another row to the data set, XP, and then calculate sigma XP, you get the answer from that. That's pretty straightforward, but sometimes it becomes a bit more complicated. You see such a big question statement. That's a lot of parts and a lot of information. Let's have a look at this now. So this person, Sankrit, plays a game using a bias die. Bias die, what does that mean? The probabilities of each outcome, they are not the same. So this bias die is such that it's twice as likely to land on an even number as on an odd number. So probability of getting an even number is more as compared to an odd number, and that's twice that. Okay. The probabilities of the three even numbers are all equal, and the probabilities for the all three odd numbers are all equal. Find the probability of throwing an odd number with this die. How do you think about it? They've given you that it's twice as likely to land an even number. So what's the ratio between even and odd? The ratio would be 2 to 1. So the probability of getting an odd number is just 1 out of 3. And you just write that down. Probability of getting an odd number is 1 out of 3. Okay. So that's fairly straightforward, the first part. Now it says Sankit shows the die once and calculates his score by the following method. So you've got the score calculation. Now you have to think about how the score is being calculated. If the number thrown is 3 or less, he multiplies the number thrown by 3 and adds 1. Okay. So the die is thrown only once. If the number is 3 or less, the score is calculated like this. He multiplies by 3 and adds 1. If the number is more than 3, multiplies the number thrown by 2 and subtracts 4. So that's how the score is being calculated. The random variable x is Sankit's score. Show that probability of x being equal to 8 is 2/9. Now, how do you think about this? Score being equal to 8. Now, how can you get a score of 8? You can think about all the possible scores. You can actually list down the possible scores for each number separately. So one possibility is to just think of it in your head. The other possibility is you might need the other values later on. Well, you actually don't. So just think of 8. How can you get a score of 8? So think about it. If you use 1 into 3 minus plus 1, that's going to give you 4. That's not going to work. 2 into 3 plus 1, that is 7. That's also not going to work. And then 3 into 3 plus 1, that is 10. That's also not giving you 8. So if the number thrown is 3 or less, that's not giving you the score of 8. Okay, so that's not possible. If you get a score of 8 using a number that's greater than 3, how is that going to be possible? The number bigger than 3 is going to be multiplied by 2. Now we're using this rule. 4 into 2 minus 4, that's just 4. If it was 5 into 2 minus 4, that is 6. And 6 into 2 minus 4, that will give you 8. Now you can just think of it in your head. So in your head, when you think about it, you would realize that the score is going to be 8 when the number on the dice is equal to 6. So when the number on the dice is 6, that is when you get a score of 8. Okay. And then what's the probability of getting a number 6? We know that even number has a probability of 2/3. There are 3 even numbers. We divide by 3. That gives us 2/9. And that's what we wanted to find out here. Now the next part says show that expected value is this and variance is this. They've given you the table already. You can do those calculations. That's fairly straightforward. Probability, now he's throwing 2 dice. Find the probability that the total of the scores on the 2 throws is 16. Total score is 16. Now, how can you get a total of 16? You've got all possible scores here. How can the total be 16? You can do 6 plus 10. Right, that's one possibility. But it could also be the other way around. It could be 10 plus 6 as well, right? So you have to consider both possibilities. With 7, you can't have it. You can have 8 and 8. So you get 3 cases in total. Number 1, you can have 6 and 10. You can have 10 and 6, and then 8 and 8. Right? 8 and 8, if you switch that, that's the same case. You should not count that twice, only count that once. So 6, 10, 10, 6, and 8, 8. These are the 3 possible cases that you're getting. Just find their probabilities. 6 and 10. Probability of getting a 6 is 1/9. Of getting a 10 is 1/9. You multiply those two, and that gives you the first case. 10, 6 is going to be the same, 1/9 into 1/9, and for 8, 2/9 into 2/9. Evaluate that, and you get the result from that. Okay, so it's either this case or this case or this case. So we find the probability for each one of them, and then we add them up together. That gives us the total result. It's actually not that difficult. Now, the last part says, now this is conditional probability. Given that the total scores is 16, find the probability that the score in the first throw was 6. Now, this is where this is very helpful to write down where these values are coming from in your calculation. So you had 6, 10 as the first case, 10, 6 as the second case, 8, 8 as the third case. They're saying, given that the score is 6, the total score is 16, find the probability that the first was a 6. So in the denominator, you have the probability of the given thing. That's 2/27. We found that in the previous part. In the numerator, we have the probability of the intersection when both of those conditions are met. When are both conditions met? In the first scenario here, in that case, the first number is a 6 and the total is 16. So that's the condition. That's what you have in the numerator here, 1/81, and that gives us the result. You can see what that turns out to. Okay. Yes, of course, that's coming. Okay, so that's this. Let's look at the next one. We will do binomial geometric. These questions sometimes tend to be a bit tricky. The discrete random variable questions, so I'm just going through some of them. Then we do binomial and geometric afterwards. A spinner has 5 sides numbered 1, 2, 3, 4, 5. When the spinner is spun, the score is the number of the side on which it lands. The score is denoted by the random variable x, which has the probability distribution shown in the table below. Find the value for p. Now, a lot of times what happens is they give you a table like this in the question, and they want you to find some missing value here. How do you do that? In a probability distribution table, you've got all possible outcomes given and their corresponding probabilities given. We know that the total probability is always equal to 1. So what you would do would be you would add up all of these values, equate them to 1, and that will give you whatever that unknown is. In this case, that value of p turns out to be 0.1. Then the second part says a second spinner has 3 sides. So the first spinner had 5 sides, and we had their probabilities given. Now the second spinner has 3 sides numbered 1, 2, 3. The score when the spinner is spun is denoted by the random variable y. It's given the probability of y equals 1 is equal to 0.3, of 2 is 0.5, of 3 is 0.2. Find the probability that when both spinners are spun together, the sum of the scores is 5. Now, how can we get a sum that is equal to 5? Now, you could either make a table for this, make a 2D table. We've got two things happening at the same time. One spinner has 5 sides and the other has 3 sides. You can make a 2D table, or you can just think of it in your head. That's your choice. So you can do it both ways. Since we want the sum to be equal to 4, how can you get a sum of 4? 1, 3, 2, 2, and 3, 1. These are the possible cases that you have. You list them down, find their probabilities. You've got the probability distribution table for them. Now, one possible case is x is 1 and y is 3, so that's 0.3 into 0.2. You'll find this probability, and similarly for the other cases, add them up all together and you get the result from that. Okay, again, not that difficult. Now, the third part says the product of the scores is less than 8. Now, again, one possibility is that you make a 2D table and write down the products in that. Now, it says the product is less than 8. Product is less than 8. Now, one possibility is that we find all the possible cases in which the product is less than 8 directly. That's one possibility. How would it be less than 8? If x is 1, y could be 1, 2, 3. So you have 3 cases here. With 2 as well, y could be 1, 2, 3, and all of them, product will be less than 8. So that's 6 cases. With 3, you could have 1 and 2. That's 8 cases. With 4, you can have just 1, and with 5 as well, we've got 1. So that's 10 cases in total. An alternative could be, since that's a lot of cases, you could do the other way around. You could say, okay, probability of the score being less than 8, that's the same thing as saying 1 minus the probability of the score being greater than or equal to 8. What would that mean? The number of cases would reduce now, because greater than or equal to 8 would be when you have 3 times 3, that's one case, and then 4 times 2 and 4 times 3, and 5 times 2 and 5 times 3. So that will be 5 cases, much smaller number of cases to evaluate. So that's 5 cases. You can do it this way. You can say, okay, the total probability is 1. Let's find the cases in which this product is greater than or equal to 8. Okay, so that's 3, 3, 4, 2, 4, 3, 5, 2, 5, 3. Evaluate each of these probabilities, add them up together, and you get this result. Now that's the probability of the product being greater than or equal to 8. For less than 8, you would just subtract that from 1, and that gives you the final result. Okay. In this case, we cannot just do total number of favorable outcomes divided by total number of possible outcomes. That does not work because the probabilities are not the same, right? Probability of each outcome is different. So number of favorable outcomes divided by total outcomes, that formula is not relevant here. We can do this with binomial distribution. Not really. How would you do this with binomial distribution? That would not make sense. In binomial distribution, we have something that has to be repeated. and the probabilities should remain the same across those repetitions. In this case, we don't have any repetitions that are happening, so no, this is not binomial distribution. This cannot be done using that. Okay, let's have a look at this example. It says the random variable x takes these values -2, 2, and 3. It's given that probability of x equals x. That is given by k into x squared minus 1. Where k is a constant, draw up a probability distribution table for x, giving the probabilities as numerical fractions. Now, this is another type of question that you'll see a lot in recent papers. They give you a formula for finding probability. So that looks like this. And they give you the possible values of x, -2, 2, and 3 in this case. Can you find the probabilities in terms of k? X equals -2, you put x equal to -2 here, you get 3k. When x is equal to 2, the second value there, you get 3k. When x is 3, you get 8k from that. You've got these three different probabilities. Now, they want the probability distribution table to have numerical fractions. That means you don't want a fraction in terms of k. So you have to find the value for k first of all. How do you find the value for k? You can just add up all of these numbers. The total probability has to be 1, and that will give you the value for k. Once you have that value for k, you can write down, you can draw that probability distribution table, and then you can find variance and expected value using the formulas after that if you have to. Okay, now this is very important. So there are some questions in which you can use combinations sometimes. Okay, so let's have a look at this. A vegetable basket contains 12 peppers, of which 3 are red, 4 are green, and 5 are yellow. 3 peppers are taken at random and without replacement. So you're not replacing the pepper that's taken out. Find the probability that the 3 peppers are all different colors. What does that mean? That means one has to be red, another has to be green, and the other has to be yellow. So that's 3 different colors. What's the probability of getting a red pepper? You can say that's 3 out of 12 for a red pepper. 4 out of 11 for green, because you're not putting that back, right? You're not putting that back. So the total number would reduce. That will be 11. And then the next time for the yellow, we've got 5 over 10. That's the probability of getting 3 different peppers. But now the problem is, think of the tree diagram. How would the tree diagram look like for this? First time you take out a pepper, that would either be red or green or yellow, right? The second time again, it could either be red, green, yellow, red, green, yellow, red, green, yellow. And then for each of them, you've got further possibilities: red, green, yellow, red, green, yellow, and so on. Now, the probability that you have found here, this is just for one possible path on the tree diagram, just one possible path in the tree diagram, from which you get 3 different colors, and that is R, G, Y. This is one path, but can you follow another path on the tree diagram that also gives you 3 different peppers? You could do, for instance, something like this. This is R, G, Y. You could say, let's go from R to Y and then to G. This is another possible path that you could follow. Now, there are many other paths as well. How many different paths like this exist? How many different paths like this exist on the tree diagram? Because you would have to find all of those probabilities and then add them up together. You'll have to sum them up together. We have only found this for one possible path that we have on the tree diagram. Now, how do you find it for the rest of them? This was one possible path, RGY. It could be another, there could be another YRG. All of them are going to be the same, right? Because the denominators are going to be the same for all of them, and the numerators are also going to be 3, 4, and 5. How many paths like this exist? We would have to add all of them up together. How many paths exist? These are 3 letters, and how many ways can we arrange them? Because that will give us the different possible paths, right? We can arrange these in 3 factorial ways. 3 factorial ways. So we say we would have to, 3 factorial is 6, right? So we would have to add this probability 6 times, because there will be 6 different paths on the tree diagram that give us the same probability. So adding this number 6 times, that's equivalent to saying, let's just multiply this number by 6. That's 3 factorial, and that gives us the probability that's 3 over 11. Okay, so this is how you would approach this problem. If you were to do this directly like this, using by thinking of the tree diagram, this is just for one path on the tree diagram. You multiply by 3 factorial to consider all the possible paths on the tree diagram. Okay. Multiply by 3 factorial. So you can simplify this and then multiply by 3 factorial, multiply by 6. Yeah. But there's an other easier way of doing this that you should definitely know how to work with, and that is using combinations. Whenever it says without replacement, we could use combinations in such problems as well. We could say, okay, we want 3 peppers that are all different colors. So we could say, we want 1 red, 1 green, 1 yellow. So out of 3 red, we say, let's select 1 red. Out of 4 green, select 1 red. Out of 5 yellow, select 1 yellow. Out of 3 red, select 1 red. Out of 4 green, select 1 green. Out of 5 yellow, select 1 yellow. That's 3C1 into 4C1 into 5C1. Divided by the total number of possible selections, you've got 12 peppers. Out of them, you have to select 3. That's the total number of possible selections. That gives you 3 over 11 directly. So you could do it directly like this using combinations. That's much more efficient, much easier. So this is what you should do in such problems. Rather than thinking of it directly like this, that's a bit more complicated. A lot of people get confused by multiplying with 3 factorial here. Using combinations makes it much simpler. Let's look at the second part of this. It says, show that the probability that exactly 2 of the peppers taken are green is 12 out of 55. Now, using combinations, that would become, if 2 are green, we are saying, out of the 4 green, we have to select 2. So that's 4C2. And then out of the remaining 8, we have to select 1. So that's 8C1. Divided by the total number of possible selections. The total number of possible selections is just 12C3. And that gives us the result that's 12 over 55. So you can do it directly like this using combinations. The alternative would be that you use that factorial thing again. You could say, okay, you could have 1 green, another green, and then the third not green. Okay, just write that as not green. Don't use the colors because that will make it more cases. So you could say you have GGR and you have GG yellow. But an easy way of doing this is to combine them and say you have 2 green and the third not green. Okay, that will make things simpler if you were to do it directly like this. And then you would say, okay, green, the first being green, the probability of that is 4 over 12. For the second being green, 3 over 11. For the third being green, 8 over 10. And then in how many ways can you arrange this on the tree diagram? How many of the different paths would give you the same case where you have 2 green and the third not green? 3 factorial divided by 2 factorial, because of the 2 g's here, they're identical. That's the number of paths that you have, and that gives you 12 over 55. Okay, so you can use any of these methods, but as you can see, this is much simpler using combinations. And then they say the number of green peppers is taken as denoted by the discrete random variable x. Draw up a probability distribution table for x. X represents the number of green peppers taken. So we could say, okay, we're taking 3 peppers in total. The number of green peppers, what could they be? It could be 0, it could be 1, it could be 2, it could be 3. Okay, find the probability for each one of them. We've already found that for x equals 2 earlier. That turned out to be 12 over 55. For x equals 0, we could say out of 4 green, select 0, and then out of remaining 8, select 3, divided by 12C3. X equals 1, out of 4 green, select 1, and then out of remaining 8, select 2, divided by 12C3. And similarly for x equal to 3 as well, you can write down those probabilities there, and that completes the probability distribution table. That's like a 5-mark question. Using this combination notation, it becomes very straightforward, very easy. Make sense? Okay, let's move on. Okay, just one last example on this, and then we move on. This is an important concept. Sometimes in questions, they will say that you have a large number of objects. A large number of objects. What does that mean? Large in this context means an infinite number of objects. So think of a factory that's making ropes. It has, an extremely large number of ropes. Now, why is that important? We'll see in a moment. With lengths either 3 meter or 5 meter, there are 4 times as many ropes of 3 meter as there are ropes of 5 meter. Now, what's the ratio? 4 times as many ropes of 3 meter. Okay, so if 3 meter ropes are 4, then the 5 meter ropes are just 1. Now, if this was a small number like 4, 1, or you could say 8, 2, any ratio, any number that's relatively smaller, then if you're taking multiple ropes, if you're selecting multiple ropes, what would happen would be, if you take out one rope, for example, if you take out one 3 meter rope, let me just use, so it might confuse some people, let me just use 4 and 1. That was the ratio, right? So let's say 3 meter ropes were just 4 and 5 meter ropes were 1. If you were to select one rope, let's say 5 meter rope, the probability of that would be 1/5. Now, the next time if you were to select a rope, what would be the probability of selecting a 5 meter rope? That will become 0, because it will be 0/4. Or if for selecting the 3 meter rope, that will become 4/4. The idea is the probability would change when you take another rope after that, right? It would be without replacement, right? It's without replacement. So the next time you take out a rope, the total number is going to change in the denominator. If it's a small number, it'll have to be considered as without replacement. However, this condition that they've given here, that it's a large number of ropes, what that means is these numbers are very big. So for example, something like this, too many zeros here, right? A lot of zeros. And the ratio is this 4:1. Now, if you have so many zeros, if you take out one rope, the probability is not really going to change much, right? So out of a billion ropes, if you take out one, the denominator does not really change by much. 1 billion minus 1, it doesn't make much of a difference. So if it's a very large number, the change in probability that you have is negligible. So we assume that the probability remains constant in this case. That's the reason why they've said that it's a large number of ropes, so that you can assume that the probability of selecting a 3 meter rope or selecting a 5 meter rope, that would not change, right? Because the number is so big, even if it changes by 1, it doesn't have a lot of impact. So the change is negligible. Now keep that in mind, that the probability remains constant. And now they're saying one rope is chosen at random, find the expectation and variance of its length. How do we think about this now? We can write down the possible write down the probabilities for them. Let's say x length is represented by x. Then x can have two possible values. It could either be 3 or 5. We know their probabilities, 4/5 and 1/5. So that's what the table is going to look like, probability distribution table. Now you can use this to find the expected value, the variance, and that will give you the result. Now it says 2 ropes are chosen at random. Find the probability that they have different lengths. How do you do this now? 2 ropes are chosen at random. As I said, you would assume that the probabilities remain constant. They do not change because of this large number of ropes. So if the 2 ropes have different lengths, what does that mean? The first could be a 3 meter rope and the second could be a 5 meter rope, or the first could be a 5 meter rope and the second could be a 3 meter rope, right? These are the two possibilities. If you make a tree diagram, these are the two paths that you follow, 3, 5 or 5, 3, right? Find their probabilities, 4/5 into 1/5, 1/5 into 4/5, and that will give the result. You can see what that turns out. We do not change the denominator. Remember, this is just the ratio. We don't know what the actual number is. The actual numbers are very big, right? These are just simplified versions. So you can't do something like this, that it becomes 4/5 into 1/4. That would be incorrect, because the actual numbers are not 5, 4, 1. The actual numbers are much bigger. Okay, so the probability will remain the same. That will not change. And then they say 3 ropes are chosen at random. Now find the probability that the total length is 11. Now, how do you think about this? 3 ropes are chosen. How can you get a length of 11? With 5 and 5, you can't have 11. With 2 3s, you can have 3 3 5. So you can have 3 3 5, right? That's the only possible scenario in which you can have the total to be 11. But in how many ways can you have 11? 3 3 5. It could be 3 5 3. It could be 5 3 3. You have to consider those 3 cases. 3 3 5, 3 5 3, 5 3 3. Add them up together. Since the probabilities are the same, you just find one of those cases, multiply that by 3, because we have to add that number 3 times, right? Just multiply that by 3, and that gives the result. You can see what that is. That's this number. Okay, so the key point here in this question was understanding when it says a large number of objects, you assume that the probabilities are going to remain constant. Okay, let's move on. Okay, now that's the general discrete random variables part of this topic, in which you have to make a probability distribution table, and then you have to find expected value or variance. The next thing is binomial distribution. This is also part of this topic. In this case as well, the variable that you would have, that would be a discrete variable. Now, what is binomial distribution? Let's have a look at this. Let's say you toss a biased coin 6 times. The coin has 0.7 as the probability of heads and 0.3 as the probability of tails. Find the probability of getting 4 heads. Now, how do you find that? 4 heads, you could say, okay, out of 6, we want 4 heads. So we can have 0.7 into 0.7 into 0.7 into 0.7 times 0.3 into 0.3. Right? But if you think of the tree diagram, this is just one possible path on the tree diagram. Head, 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 tail, tail. There could be many other paths on the tree that also give you 4 heads and 2 tails. In such problems, we use binomial distribution formulas. I'll tell you how to identify that in a moment. But so this is actually the logic behind that. I'll just explain that. You can have a look at this if you want. But let's just get to the takeaway from that. This is the formula that we've got for this binomial distribution formula, NCR into P raised to power R into Q raised to power N minus R. If you had to find that probability, we could use this formula to find that probability. Now, how do you understand this formula? What do these different letters represent here? N represents, this number N represents the number of times you are repeating something, number of trials, number of repetitions. That's what N represents. So in binomial distribution, you would have something repeating. So in that case, in the example that I showed you, you were tossing the coin 6 times. So something was repeating. So N in that case would be 6. P is the probability of success and Q is the probability of failure. Now, what's the probability of success? Success is whatever it is that you're finding the probability for. So you're finding the probability of getting heads, right? 4 heads. So heads will say this is a success. This is our criteria for success. Okay. So P is the probability of success. Q is the probability of failure. And then what about X and R? What do they represent? X is the number of successes that you can have. Number of successes. Now, X is a variable that can take different values. For example, in this case, we were tossing 6 coins. The value for X could be 0, that you get 0 heads, or 1 head, 2 heads, 3 heads, 4 heads, 5 heads, up to N. In this case, N was 6. So up to 6 heads. But in general, you would go up to N like this. So X is a variable that can take any value from 0 to N. What about R? R is the number of successes that you want to find the probability for. So for example, in this case, we wanted to find the probability of getting 4 heads. So we would put R equal to 4 here. So basically, it would become probability of X equal to 4. That when the value of X is equal to 4, that means the value of R here is 4. So both of these represent number of successes, X and R. X is a variable that can take all of these values from 0 to N. R is the value that you want to find the probability for. Number of successes you want to find the probability for. Now, how do you use this formula? In that example that I showed you above, the probability of success was 0.7, probability of failure was 0.3, N was equal to 6. All we have to do is just input values in the formula, and that gives us the result. 6E4 into 0.7 raised to power 4 into 0.3 raised to power 6 minus 4. Just input values in this: n equal to 6, p equal to 0.7, q equal to 0.3, and that gives you that probability. That's the probability of getting 4 successes. So in binomial distribution, how do you know something is binomial distribution? The main thing that you would have to do, that you would be doing in binomial distribution would be, you'll be finding probability of getting a certain number of successes. You'll be talking about probability of getting a certain number of successes. So in this case, we wanted 4 successes, right? So you'll be talking about probability of getting a certain number of successes, right? That's what the binomial question would look like. But there's some conditions that also have to be met alongside that. What are those conditions? These are the conditions that we've got. There should be something repeating. There should be repeated trials. But the total number of times you're repeating that should be fixed. The n should be fixed. There should be only 2 possible outcomes. We'll call one of them success and the other failure. Now, it's not necessary it's exactly 2 in the original scenario. You could sometimes convert that to 2 as well. For example, you could have 4 different outcomes, but you want to find the probability of getting one certain outcome. You would call that outcome the success and the rest failure, right? So you can convert that to 2 outcomes sometimes yourself by calling one success and everything else combined as failure. Third condition is independent probabilities. What that means is probabilities of success and failure, they should remain unchanged across all trials. That means if you're repeating something, so if the coin was being tossed 6 times, the probability of heads every single time should be the same and should not be changing, right? The first time, if it was 0.6, 0.7, the second time also it should be 0.7, third time also it should be 0.7. If it changes, then you can't use binomial distribution formula. For using this formula, that has to remain the same. And the fourth is the discrete outcomes, the number of successes that's discrete. That's kind of understood. The first 3 conditions that they are important. Repeated trials where n is fixed, only 2 possible outcomes, and their probabilities should remain constant. And what you would be looking for would be number of successes. X would represent the number of successes. Okay, the variable will represent number of successes. So in binomial, key thing to remember, you'll be talking about number of successes and these conditions should be met. Now, let's have a look at some examples of this. Let's say you roll a fair 4-sided dice. Now, in the formula sheet, by the way, this formula is going to be written like this: n r p raised to power r into 1 minus p raised to power n minus r. Okay. So in case you forget the formula and you want to refer to the formula sheet, just remember, this is what the notation would look like there. Now, this, as you might know from binomial distribution as well, this represents NCR. This is p raised to power r. Q is just 1 minus p, right? So 1 minus p, you can replace that with q if you want to use this notation, and that becomes the formula that we are using here, right? So it's given in the formula sheet in a slightly different way. 1 minus p is the same thing as q, and this is NCR, okay, for binomial distribution. So now let's say if we roll a face 4-sided dice 9 times, the dice has numbers 1, 2, 3, 4 written on its faces. What's the probability of getting a factor of 6 4 times? Now, is that binomial distribution? Can we say it's binomial distribution? Does it satisfy the conditions? We have something repeating. We've got something repeating 9 times. Okay, so that condition is fulfilled. If we have something repeating 9 times, okay, what else? Do we have something that we can call a success? Getting a factor of 6. So we can call this thing a success. The outcome that we want, we call that a success. Okay. So what's the probability of getting a factor of 6? 1, 2, 3, 4. These were the numbers. 1, 2, 3, 4. How many of them are factors of 6? 3 of them. So probability of success is 0.75. Probability of failure is 0.25. So yes, we can convert it to outcomes, even though it was actually 4 outcomes here. But whatever it is that they're asking about, we will call that success and then everything else failure. So probability of success turns out to be 0.75. Failure turns out to be 0.25. Okay, so we've got N, P, and Q. The probabilities are not going to change across trials. What's this probability now? We want to find the probability of getting this success 4 times. So we're talking about number of successes, right? So all conditions for binomial, they are met here. So success is getting a factor of 6, failure not getting a factor of 6 is the opposite of that. use the formula, probability of X equals 4. You want 4 successes. Input values in this, you get the result. That turns out to be this. Now, let's change that slightly. What did they say? What's the probability of getting a factor of 6 less than 2 times? Less than 2 times. So that means probability of X less than 2. Now, for that, you would have to add two probabilities. Less than 2 could be 0 or 1, right? And binomial, you also have to consider 0 because you can have 0 success, right? You have no success. That is a possibility. So less than 2 means either X is equal to 0 or X is equal to 1. You sum these two probabilities and that gives the result. You find both of them individually and then you add them up together and that will give you that result. Okay. Then if they say probability of getting a factor of 6 less than or equal to 6 times. Okay, what does that mean? Probability of X being less than or equal to 6. How many times were you repeating the experiment? 9 times. Less than or equal to 6 means you want all of these cases. You want all of these cases. You want 0, 1, 2, 3, 4, 5, 6. One idea is that you calculate all of them. That will be a lot of working. And you'll have to calculate 7 different probabilities. Now, when you have a case like this, when on one side you have a lot of cases to evaluate, you can do it the other way around. You could say, okay, that's a lot of cases that we'd have to evaluate. Let's consider the opposite of that. 1 minus probability of these 3 outcomes. So 1 minus probability of 7, 8, and 9. Right? So this can be reversed like this. 1 minus probability of X greater than 6. That's 7, 8, and 9. Find these 3 probabilities, subtract them from 1, and that will give you the final result. That turns out to be this. Okay. For in a binomial distribution, for inequalities, we don't have any direct formulas. As we'll see for geometric, we do have one. But for binomial, we don't have any direct formulas. We have to calculate each probability separately and then add them up together like this. Now, in a binomial distribution, we have a direct formula for finding expected value of X, and that's given by n times p. Variance is npq. Again, both of them are given in the formula sheet as well. In the formula sheet, they will use for the expected value, sometimes they'll write mu there. And for variance, they use this notation sigma square. Square root of that is standard deviation. So sigma represents standard deviation. Okay. These are the formulas for binomial distribution for expected value and variance. You could find the mean and variance using a probability distribution table as well, but it's much more efficient in this case to just use these formulas directly, because if you were to make a probability distribution table here, that's 10 possible values in this particular example, 10 possible values of X and then their corresponding probabilities, evaluating XP, sigma XP, that's a lot of effort. That will give you the result eventually. However, if you know it's a binomial distribution, we have a direct formula for that. That's just NP. Just use that to find expected value and then NPQ to find the variance. Okay. Then there's something called parameters of a distribution. These are things that define or describe a binomial distribution. Sometimes they ask you about this in the question directly as well. Write down the parameters of a certain distribution. How would you do that? You would write the value for n in that and the value for p. There are 2 parameters of a binomial distribution. One is n, that represents the number of repetitions, the number of trials, the number of times you're repeating something, and p, that's probability of success. These are 2 parameters of a binomial distribution, right? Not q, because once you know p, q can be found easily from that. So these are the 2 things that you need to be able to describe a binomial distribution. And then this notation, sometimes they use this as well. If you have X and then this tilde, B8, 0.7, this notation, what does it mean? The first number in this notation represents N, the second number in this notation represents P. So you would say this notation, if it's written like this, that means X is binomially distributed, X follows binomial distribution with N equal to 8 and probability of success equal to 0.7. Okay, so you need to know that these are the 2 parameters of a binomial distribution. Also, sometimes they ask you to list down these conditions as well. So you need to make sure that you memorize these conditions, right? So in some questions, they will ask you to just list down the conditions for a binomial distribution, for geometric distribution. You should memorize these. Okay. All right. So that's about binomial distribution. So remember what we were talking about there? Probability of getting a certain number of successes. Now, what about geometric distribution? What about geometric distribution? In geometric distribution, we are not talking about getting a certain number of successes. In geometric distribution, we talk about probability of getting our first success on a particular attempt. Probability of getting the first success on a particular outcome. So in this case, we'll be talking about the first success. Okay. Now, let's look at this example. So we have some match going on in which a team has a probability of winning that is 0.2, and probability of losing that's 0.8. Find the probability that they win. So let's say it's Pakistan. I think at the time of this example, it was World Cup going on. That was our situation. Probability of winning, that was 0.2. Probability of losing, that's 0.8. Find the probability that the first Pakistan win comes in their fourth match. First Pakistan win comes in their fourth match. How do you find that? If the first win comes in their fourth match, that means the first three are losses, right? So if the probability of winning is 0.2, probability of losing would be 0.8. So we can say 0.8 and 0.8 is 0.8 into 0.2. That gives us this. Now, this is actually geometric distribution where we talk about the first success. Where we talk about the first success, and we have this formula for this. We can use this formula directly. Once we know it's a geometric distribution, we'll talk about how to identify that. But once we know it's a geometric distribution, we can just use this formula. Probability of x equals r, that is given by q raised to power r minus 1 times p. Now notice there's no n in this case because the total number of repetitions is not supposed to be fixed in this case, right? It could be anything. So again, p represents probability of success here, q represents probability of failure. X represents the number of attempts or the number of trials, the number of repetitions needed until you get your first success. These are a number of keywords that you will see in such problems. Until something happens, first success, number of attempts until you get your first success. That's geometric distribution. Okay, number of attempts needed to get your first success. R is the value for x that you want the probability for, right? So R also represents number of attempts, but x is a variable that could take all of these values 1, 2, 3, 4, 5, 6, all the way up to infinity. R is the specific value that you want to find the probability for. Let's take an example. So in this case that we saw above, we had to find the probability that the first Pakistan win comes in their fourth match. If we were to use this formula, we could do it like this. Q is 0.8, probability of losing, probability of failure, that's 0.8. 0.8 raised to power 4 minus 1 times p, that's 0.2, and you get the result directly. Okay. Now, let's have a look at some examples in this. In fact, before that, conditions for geometric distribution. Now, these are very similar to binomial distribution with some key differences. Here as well, you've got repeated trials. You need to have something repeating, something happening multiple times over and over again. However, n in this case is not fixed. The number of trials, that is not fixed. In binomial, the number of trials is supposed to be fixed. In geometric, it's not necessarily going to be a fixed value. Okay, in general, it's not fixed. The other conditions are the same. Only two possible outcomes, success and failure, equal probabilities across trials, independent probabilities, they don't change discrete outcomes. The first condition, only that has a difference, that the number of trials is not necessarily fixed. But the key difference is what probability you would be looking for. In binomial distribution, we were looking for the probability of getting a certain number of successes. In geometric, we talk about number of attempts, not number of successes, number of attempts or number of trials or number of repetitions until we get our first success. Okay, so that's the difference. In binomial, we talk about number of successes. And here we talk about first success. Okay, let's take some examples now. So let's say these are the probabilities of winning and losing. Find the probability that the first Pakistan win comes in their sixth match. That's pretty straightforward. This is the formula q raised to power r minus 1 times p. In the formula sheet, it will be written like this: 1 minus p raised to power r minus 1 times p, or maybe p into 1 minus p raised to power r minus 1. It's the same thing. You can replace 1 minus p with q, and you get this formula. In their sixth match, what does that mean? 0.8. raised to power 6 minus 1 times 0.2, and that gives you a result, and that's pretty straightforward. Now, this is very important. In geometric distribution, we can find the inequality probabilities directly as well. In binomial, we could not do that. We had to find each probability separately and then add them up together. In geometric distribution, however, we can have direct formulas that we can use to find probabilities for inequalities. I'll quickly tell you about the logic of it. If you get that, that's great. Otherwise, you have to memorize the formula. In any case, for understanding the detailed logic, again, you can watch the crash course videos related to this. So they're saying the first Pakistan win comes after their seventh match, after the seventh match. What does that mean? The first win comes after the seventh match. So we could write that probability like this. That's x greater than 7. X greater than 7, right? The first win comes after the seventh match. Now, when after the seventh match, that does not mean it comes in the eighth match necessarily. After seventh could be 8th, 9th, 10th, 11th, 12th, all the way up to infinity. We don't know where exactly it's going to be. So greater than 7 means it comes at some point after 7. We don't know where. Okay. Now, think of it like this. Probability that the first win comes after the seventh match, x greater than 7. If you think of it another way, that's the same thing as saying if the first win is coming after the seventh match, that necessarily means that you're losing the first 7 matches. If the first time you're winning is after the seventh match, that's equivalent to saying that the first 7 are all losses. So that's what you can say. You can say, okay, this means the first 7 are all losses. So this probability can be found directly like this. You can say probability of x greater than 7, that is 0.8 raised to power 7, and that's 0.209, and that will give you the result. Alternative would, of course, be that you say, okay, greater than 7, that's the probability that we're looking for. That's a lot of cases, 8, 9, up to infinity. You can't find all of them. So you reverse this. You say, okay, 1 minus probability of x equals 1, 2, 3, 4, 5, 6, 7. And that gives you the result. That is one possibility. You could do that. That is one possibility. But just give me a second. Okay, so one possibility was that we found the probabilities of x equals 1, 2, 3, 4, 5, 6, 7, subtracted them from 1. That's pretty long, but that's doable. You can do that if you want. In this case, notice that we're not considering x equals 0. So in geometric, x equals 0 possibility does not exist because you can't have your first success on 0th attempt. You have to attempt something to get success, right? That's a lesson for life as well in general, that without effort you don't get success, right? So with you can't get success on 0th attempt. That's not possible. But when you talk about binomial, number of successes could be 0 as well. That's possible. But first success cannot come on 0th attempt. You can't have success without attempting. Okay. So in this case, we start from x equals 1 onward. Okay, now this is the direct way of doing this. We say this is equal to 0.8 raised to power 7. And from this, we actually get this direct formula, this general formula that looks like this. Probability of x greater than r, that means probability that the first success comes after r attempts, that is equal to the first r attempts being all failures. So this is a formula that we have now that you will need to remember. It's not given in the formula sheet. For geometric distribution, you will remember this formula: x greater than r, that is equal to q raised to power r. Whenever you have an inequality, you will convert that to this form and then find that probability. Okay, so for geometric, you have to remember this formula: probability of x greater than r, that is equal to q raised to power r. Okay, now let's look at some more examples. Find the probability that the first success comes in or after their seventh match. What does that mean? That's x greater than or equal to 7. Now, the formula that we have is only for greater than, right? It's an inequality. We have the formula for greater than, x greater than r, the probability of that is equal to q raised to power r. Can we convert it to the greater than form somehow? Greater than or equal to 7. If we write those numbers, they are 7, 8, 9, 10, 11, and so on. In greater than form, we could say these numbers are greater than 6 because these are discrete numbers, right? They can only be integers in this particular scenario. So greater than or equal to 7 is the same thing as saying x greater than 6. And that we know is going to be q raised to power 6. And that gives us the final result. That's 0.262, 0.8 raised to power 6. Let's take another example. If it says the first success comes in or before their fifth match. So now less than or equal to 5. Less than or equal to 5. What does that mean? We have the formula that's greater than r. We have formula for greater than something. They want us to find less than or equal to something. So that means we'll have to do 1 minus something, right? 1 minus some expression. What we can do is we can write down the numbers like this. Okay, x less than or equal to 5. That means it could be 1, 2, 3, 4, 5. What are the numbers that we do not want? These are the numbers that we don't want: 6, 7, 8, all the way up to infinity. So we subtract from 1 all of these, probability of all of these numbers. How would you describe them? In greater than form, these numbers written in orange, 6, 7, 8, and so on, you would describe them as x greater than 5. And that's what we know how to find. Probability of x greater than 5 is q raised to power 5. Just input that value here, you get the result from that. First success comes before their fifth match. What does that mean? X is less than 5. Again, we can write down the numbers. What numbers satisfy this condition? 1, 2, 3, 4. So we want 1, 2, 3, 4. What is it that we do not want? We do not want 5, 6, 7, 8, and so on. These are the numbers that we do not want. How would we describe these numbers in greater than form? We can say these numbers that we do not want are greater than 4. So 1 minus probability of x greater than 4, and that gives you the result that turns out to be this. So I would recommend that you just remember this formula, convert everything that you have to this form, and then if you have any inequality form, convert that to x greater than r form, and then use that for this calculation. Okay, so this first formula is going to be given in the formula sheet. This is not going to be given. You have to remember that. There are other formulas as well. If you find it difficult to convert it to this form, then you have these other formulas, which I don't generally recommend remembering because students will often, end up mixing these up. But if you think your memory is very strong and you find it difficult to convert things to this form, then you can just memorize these other forms as well and just use them directly. And that's possible if you think you can memorize this. I can't generally memorize things well, so I prefer using, logic to convert it to this form. But that's your choice now. You can do it both ways. Okay, let's move on. Now for a geometric distribution, we have the expected value formula. The expected value, or the mean of a geometric distribution, is given by 1 over p. Mean of a geometric distribution, or expected value of a geometric distribution, that's given by 1 over p. Okay, that's a formula that, again, that's given in the formula sheet as well. Variance for a geometric distribution is not defined. It's only the mean. Okay. Parameter of a geometric distribution. For binomial, we had two parameters, n and p. For geometric, we only have one parameter that's called p. That's probability of success. And then you have this notation that you need to be familiar with. They write something like this: x and then tilde, GEO, and some number in the bracket. That means x follows geometric distribution with p equal to 0.3. Okay. So that's about geometric distribution. Now let's have a look at a couple of examples, and then not a couple, quite a few examples, and then we end for today. We will do normal distribution and representation of data in the morning tomorrow, inshallah. We'll try to start around 9:30, right? 9:30. We have two topics to go. They're relatively easier ones now. Normal distribution, that requires practice, but once you've done that, the questions are very repetitive. Yes, of course, AM, because some people have their biology exam on Monday. Hopefully, if things get better, inshallah. So we'll have a session tomorrow, inshallah, around 9:30 a.m. in the morning. Let's do 9:30 a.m. Yeah, 9:30 a.m. 9:30 a.m. in the morning. I'll be posting about that in the group as well. 9:30 a.m. The benefit of that would be that you would have the remaining day free for whatever you want to do. If you have any other exam, you can prepare for that, and you'll have time to do anything else after that. If you do it tomorrow night, then you'll waste the whole day before, and then you'll spend time in this, and that's not going to be very beneficial. Okay, so let me just leave this here, although it's not much different, but let me give you options: 9:30 or 10. So you can write 9:30 or 10 in the chat. Those of you who prefer 9:30, write 9:30. Otherwise, write 10. All of you respond. Shafi, are you okay? Oh, acha, you were saying to my son. I thought somebody else was writing on your behalf there. Some kid who got hold of your computer. Ibrahim. His name is Ibrahim. 10. Okay. So let's do 10. Let's do 10 tomorrow. Let's do 10 a.m. tomorrow. And we will be doing... We'll be doing normal distribution. We'll be doing normal distribution and what? Representation of data. So that's going to take around 2.5 hours, I think, in total. 2.5 hours. So 10 to 12:30. Keep that in mind. Okay, that's for tomorrow. But let's complete this. Let's do some examples of this now, of binomial and geometric. So sometimes you end up getting some pretty complicated questions on this. This is one very complicated one. Okay. Probability that Sue completes a Sudoku puzzle correctly is 0.75. Sue attempts n Sudoku puzzles. Find the least value of n, for which the probability that she completes all n puzzles correctly is less than 0.06. Now, what does that mean? So this is one of the more difficult questions that you'll find in binomial distribution. So she's solving Sudoku puzzles. For any one puzzle, the probability that she gets that correct is 0.75. Okay. Now she attempts n puzzles. Find the least value of n, for which the probability that she completes all n puzzles correctly is less than 0.06. Now, how do you think about this? First of all, let's talk about this probability. Probability that she completes all n puzzles correctly. What would that be? It's a binomial distribution. Something is happening repeatedly. She's solving puzzles. Probability of success is 0.75 for every puzzle, so that remains constant. The total number is fixed, that is n. So we can say probability of getting all n puzzles correctly, what would that be? Probability of x equals n. That's NCN into 0.75 raised to power n and into 0.25 raised to power n minus n, right? Let's simplify this. Simplify this and see what that gives us. NCN, that is 1. So for example, 6C6 is 1, 4C4 is 1, 2C2 is 1, right? NCN is going to be 1. So that leaves us with just 0.75 raised to power n. This is the probability that we're getting. Now they're saying this probability is less than 0.06, less than 0.06, okay? So we say this is less than 0.06, we put that less than 0.06, then find the value of n from this. Those of you who have done paper 3, you could use logs in this, take log on both sides, use the power law, divide this on the other side. But when you divide this, be careful. Log of numbers between 0 and 1, that is less than, that is negative. So you have to be careful when you divide this on the other side. I would recommend in inequalities, first evaluate this number so that you can clearly see that it's a negative number here. So when you divide it on the other side, the inequality sign would flip. Right, the inequality sign would flip when you divide it on the other side. Now, using logs, you get n greater than 9.78. The least value of n, what's that? The least value of n turns out to be least value of n turns out to be 10 because it has to be an integer. N represents the number of times you're repeating something. So that's an integer that turns out to be 10. Okay. Now, those of you who do not know logs, what you would do would be, if you have not done paper 3, if you're an AS, in that case, again, you would write this inequality like this: 0.75 raised to power n, that is less than 0.06. And you would find this using trial and error. Okay, find the value of n, the least value of n, using trial and error. How would that work? Input some value of n here. For example, I input 5 here. When I input 5 in place of n, I get 0.237. Is that less than 0.6? It's not. So we try a bigger value. We can try a 10, for instance. When you try 10, we get 0.056. Okay, now is that less than 0.06? Yes, that is less than 0.06. But is that the first value that gives us something less than 0.06? So we can try 9 as well. That's 0.075. So now that means at 0.075, at n equal to 9, we're getting 0.075, which is still bigger than 0.06. At n equals 10, we get a number that's less than 0.06. So the least value of n that we are looking for, that is equal to 10, and we can write it like this. So without using logs, you can use trial and error as well. If you're an AS and you don't know logs, then you can do it like this as well. Okay, and that will give the value of n. So sometimes we make inequalities like this to find this. Now, I want to focus on the last part here. You can look at the second part. Let me just go to the second part as well. It says, find the value of x that has the highest probability, given that Sue attempts 14 puzzles every month. Okay, so every month she's attempting 14 puzzles now. And the number that she completes successfully is denoted by x. Find the value of x that has the highest probability. So we have all of these possible values of x, 0, 1, 2, 3, 4, all the way up to 14. How do you find the value of x that has the highest probability? Do we find all of these probabilities? That will be too much work. They've given us a hint, and that's actually true in general as well. In a binomial distribution, probabilities are going to be higher close to the mean. Close to the mean, the probabilities are going to be higher. So they have told us about this as well. You may assume that this value is one of the two values closest to the mean of x. What that means is we can find the mean of this distribution. It's a binomial distribution in which the value for n is 14, the value for p is 0.75, q is 0.25. We can find the mean of this binomial. Mean is given by n times p. That turns out to be 10.5. The two values closest to 10.5, they are 10 and 11. We can find the probabilities of 10 and 11, and they turn out to be these two. It's bigger for x equals 11. So we say that's our final answer, x equals 11. That has the highest probability. That's what we were looking for. Now, third part again is fairly complicated. It says, find the probability. So understand the situation. She's solving 14 puzzles every month now. Find the probability that in exactly 3 of the next 5 months. So now they're talking about 5 months. They were talking about 1 month earlier. In every month, she was attempting 14 puzzles. And then We're talking about 5 months. Out of those 5 months, find the probability that in exactly 3 of the next 5 months, she completes more than 11 Sudoku puzzles correctly. So we're talking about two binomial distributions here. Two binomial distributions. So one thing is that she's solving multiple puzzles every month. So that's one binomial, right? She's repeating that process of solving Sudoku puzzles every single month. But then we're talking about months. We're talking about 5 months. So we have 5 months in total. And we want 3 successes out of that. Okay, so let me show that to you here. So we've got one binomial that is in every month she's solving 14 puzzles. Okay. N equals 14. And we have another binomial in which we're talking about 5 months. What's the criteria of a month being successful? Sue completes more than 11 Sudoku puzzles correctly in that month. So if in a month, we're talking about the case in which in a month, she solves more than 11 puzzles correctly out of 14. So that's the criteria for success of this outer binomial. So what we want to do first of all is we want to find the probability that she solves more than 11 puzzles correctly in 1 month. How can we find that? That's this binomial where n is equal to 14, probability of success is 0.75, probability of failure is 0.25, probability of x greater than 11. That's 12, 13, 14. Find each of these probabilities, add them up together, that turns out to be 0.2811. So this is the probability that in one given month, she solves more than 11 puzzles correctly. And then we have the other binomial, n equals 5. We're talking about months here. A month is considered successful if she solves more than 11 puzzles. So what's the criteria for success here? This probability, that's 0.2811. What about the failure then? 1 minus that. That gives us this. We've got another binomial here. We want the probability of having exactly 3 successes. So exactly 3 out of 5 successes. Just input values in this. X equals 3, input the values, 5c3, p raised to power 3, q raised to power 2, and that gives you the result. That's 0.115. So this is what happens sometimes as well. That's the more complicated type of binomial distribution question in which you have one binomial, that's the outer binomial, and to find the probability of success for that, you have to use another binomial. Okay, so probability of success for this comes from that other binomial distribution. Now this happens with 2 binomials, as in you have one binomial, probability of success of that comes from another binomial. This happens with binomial and geometric. You have one binomial distribution, probability of success for that comes from a geometric distribution. It happens in normal as well, that you have a binomial distribution outside, and the probability of success for that comes from a normal distribution, right? So binomial distribution would be the outer distribution, and for finding the probability of success for that, you would sometimes have to use either binomial, geometric, or normal, depending on the situation. So let's have a look at this example. Ramesh throws an ordinary face 6-sided dice. Find the probability that he obtains a 4 for the first time on his 8th throw. What does that mean? We're talking about first success. What's the criteria for success? Obtaining a 4. He obtains a 4 for the first time on his 8th throw. Okay. What kind of distribution is that? That's geometric distribution. We're talking about first success. It's a fair dice. Probabilities remain constant. They do not change. First success coming on the 8th throw, we could say probability of x equals 8. The formula is q raised to power r minus 1 times p. Just input values in that and you get the result. Find the probability that it takes no more than 5 throws for Ramesh to obtain a 4. No more than 5. How do you write that? No more than 5. 5 is possible. less than that is possible, greater than that is not possible. So we say that's x less than or equal to 5. Now that's an inequality. It's a geometric distribution. Again, because we're talking about first success, obtaining a 4. Probability of a 4 is 1/6 as before. We have this inequality formula. X greater than r, probability of that is q raised to power r. You can convert that to this form. As we did before, 1 minus probability of x greater than 5. That becomes 1 minus q raised to power 5, and that gives us the result. Now, the third part, that's important. It says, Ramesh now repeatedly throws two ordinary fair six-sided dice at the same time. Each time he adds the two numbers that he obtains. Okay. So now he's throwing two dice and he's adding the numbers that he's obtaining for 10 randomly chosen throws of two dice. So now we know that we are throwing the dice 10 times, two dice 10 times. Find the probability that Ramesh obtains a total of less than 4 on 3 occasions, on at least 3 occasions. Okay, now how do we understand that? Total of less than 4. Let's first of all focus on that. That's the outcome that we want, right? Obtain a total of less than 4. Can we find the probability of that first of all? Obtaining a total of less than 4? We're throwing two dice. Less than 4 total is possible with 1, 1, 1, 2, 2, 1. These are the only three cases. Out of how many? 36. 3 out of 36. That's the probability of success. And probability of failure is this. What we want now is that Ramesh obtains at least 3 successes. At least 3 successes. What's that? We're talking about probability of having a certain number of successes. That's binomial distribution now. N equals 10. That was the number of times we were repeating the experiment. This is the formula that we've got for this. All we have to do is input values in the formula greater than or equal to 3. That's a lot of cases, 3, 4, 5, 6, 7, 8, 9, 10. We flip that. We say, okay, subtract from 1, x less than 3. That means 0, 1, 2. Find these probabilities and subtract them from 1, and that will give the result. Let's take another example. Let's say you've got this. An ordinary fair die is thrown repeatedly until a 5 is obtained. The number of throws taken is denoted by the random variable x. Write down the mean of x. Again, what does this represent? It's a geometric distribution. We're doing something repeatedly until we get our first success, until we get a 5. That's the criteria for success. That's a geometric distribution. For a geometric distribution, the mean is given by 1/p. Probability of 5 is 1/6. So 1/1/6, that becomes 6, right? Probability that 5 is first obtained after the third throw, but before the 8th throw. What does that mean? After the third, but before the 8th. That means it could be 4, 5, 6, or 7. Right? After the third, that means 4th, 5th, 6th, or 7th. These are the 4 cases that are possible. One idea is that you find each of them individually and then add them up together using geometric distribution formula. That works perfectly fine. That's the result that you get from this. But what if they said it's obtained after the third throw, but before the 18th throw? What about that? That will be too much calculation to do in that case then. So we need some direct way of doing this as well. How can we do that? Using that inequality formula, we know that probability of x greater than r is equal to q raised to power r. So can we somehow write this in greater than form? Let's think of it this way. These are the numbers that we want, 4, 5, 6, 7. Can we get them in greater than form somehow? We could say, let's write down more numbers after that, 8, 9, 10, 11, and so on. All of these numbers from 4 onward, they are greater than 3. So we can find the probability of all numbers that are greater than 3. So all of these numbers, and then subtract from that the probability of these numbers. And that would leave us with these yellow shaded numbers. How do I do that? Probability of x greater than 3. X greater than 3. That will give you the probability of all of these numbers up from 4 up to infinity. Subtract from that the probability of these numbers in the middle from 8 onward. So not in the middle, from 8 onward on the right side. How would you describe them in greater than form? Greater than 7. So the final result, what does that turn out to be? X greater than 3, probability of that minus the probability of x greater than 7. And you can do this directly. Q raised to power 3 minus q raised to power 7, and that will give the same result as well. Okay, I would recommend that you understand this well, because if this difference was bigger, then doing it individually for each number would be too long. Okay, and the last part is fairly straightforward. Probability of success, of first success coming before the 10th throw. So x less than 10, we can replace that with 1 minus x greater than 9. Again, by writing down numbers like this, less than 10 means we want all the numbers from 9 and 9 and before. We want all the numbers. 10 minutes और लग सकते हैं बात में जाना Okay, so we have these numbers from 1 to 9 that we want. What are the numbers that we do not want? From 10 onward, how do you describe them? Greater than 9. So you can say 1 minus probability of x greater than 9, right? And let's just input values in the formula. Okay, so we're almost done. Just 3 more examples. Let's start with them quickly. Okay, so again, another example. The probability in a certain region, probability that on any given day, probability that any given day in October is wet as 0.16. Find the probability that in a 10-day period, fewer than 3 days will be wet. Fewer than 3 successes, that's binomial. So we say n is equal to 10, p is this, q is this. Less than 3 means 0 and 2 probabilities, add them up together, and that gives the result. In binomial, we don't have an inequality formula. You have to calculate each of them separately and then do it. Second part, the first wet day in October is 8th October. We're talking about first success. That's geometric. So we use geometric distribution with x equal to 8. That means 0.84 raised to power 7 into 0.16, and that gives us the result. Now, the last part, that's very important. For 4 randomly chosen years, we're talking about 4 years, find the probability that in exactly one of these years, the first wet day in October is 8th October. What's the outcome that we're talking about? First wet day in October is 8th October. We've already found the probability of that in the first part. And the second part, that was 0.0472. So now what we have is years, we want that we have exactly one success out of those 4 years. That's binomial distribution. N equals 4. We want one success out of 4. Probability of success is going to come from the previous part. That's 0.047. It will be 1 minus that. And then with n equal to 4, apply the binomial distribution formula. X probability of x equals 1, that gives you this. That turns out to be 0.116. That's your final answer. This is actually a binomial distribution. And inside that, you have a geometric distribution, right? Because this probability of success, that combine these two parts as well. They could skip the second part. They could just skip the second part and just ask you to do this third part directly. In that case, you would first have to find this probability. That would be the probability of success in the next part. Okay, sometimes you may have to do it by yourself as well. In this case, it becomes easier because they made you find that probability first, and then you start to use that in the next part afterwards. Okay, then another type of question that you'll see in recent papers, I'll skip the other parts. You can just have a look at them. They're fairly straightforward. Rajesh applies once every year for a ticket. The probability that he's successful is 0.3, independently of the other years. Find the probability that Rajesh is successful for the second time on his 10th attempt. He is successful for the second time on his 10th attempt. Now, we're not talking about first success. We're talking about second success. Now, that's not geometric. That's not geometric. This geometric talks about first success. This is second success. Okay, now how can we think about this? You can think of it like this, that okay, the second success comes on the 10th attempt. That means we know for sure this 10th attempt, it has to be a success, right? That's a given because there's a success in that. Now, if it is a second success, what that means is in the first 9 years, in these 9 years, there should be one other success so that the 10th one becomes the second one. Okay. So the 10th has to be a success. And amongst the first 9, we want one more success. Now, for the first 9, we can think of it as a binomial distribution. We can say, okay, we've got 9 repetitions. Probability of success is 0.3. Probability of failure is 0.7. Out of these 9, we want one success. We want one success. Okay. Out of these 9, we want exactly one success. How do you find that? N is 9, P is 0.3, Q is 0.7, P equals the probability of X equals 1 using the binomial formula. That gives us the probability of getting exactly one success in the first 9 attempts. So we have one success in the first 9 attempts, and the 10th is also a success. So we multiply this by 0.3 probability of success for the 10th attempt, and that gives us the final result. Okay, what about now? Can you see it now? Okay, so were you able to understand the previous question? Did it work and fine until that point? Okay, all right. Let's do this one last example quickly and then we end. I know it's very late now. In a game, players attempt to score a goal by kicking a ball into a net. The probability that Leno scores a goal is 0.4 in any attempt, independently of all other attempts. The random variable x denotes the number of attempts that it takes him to score a goal. So any one attempt, 0.4 is the probability of success. Okay. X represents the number of attempts that it takes him to score a goal. Find the probability that he scores his second goal on or before his 5th attempt. Second goal on or before his 5th attempt. So in the previous example, it was on a certain attempt. Now they're saying on or before the 5th attempt. How do you think about this now? You have to make multiple cases for this now. If the second goal comes on or before his 5th attempt, what are the possible cases? We've got these 5 attempts, let's say 1, 2, 3, 4, 5. Okay, these are the 5 attempts. There are multiple cases. Number 1 could be that the second success comes on the second attempt, third attempt, the other case, another case, 4th attempt, another case, 5th attempt. These are 4 different cases that we get from this. In the first case, that just means the first is also a success, and the first and second both are successes. That's 0.4 into 0.4, and that will give you something. In the second case, this is a success, but this is a second success. That means there has to be another success amongst the first 2 attempts. So we can consider the first 2 as a binomial. It's a binomial with n equal to 2, and probability of x equal to 1. That's what we have to figure out. What would that be? Probability of success is 0.4 as before. 2c1 into 0.4 into 0.6 times 0.4 for the second success on the third attempt. Then the next case, similarly. This is the second success. That's what the 0.4 is for. And then from the first 3 attempts, we want one success. So that's a binomial with n equal to 3. And we want to find probability of x equal to 1 in that. That's 3c1 into 0.4 into 0.6 squared. Okay. And then finally, the second success comes on the 5th attempt. If it comes on the 5th attempt, the second success, again, for that success, we've got 0.4 here at the end. But then before that, if this is the second success, we want one more success in the first 4 attempts. We want one more success in the first 4 attempts. So n equals 4 there, probability of x equals 1. That becomes 4c1 into 0.4 into 0.6 cubed. These are 4 different cases, add them up all together, and that gives us the total result. That's 0.663. And that's your final answer. So sometimes it can be as complicated as this as well. Let me know if there are any questions now. That was a very, very long session, but I hope that was helpful. We went through a lot of different examples, a lot of different cases. If there's any question now, let me know. We could discuss that. Okay, for everyone. All right, okay, on it. Okay, so this is the next topic that we're doing, normal distribution. So in the last topic, we talked about discrete variables and continuous variables, binomial and geometric distributions. Both of them were discrete distributions, right? The variable could only take integer values in that case. But now, normal distribution is a continuous distribution. The variable that you would have in this case, it can take any real value, right? So any decimal values are also going to be possible in this case. Now, for normal distribution, this is the first thing that you need to know about. It's a continuous distribution, and it's described by its mean and variance. For describing a normal distribution, you need 2 things. Number 1, the mean, and number 2, the variance. Okay. Now, this is the notation that is used here. For mean, we use mu. For variance, we use sigma square. If you have something written like this, x and then tilde, and then you have n, 15, 25. What does this represent? Inside the brackets, the first number would represent the mean, and the second number would represent the variance. Okay, so this notation, n, 15, 25, what that means is x follows normal distribution with mean equal to 15 and variance equal to 25. Now, in this notation, this number represents variance. That's very important to remember. But in our calculations, as you will see, we will be using standard deviation. So standard deviation is square root of variance. If variance is 25, standard deviation is going to be 5. You just take square root of that, and you get the standard deviation from that. Okay. Now, we will be using this normal distribution curve to find probabilities. Now, again, the idea is we will have some situation given, and we would have to find some probabilities using that. In geometric and binomial, we had some formulas that we used to use to find probabilities. In this case, we will be using area under a curve to find probabilities. Okay. Now, this is what the normal distribution curve looks like. It's also called the bell curve. It's a symmetric curve. The area under this curve represents probability. Area under this curve represents probability. Now, the total area is going to be 1, of course, because total probability is 1. It's a symmetric curve, so if you break it in the middle like this, the area on the right side and the area on the left side, they're both 0.5. And in the middle, you have the mean of the distribution. Okay, so the distribution is symmetric about the mean. So when it's perfectly normal, yes, mean and median are going to be the same in this case, if it's a perfectly normal distribution. As you go close to the mean, the probabilities are bigger. So you have more area under the curve close to the mean. As you go far away from the mean, the probabilities become smaller because there's less area under the graph. Okay, and in the middle, there's more area under the graph. As you go far, there's less area under the graph. Now, how do you find this area under the graph? Actually, this area is found using integration, as in the logic behind that is this integration is quite complicated. So what we have in the exam is that they give us a table that we will be using to find these areas. Okay, we'll talk about how to use that table, but the idea would be, let's say you've got a variable like this. It's a variable x. It represents test scores of some students. Okay, so remember, it's supposed to be a continuous variable. So you can have any decimal value in this case as well. If it's a normal distribution, any decimal values are also possible. Now, in this case, let's suppose we have this data about a test in a class. The mean of the whole class is 60 and the standard deviation is, let's say, 12. Okay. Now, if we had to find the probability, for instance, that somebody got a test score of less than 60. Now, 60 was the mean. So 60 would be exactly in the middle of this normal distribution curve. So less than 60, what would that area be? That would be 0.5. Okay. However, if it was something else, for example, x less than 70, we could say this number is 70. We're looking for all of this area towards the left of 70. Now, that is something that we can't really, find directly like this. There will be a process that we use for this. We'll talk about that. How to find, for example, probability of x less than 70. We'll talk about that in a minute. But in normal distribution, you need to understand less than something or less than equal to something, they're both the same thing. Greater than or greater than equal to something, they're both the same thing. Equal to does not make any difference. Equal to does not make any difference in normal distribution. In discrete distributions like binomial and geometric, these two would have different meanings. In normal distribution, they're both the same. Why? Because probability of the variable being equal to any particular value is actually 0. Because if you find the probability of x equals, let's say, 65 or 40, where will 40 be? 40 will be somewhere here on the left side. Let's say this is the point 40. Now, probabilities area under the graph, this is just a point. What's the area under a point? There's no area under a point. Under a point, there's just one line. There's no area there, right? Another way to think about this is in continuous distribution, since the value can be any decimal value, when you say something like this, probability of x equals 40, what it actually means is somebody has a score that's exactly like this, 40.00000. Now, in test scores, it might not make a lot of sense, but think of some other variable, for example, height of a person. So what's the probability of somebody having a height that is exactly, let's say, 5.5 feet? So exactly 5.5 feet means it should be 5.500000000, and then infinitely many zeros like this. It's very unlikely that somebody has a height that's exactly 5.5 to the dot, and there's no, even a 1 after a billion decimal places. It's very, unlikely, right? So in this case, we say probability of something being exactly equal to some value in normal distribution, that's going to be 0. So we would not generally be finding probabilities at a particular point. We will always be finding probabilities for an interval in this case, right? So less than something, greater than something, between two values. We will not be talking about these probabilities because they will be equal to each other. But why are they important? Because you need to understand that these two are the same thing. They don't have any difference. Now, how do you find this probability? Probability that x is less than 70, for instance. How do you use this curve to find this area? Let's understand that. Now, for this, we have something that we call the standard normal distribution, okay, that we will be using to find these areas. Now, finding these areas is, as I said, done using integration, but that integration is pretty complicated. So you have the results from this integration given in the form of a table. Now, before we move on to this, let's go and understand how to read values from a table. So you'll be using a table, and that table represents areas of a normal distribution like this. It's called a standard normal distribution. A standard normal distribution is one in which the mean is 0, variance is 1, and standard deviation is also 1. So there's a standard normal distribution, which we also call Z distribution. It's a distribution such that the mean is 0 and the standard deviation and variance, they're both equal to 1. So what we would do would be, whatever distribution we have, we would be converting that to a standard normal distribution and then use that to find values from the table. Now, how will that work? Let's understand it using this table. Let's understand first of all how to read the table. Okay, so you'll have a table that looks something like this. These highlighted regions that you see, let me just get rid of this quickly first. Okay, so these highlighted row and column that you see, the first column and this first row, they represent z values. They represent the z value. Okay. Now, the blue line that you see, the blue column that you see, it represents the unit place and the first decimal place for the z value. 0 0.1, 0 0.0, 0 0.1, and so on. This yellow part on top, that represents the second decimal place, and the green part here represents the third decimal place. Okay. Now, for example, if there's a z value, of 2.4, where is 2.4? This is 2.4. These values here, the unshaded part, this represents probability. So you'll have a z value and you would have probability corresponding to that. So let's say there is a z value of 2.4. How do you find the corresponding probability value from this? This is the z value. This number that you see, that's the probability. That's 0.9918. Probability corresponding to this would be 0.9918. Okay. And similarly, if you had more decimal places, for example, if you had a z value of 1.34, let's say, z value of 1.34, what will be the probability corresponding to that? 1.3 is going to be found in this region. This is 1.3. And then 4, that's here. You would come down here, go to the right here. This is the value that corresponds to that. And the probability value that you get from that is 0.9099. So when you have two decimal places, you can just do it like this. Read the first decimal from here, second from here, and you get the result from that. In your formula sheet, it's not going to be shaded like this. So you need to remember that this first column represents first decimal, this represents second, and the green part represents the third decimal place. Okay, now if you had 3 decimal values in z, for example, if you had 0.675, what's the corresponding probability value for that? You'll find 0.6 here, you'll find 7 here. That gives you 0.7486, but then there's a third decimal place there as well, and that is 5. That's here. You say add 16. So this says add here, right? Add means 0.7486. That's the value that you get from there. To the last 2 decimal places, add 16. And that will become 0.7502. Now, you can do it mentally, and that's perfectly okay. If you find it difficult to do it mentally, on your calculator, put something like this. Without the decimal, input this on your calculator. 7486 plus 16, and that will give you 7502. And then what you can do is you can just put a decimal in the beginning, and that will be the probability. Okay, so that's how you find probability values using z values. It could be 1 decimal, 2 decimals, 3 decimals. All right. Now, when you're doing calculations, you will see sometimes you will have z values that have more decimal places like this, 0.66667. Now, in the table, the z values are rounded off to 3 decimal places. So before you read the table, you should round them off to 3 decimals and then read the value from the table. Okay, now there's a problem. And the problem is this z value that you see here, these probabilities that you're given here, they're only given for one specific case. And you can see that in all of these expressions that I wrote here, I wrote z less than this value, z less than this value, z less than this value, right? So the table only gives you probability values for one specific case. And what is that specific case? It's when you have something like this. There's a positive z value, and you're finding the area to the left side of that. So in all of these cases that you saw here, z less than a positive value, z less than a positive value, z less than a positive value. This is the only form for which the table gives you the area, right? So less than 2.4, less than 1.34, less than 0.675, all of these values are positive, and we're considering area to the left side of them. To be able to use this table, you need a form that looks like this, z less than a positive value. Okay, this is the only form for which the table can be used. If this is not the form that you have, then the table cannot be used. Okay, so table is only used for this particular form, z less than a positive number. And it's shown here using this graph as well that you will get in the exam. In the formula sheet, you have this graph given, and that tells you that you're looking at the left side of a positive value. Okay, so that's how you read this table. Now, once we understand how to read the table, let's go back there and understand how to find those probabilities. Now, remember that table that you're given, that is only for this one standard distribution where mean is 0 and standard deviation and variance they are 1. Now, you could have many different types of data sets in which the mean could be anything, the standard deviation could be anything. The table is only for one specific case where the mean is 0 and the standard deviation is 1. So what you have to do is, whatever is the data that you're given, for example, in this case, the mean is 60, and the standard deviation is 12. Whatever data you're given, you would first have to convert that to a standard normal distribution. You'll have to make the mean equal to 0, and you'll have to make the standard deviation equal to 1 somehow. Now, how is that done? That is done using this formula, z equals x minus mu over sigma. It's not given in the formula sheet. You need to memorize this. Z equals x minus mu over sigma. What this formula does is, whatever value you give to it, it subtracts mean from that, and it divides by the standard deviation. What that does is, it converts the mean of the distribution. To 0 and standard deviation to 1. So whatever value of x you have, for example, if you have a data like this, these are x values. You convert them to z values. How? By inputting in that formula. For example, if x is 48, you would say z is going to be 48 minus the mean, that's 60, divided by standard deviation, which is 12, and that gives you -1. That's the z value that you get corresponding to 48. And similarly, for all of those values, you find the corresponding z values. Okay, so that's how you convert something to z. And now, if you were to find the mean of all of these values, standard deviation of all of these values, you would see, if you had all of these values written down here, the mean would turn out to be 0 and the standard deviation would turn out to be 1. And then we could use that normal distribution table. Now, this is important. We'll talk about this later again as well. Z value, what does it represent? The Z value represents the number of standard deviations a particular value of x is away from the mean. This understanding is very important. It will make some questions later on, as we'll see, much more efficient and much more easier when they talk about number of standard deviations of values away from the mean. We could use the Z value directly. If we have this understanding of Z value, what does Z value represent? Z represents the number of standard deviations of value of x is above or below the mean. For example, look at this value, 84. Mean was 60. 84 is 2 times the standard deviation above the mean, right? Because standard deviation was 12. So if you add 24 to the mean, you get 84. So the Z value, see, that turns out to be 2 because it is 2 standard deviations above the mean. Similarly, if you look at 48, this is 1 standard deviation below the mean. 60 minus 12, that is 48. So 1 standard deviation below, you can see the Z value that you're getting for this is -1. Okay, similarly, another value, for example, you've got 78 here. 78 is 60 plus 1.5 times the standard deviation. So this is 1.5 standard deviations above the mean. The Z value turns out to be 1.5. So these values of Z, they are representing the number of standard deviations you are away from the mean. The number of standard deviations are above or below the mean. If you're above the mean, the Z value would be positive. If you're below the mean, the Z value would be negative. Now, keep that in mind. We'll refer back to this later on when we look at some of the more difficult questions later on. But that's the idea. Okay, so the idea is whatever x values we're given, we convert them to z first of all to find probabilities. Now, how exactly are we going to find those probabilities? Let's consider this example. So we had that data that I showed you earlier. The mean of that data was 60 and the standard deviation of that data was 12. Okay, let's suppose we wanted to find probability of x being less than 60. Probability of x being less than 60. As we saw earlier, we could not do that directly from just looking at the diagram. How do you find this area? Now, to be able to use that table to find the area, what we do is, we first of all convert it to z. How do we do that? Using that formula, z equals x minus mu over sigma. Okay, whatever value of x we are given, what we do is, we convert that to z first of all. So 70 minus the mean divided by standard deviation. And that gives us the corresponding z value. That gives us corresponding z value. In this case, that turns out to be 0.833. So the original distribution looked like this, with 60 as the mean, and we had to find the area to the left of 70. What we do is we convert that to the z distribution such that the mean is 0, and we say in the x distribution, this area to the left of 70, that corresponds to the area to the left of 0.833 in the z distribution. Okay. So what we do is we find the corresponding z value from that. And now this is something that we can find from the table. You have to make sure that you round this to 3 decimal places, first of all, before you can read the table. And now this is z less than 0.833. This is the standard form. We can go to the table, read that value of z, read the probability value corresponding to this value of z, and that will turn out to be 0.7975. And that's the final probability that we were looking for here. Okay. Now, this was the standard case. This was the standard case where you had z less than a positive number. But a lot of times we would not have that. For the table, we need this form z less than a positive number. Otherwise, we cannot use the table. What if it was some other form? For example, if you had to find probability of x greater than 90, same data, mean 60, standard deviation 12, you would convert it to z first of all. So it becomes 90 minus 60 divided by 12. And that gives you that z is greater than 2.5. Z is greater than 2.5. Now, that's not the standard form. The standard form is z less than a positive number. That's the only form for which we can use the table. Now, how do we think about this? We can draw a normal distribution curve. We can say, okay, z is greater than 2.5. What does that mean? 0 is going to be in the middle. 2.5 is on the right side. We want this yellow region to the right of 2.5. That's the area that we're looking for. That's the area that we're looking for to the right of 2.5 there, right? That's the area that we want. However, the table cannot give us that area. The table cannot give us area to the right of some value. It can only give us area to the left side of a positive value. So what we do is we say, okay, the total area under the curve is 1. If we subtract from 1 the area to the left of this value, isn't that going to be the same? So total is 1. We can subtract from 1 all of this region on the left side. And that will give us that yellow region. So we could write that probability like this. We could say z greater than 2.5 is the same thing as saying 1 minus probability of z less than 2.5. Okay. And now this is the standard form. We can use the table for this. Go to the table, find the probability value corresponding to 2.5, and that will give you the result. 1 minus that, that's the final probability that you get from this. Okay. Now, similarly, you'll have a number of different cases that you could have for finding probability here. So we started with x less than a positive value, z less than a positive value. This is z greater than a positive value. We convert it to this form, 1 minus that. Okay. But then there are a number of other cases that you will have to think about using the same normal distribution curve. Let's quickly go through those cases. Another possibility could be that you're finding probability of x greater than 54. Now, if you convert that to z, that ends up giving you z greater than a negative value. Z greater than a negative value. So that's z greater than minus 0.5. If you look at a normal distribution curve, 0 is in the middle. Greater than minus 0.5, what that means is you're considering the region to the right of minus 0.5. Now, is that the standard form? Is that the standard form? It's not the standard form, right? The standard form is z less than a positive number. So when we have negative numbers like this, what we generally do in single-sided intervals and one-sided intervals like this is that we flip our diagram. Flip the diagram, what does that mean? Reflect this about the center, about the mean, so that it becomes something like this. So you reflect that and you get this lower diagram. So the area to the right of minus 0.5, that's the same thing as saying, if you flip the diagram, the area to the left of 0.5, so you flip it like this. So you can say, okay, this area, z greater than minus 0.5 is the same thing as probability of z less than 0.5. And now that is the standard form. That's something that you can use the table for. You'll go to the table, find the probability value corresponding to 0.5, and that will give you the result. Okay. So when you have negative values like this, you can flip your diagram. What about this? Z less than a positive number, that's the standard form that we want. What if we end up getting Z less than minus 0.65? Again, that's not the standard form. It's Z less than a negative number. We cannot use the table for this. So what do? We say, okay, area to the left of minus 0.65. That's what we're looking for. Now that's on the left side. It's a negative value. The first thing we do is we flip this. Okay, we flip this and we say that area is the same thing as this area. Area to the right of 0.65, right? This yellow region, that will be the same as well using the symmetry of the curve. So that's the first step that we could do. We could say, let's convert it to this form. That's the same thing as Z greater than 0.65. Do not think of this in terms of inequalities that we're multiplying the inequality by a negative number and the inequality sign reverses. No, that's not what we are doing here. In that case, the Z would also become negative, right? We're not thinking about inequalities here. Do not think of it that way. Always think of the graph. Think of the graph. Think about the area under the graph. The area under the graph here is the same as the area under the graph here. So that's why we can write this form like this. So Z greater than 0.65. But now it's still not the standard form. So what we can do now is we can say, okay, the total area is 1. Subtract from 1 the area to the left of 0.65. And that will give us that yellow region. And that is something that we can find from the table now. Z less than 0.65. We can find this number from the table, subtract that from 1, and that gives us the probability. Okay, so that's what we do for one-sided intervals. For negative values, we flip them first, and then we do that calculation. Sometimes you'll have intervals like this. So for example, Z could be between 1.3 and 2.1, let's say. Now, in this case, how do you find this area? Between 1.3 and 2.1, what that means is, you've got 1.3 value and 2.1, both of them are positive values. Both of them will be on the right side of the normal distribution curve, right side of the mean. You've got 1.3 here, you've got 2.1 here. We want Z to be between these values. So we're looking for this shaded region. This is the area that we're looking for. How can we find that? Remember, the standard form is Z less than a positive number. That's the form for which we can use the table. So what we do is we say, let's find the area to the left of 2.1. Area to the left of 2.1, all of this area. Okay, subtract from that area to the left of 1.3, and that would leave you with the shaded region that you've got here. So that's what we can do. We can say this area, again, do not think of inequalities. Do not think of inequalities. We're thinking of the area on the graph. On the graph, the area to the left side of 2.1, if you subtract from that area to the left of 1.3, you will get this area in the middle. Okay. And now both of these are standard forms. Z less than 2.1, you can find this from the table. Z less than 1.3, you can find this from the table. Find those two probabilities, find their difference, and you get the result. What if you have negative values in the interval? So if you have minus 1.5 and minus 0.3, if both of them are negative, what we do is, no, we don't have to subtract from one anywhere here. Both of them are positive, right? Z less than a positive number, Z less than a positive number. We don't have to subtract anything from one. These are both standard forms. We just find them directly from the table. These are direct values from the table. We are not subtracting anything from one here. Okay, let's have a look at this. Z is between minus 1.5 and minus 0.3. Okay, now these are both negative values. So on the graph, that's this shaded region. That's this shaded region, right? Now, how do you find that? Both of these values are negative. So the first thing that we do is we say, let's flip this. Let's flip this, and that will give us this corresponding area. So between minus 1.5 and minus 0.3, using the symmetry of the graph, we can say that's the same thing as saying Z being between 0.3 and 1.5. And now again, this is the same as the previous case. We've got two positive values. Find the area to the left of 1.5. Subtract from that the area to the left of 0.3. Both of these are standard forms. We can use the table directly from them. Z less than a positive number, Z less than a positive number. Find the probability values from the table, find the difference, and you get the result from that. Okay. Now, the most complicated case is when you have something like this, when one value is negative in that interval and the other is positive, right? So you have this negative value and the other is positive. So Z is between a negative value and a positive value. Now, in this case, the problem is flipping does not help, because even if we were to flip this on the diagram, the thing is one of these values is negative and the other is positive. So if you were to flip this, this would become positive and that will become negative, and we still have one negative number, one positive number. So flipping this right away is not going to help. So how do we think about this? We think of it, this is one way of doing this, that we think of it like this. We say, okay, area between minus 0.9 and 1.2, that's what we're looking for. Let's find the area to the left of 1.2, all of this area. Subtract from that the area to the left of minus 0.9. Okay, just like we used to do in the first case that we saw earlier. For a two-sided interval, we say, let's find the area to the left of 1.2, subtract from that the area to the left of minus 0.9. Okay, now when you split it into two parts like this is now the standard form. This is the standard form, z less than a positive number. You can find this directly from the table. There's no problem with that. The problem is this one. This is not standard form. So you have to convert this part to the standard form now. How can you do that? We've done this case before. Z less than a negative number. You can think of it like this here. We are talking about this area. That's the area that we're looking to find. First of all, we could flip this, and that becomes the same thing as the area on the right side, right? That becomes the same as probability of z greater than 0.9. It becomes that, right? And then you can say subtract from 1 the area to the left of 0.9. And that gives you this 1 minus probability of z less than 0.9. That is what is going to give you this particular area. And now you see, we have converted this to standard form as well. This is standard form. This is standard form. This is also standard form. We can find these directly from the table now. Find these two values from the table, input them here, and that is going to give you the result. After simplification, you get that area. Okay. So that's what happens when you have one negative value and the other positive value. So that's the case in which you have simple normal distribution. Simple normal distribution means when you have some data given and you have to find some missing, you have to find the probability from that, right? You've got data given, you have to find corresponding probability value from that. That's how we work with this. But then there's another case, and that is when you have inverse normal. You would have inverse normal. Inverse normal, what's that? Inverse normal is when you have some information given about probability and there's something missing in the data. In the original data, there's something that is missing. Okay, so you have information about probability value, but mean might be missing, standard deviation might be missing, variance might be missing, and you would have to find that missing information. Okay, you have to find that missing information. Now, how do you do that? Let's consider this example. So let's say we've got a normal distribution like this, such that the mean is mu and the variance is 9. Mean is mu and the variance is 9. Okay, that's what we're given. So if variance is 9, remember the second number represents the variance, but in our calculation, we have to use standard deviation. So we can find square root of that. Standard deviation is 3 for this. And we're also given that probability of x less than 20, that is 0.6341. Given this information, what we're looking for is, we're looking for the value for mean. We want to find the value for mean somehow. Now, you have the probability given, and you have some missing information in the data, the mean is missing. So this is called inverse normal, where from the probability, using the probability, you have to find some missing information in the original data. Now, how does this work? For this, we first need to understand how to read the table in the reverse direction now. In the opposite direction, how do you read the table? Again, let's go back to the table. This is the table that we had. So now you would have some probability value. So when you have probability value, you have to search in this region. This is the region that represents probabilities. Okay, so you have to search in this region, not in the first column, in the first row. That's z values. You have to do the other way around now. Let's say you are given that there's a probability value 0.8790. So z less than some value is 0.8790. Now, what's that z value? How do you find that z value? That's the question. The z value, how do you find that? You would search for this probability in the table 8790. So the probability values are given in an ascending order from top left to bottom right. So they increase like this in this order. So it's not going to be difficult to find that. They're sorted like this. So 0.8790 0.8790. Let's search for that value, 0.8790. You keep going to the right, 8790, 8790. This is the value, 8790. Okay. Now this is the value 8790. Corresponding to this, what's the z value? It's 1.1 here and 7 here. You say the z value is 1.17. Okay, and you write that there. So that's how you read the table in the reverse direction. You have the probability given, and you have to find the z value. Now, in this case, in the first example, we could find that exact value in the table. Okay, we could find that exact value from the table directly. Now, what if you had 0.8599? 0.8599. Let's search for this. 8599. 8599. Okay, so this is 8599. Again, what's the z value corresponding to this? 1.0 and 8. 1.08, that's the z value that you get from this, 1.08. Let's take another example. Let's say we had 0.8753. 0.8753. Let's search for that. 8753. This is 8749. This is 8770. 8753 is not there in the table. 8753 is not there in the table. Right? In the previous two examples, we were able to find that exact value. Now, this is not there in the table. How do you find this corresponding z value for this? What you do is you consider the z value, the probability value in the table that's immediately smaller than this, 8753. What's the closest value that's less than this? That's 0.8749. You select this from here. Select this from here. The z value corresponding to that is 1.15. Right, 1.15, that's what you write down here. Write down here 1.15 first of all. But then you had 8753 there. In the table, you found 8749. What's the difference between them? 4. So that means you still need to add 4 more to this probability to get to the actual result. This is 4. And that gives you the corresponding third decimal place of z. That's 2. So the z value turns out to be 1.152 from this. That's the final z value that we've got. Okay, let's take another example. So in this case, we had to have the third decimal place as well, and that's how you can find that. Okay, now what about another example? Let's say we've got probability of 0.7080. Okay, 0.7080, let's search for that. 7080, we don't have that here. This is the immediately smaller value that we find, 7054. Now, corresponding to that, we've got 0.5 here, 4 here. The z value is 0.54 from that. But then we have found 7054. What's the difference between 7054 and 7080? We have 26. So we have to go to the right side now and search for 26 here. Well, do we have 26 here on the right side? We don't in this case. 26 is going to be somewhere here in the middle of 24 and 27. Now, is 26 closer to 27 or 24? It's closer to 27, so we use 27 from here, and we say that the third decimal place is going to be 8, and it becomes 0.548 from that. That's the z value that we get from that. Okay, take another example. Let's say you had 0.5892, and you had to find the corresponding z value for this, 5892. Let's search for that. 5892. Can we find that here anywhere? 5892. The immediately smaller value is this, 5871. Consider the z value corresponding to that, 0.22. That's the first two decimal places. But then how much more do you have to add? 92 and 71, the difference is 21. So you need 21 more. You go to the right side and find 21. Now, where is 21? Well, it's going to be in the middle of 19 and 23. We don't have 21 exactly. It's between 19 and 23. So now we think about which value is it closer to. Is it closer to 19 or is it closer to 23? Well, it turns out it's exactly in the middle. It's exactly in the middle. So what do we do in this case now? We either choose this or this. You can choose any of them, and that's all right. You can choose 19 or 23. So the third decimal place could either be 5 or it could be 6. Any of them would work in this case because it's exactly in the middle. So we can use any of those values. So you could say it's 225 or 226. Both of them will be acceptable in this case. All right. Okay, sometimes the probability value, if you look at the table, all the probability values here, they're given to 4 decimal places. Z values are given to 3 decimal places. Probability values are given as 4 decimal places. If you have a probability that is not given to 4 decimal places, for example, if you have 0.8, you would think of it as 0.8000. Okay, and then search for that in the table. 0.800 is not there. We've got 7995. Z value corresponding to that is 0.8 and 0.4. So that's 0.84. We have to add 5 more to that, and that gives us 2 as the third decimal place. It becomes 842. Okay, now if you had 0.7191, okay, so let's consider that. If the probability value was 0.7191, let's search for that. Do we have that here? 7191. Okay, 7190. This is the closest value that's smaller than that. The Z value corresponding to that turns out to be 0.5 and 8. So Z is 0.58, but then we need to add 1 more to it. Let's go to the right side. Where is 1 going to be? 1 is here, right? 1 is here. Now, is 1 close to 3 or is it close to 0? 1 is close to 0. So in this case, you do not add 1 here because 1 is actually close to 0. So you don't have to. So one choice is that you add nothing, you add 0. And the other is that you add 3. 1 is closer to 0 here. 1 is closer to 0. So you add nothing with that. You say this is 0.580. Okay, so this is 580 or just 58. Now, some values, you would find that some values are given directly at the bottom of the table as well. Okay, let me just show that to you quickly if I can find that. You would find that at the bottom of the table, there are some values that are given to you directly. And these are very common values. So sometimes you have a probability of 0.75, 0.9, 0.95, 0.975, 0.99. If you have one of these probability values, you can write the Z value corresponding to that directly from this table at the bottom. These are some common values. You don't have to, you can find these values from the table as well if you want. That will work as well. But you can just look at this bottom table for these common probability values. For example, if for probability is 0.75, the Z value is 0.674. For 0.9, it's 1.282. For 0.9 in particular, from the table, you get 1.281 or 1.282 because the third decimal place, for the third decimal, we'll have it exactly in the middle. So it's either this or this. But in the marking schemes, they normally use 1.282 for this. Why? Because it's already given here at the bottom. So you should prefer using 1.282 in this case and not 1.281. So for common values, I would recommend that you use these values at the bottom and skip the table. You'll get the same values from the table as well, but this is much quicker. That's what you should be using. Okay, let's move on now. Z values are written to 3 decimal places and probabilities to 4 decimal places in this table. Now, let's go back from where we switched to that table earlier. So now we know how to read the table in the reverse order, how to read the table in the inverse order, right? So now let's say we are given that there's a variable such that its mean is unknown. We have to find that, and its standard deviation is 3. And we're given that the probability of x is less than 20, that is equal to 0.6341. How do you find the value for mean? Remember, the table can only be used for that particular form where probability of z is less than a positive number. So how do you go about finding this value for mean? First of all, you say, okay, if probability of x is less than 20, if that is equal to 0.6341, you think of it like this. Okay, what's the corresponding z value for this? What's the corresponding z value for this going to be? So you write it like this: z less than some expression that is equal to this. Okay, so first of all, you write it like this. You replace x with z, and you say z less than some value that is going to be equal to this probability. So we have to find the value of z that corresponds to 20 here. We have to find that value for z. Now, how do you find that? You cannot use the table unless you know for sure that this is the standard form, because this number could be negative, it could be positive. So the first thing that you have to do always is figure out whether this number here is positive or negative so that you know if you can use the table for that or not. How do you figure this out? You think about the normal distribution curve for this. And that's how you figure this out. You say, probability of z less than this number that is equal to 0.6341. So on the normal distribution curve, what we're saying is the area towards the left side. So less than means we are saying area towards the left of this z value that is equal to 0.6341. Now, is 0.6341 a small area or a big area? Remember, the total area is 1. So with respect to 1, half of 1 is 0.5, right? So 0.6341 is more than half. It's bigger than 0.5. So we want the area to the left of the z value to be a bigger value, to be a big value. Now, where do we place z on this normal distribution curve then? Do we place that on the left side, on the negative side, or on the positive side? If you were to place that on the negative side, the area to the left side would be smaller. If we place that on the positive side, the area on the left side would be bigger, and that is what we want. So that tells us that the z value is supposed to be positive here. Now, if that's positive, now we know it is the standard form, z less than a positive number. We can use the table for this. We go to the table, find the z value corresponding to this probability, 0.6341, and that would give you the z value 0.343. Now we've got the z value. We had to find the mean. We use the formula that we've got, z equals x minus mu over sigma. Z value is 0.343, x is 20, mean is unknown, standard deviation is 3. Just input those values in this formula, you get the value for mean from that, and that's what we were looking for. Let's take another example. What if you had something like this? There's a variable x, again, that's normally distributed, and the mean is unknown, variance is 25. Again, we have to find the value for mean. It's not necessary that you'll always have the mean missing. Sometimes you have the standard deviation missing or the value of x missing. It could be any missing information in the data. You have this value of x missing as well. The idea is going to be the same. It's the same process that we follow. If it says x, probability of x greater than 30 is 0.2. How do we go about doing this? We say that means z greater than some value, this probability is going to be 0.2. And now the first thing we have to do is we have to figure out whether this number here is positive or negative. So again, how do we think about this? We say area towards the right side, area towards the right of this value, area towards right of this value, that is 0.2. Is that a small area or a bigger area? If you compare that with 0.5, that's a small area. So z has to be somewhere such that the area to the right of that is small. So where do we place z then? If we place z on the negative side, area on the right would be bigger. That's not what we want. If we place z on the positive side, area on the right would be smaller, and that's what we want. And now we know that this area here, this is 0.2. But so we understand that z value is supposed to be positive. But the problem is it's not the standard form. It's z greater than something. The standard form for using the table is z less than positive. So we convert it to that form. How do we do that? We say, okay, if the right side is 0.2, then that means area on the left side of this is going to be 0.8. So we can write this as that the probability of z less than that value, that is equal to 0.8. Right? If the area to the right is 0.2, area to the left is going to be 0.8. And now this is the standard form. It's z less than a positive number. We can go to the table, find the z value corresponding to this probability. Right? This probability is 0.8000. Go to the table, find the z value, and that z value turns out to be this 0.842. And that gives you the corresponding mu. When you input that in the formula, you get the value for mean for that. What if you had something like this? Now we've got normal distribution. and we've got the mean of that distribution, we've got the standard deviation and variance. And now they're saying probability that x is greater than some value is equal to 0.725. And we need to find the value for a. We need to find the value of a in this. How can we do that? Again, what's the process? First of all, we write this like this. We say, write this probability in terms of z. X greater than a, let's say that corresponds to z greater than some value. That probability is 0.725. And again, we think of it like this. We are saying the area towards the right side. The area towards the right of this z value, is that smaller or bigger? That's bigger. So where do we place z then on the normal distribution curve? If we place that on the positive side, area on the right side will be smaller. That's not what we want. So we have to place that on the negative side. So in that case, the area to the right would be bigger. So that tells us that the z value is actually going to be negative. So z value is negative here. That's what we understand from that. Okay, so first of all, you have to identify that whether that z value is positive or negative, and this is telling us that it's supposed to be a negative value. Now, if it is a negative value, that means it's not the standard form. The standard form is z less than a positive number. This is not the standard form. So what do we do then? We can flip this. We can say, let's flip this. If that area to the right of that negative value is 0.725, if we were to consider the corresponding positive value of z here, the area to the left of that positive value using the symmetry of the curve, this area should also be the same, right? So if this number was, let's suppose, minus 1.5, the area to the right of that is the same as the area to the left of plus 1.5 because of the symmetry of the curve. So whatever was that negative value, the corresponding positive value for that, the area to the left of that, that will also be 0.725. So what we can do is we can say, we can write this probability as probability of z less than the positive z value. That is equal to 0.725. And now this is the standard form. This is something that we can use the table for. Go to the table, find the z value corresponding to this probability 0.725. And that turns out to be 0.598. And now we don't put this in the formula directly. Since we know that z value was supposed to be negative, we have to write this as a negative value. So we say the positive z value, this side, this is 0.598, but the actual z value was negative. So we put a negative sign with that. And we say this is minus 0.598. Put that in the formula now. You know the mean, you know the standard deviation. X is missing. In place of X, you put A. And that gives you the value for A. You get the result from that. And then the last case for this, when you have a normal distribution that looks like this, its mean is 40, its standard deviation, its variance is 25. And again, what we're given is that probability of x less than b, that is equal to 0.215. And we want to find the value for b somehow. Again, we think of it like this, z less than some number that is equal to 0.215. And again, that means that area towards the left is smaller. So where should z be? Z should be on the negative side. That's where z should be. This is where z is going to be. It's going to be on the negative side, because that will make sure that the area on the left side is smaller. So that means z is a negative number here. If z is a negative number, that means it's not the standard form. The standard form is z less than a positive number. So how do you convert it to standard form then? That's the question. First of all, we could say, let's flip this. It's a negative number, right? Let's flip this. If this area is 0.215, if we flip this, that means this area here to the right, this should also be 0.215. The area to the right of the positive z value, that should also be 0.215. But that as well, we cannot find from the table directly. We can only find area to the left side of a positive value. So now we say, if this area is 0.215, then what about the area to the left of this positive value? We could just say that is going to be 1 minus 0.215, and that is 0.785. So area to the left of this positive z value, that is 0.785. We convert it to this form. We say probability of z less than that positive value, that is 0.785. Now, this is something that is in the standard form. Go to the table, find the z value corresponding to this. That turns out to be 0.789 from the table. Now, the actual z value was supposed to be positive, as we found earlier. So we put a negative sign with this, minus 0.789. and then just input in the formula, find the value of b from that, and that gives you the result. Okay, so that's how inverse normal works. These are the four standard cases that you would have here for one-sided intervals. For two-sided intervals, it's a bit more complicated. That's very rare as well, but we will see that when we do some questions. I have a couple of examples signed up in which you have two-sided intervals. We'll talk about them. So that's the second major part of normal distribution that we have. Inverse normal, when you have probability given and you have to find some missing information from the data. Then the third major concept that you have here is binomial to normal approximation. Binomial to normal approximation. Now let's think about this. You've got this example. It says assume that for a randomly chosen person, the next birthday is equally likely to occur on any day of the week. That means every day has equal probability. What's the probability of the birthday being on a Monday? That's 1/7, right? And for every day, it's 1/7. Now, they want us to find that out of 350 randomly chosen people, at least 47 will have their next birthday on a Monday. Now, what kind of distribution is that? We have some repetition going on. We've got 350 people that we're talking about. For each of them, the probability that the birthday is on Monday is the same, right? For every person, it's the same probability. That's 1/7. So we could say it's a binomial distribution because n is 350, probability of success 1/7, if you call this a success, having your birthday on a Monday, then probability of failure would be 6/7. So what we're actually looking for now is probability that you have at least 47 successes, So that becomes x greater than or equal to 47. That's what you have to find in binomial distribution. Now, x greater than or equal to 47, what does that mean? The total number was 350. You have to find all the probabilities from 47 onward. 47, 48, 49, 50, 51, 52, all the way up to 350. That's a lot of probabilities to calculate. How do you do that? That's very complicated, right? That's going to be a lot of calculation. Even if you do the other way around, if you say that these probabilities are too much to calculate, what if you do 1 minus probability of x less than 47? Can you do it that way? In that case as well, you have to find probabilities for x equals 0, 1, 2, 3, 4, all the way up to 46 and subtract all of them from 1. Again, too much calculation. It's not feasible to do it manually. So in such cases, what we do is we use something that we call binomial to normal approximation, which the calculation from binomial directly becomes very tedious, it becomes very long. Okay, now how is that done? How do you convert it to a normal distribution? If it was a binomial distribution, these were the values of NP and Q that we had there. In normal distribution, the parameters are mean and standard deviation. Right? These are the parameters of normal distribution, mu and sigma. How do you find mean and sigma from this? For a binomial distribution, remember mean is given by n times p. Standard deviation is square root of NPQ. In the formula sheet, you have the variance given, that's NPQ. Standard deviation will just be the square root of that. That's square root of NPQ. You find the corresponding mean value and the standard deviation value from this. Once we have these values, we can now think of it as the normal distribution and find the probability from that. But there's another problem here, and that problem is we've got this as a discrete distribution. So greater than equal to 47, what that means is in discrete distribution, greater than equal to 47 actually means if you have this number 47 and this is 48, this is 49, then greater than equal to 47 means that 47 is supposed to be considered, 48 is supposed to be considered, 49 is supposed to be considered, and 46, 45, they're not going to be considered. So these values, we will consider all of them, the values to the right of 47, and these values, we're not going to consider values to the left of 46. And for discrete distributions, that's perfectly okay. There's no problem with that. Because the decimal value, there are no decimal values that can exist here, right? So we just consider the region to the right of 47, the region to the left of 46. But the problem in normal distribution is when we convert it to normal distribution is a continuous distribution. So in a continuous distribution, values can also be in decimal. So we can also have some value in the middle here. We can have 46.1, 46.2, 46.5, 46.7. What do we do with those values? In discrete, that was not a problem because greater than or equal to 47 meant these, that we have to select these and not select these. Now, in normal distribution, what do we do with this region in the middle? What we do is we say, let's divide it into half. So the problem is, do we consider this region or do we not consider this region? So on that normal distribution curve, the region between 46 and 47, will we count that in this probability or will we not count that? Right? That's the problem. So what we say is, let's break it in two halves, break it in the middle, 46.5. So any value that's less than 46.5, that will round off to 46. Any value that's greater than 46.5, that will round up to 47. So we have the cutoff point in normal distribution 46.5, and we say, if you have x greater than or equal to 47 here, in normal distribution, we would say that becomes greater than 46.5. Now, I'll tell you exactly using some examples how to do this in different cases. But the idea is you convert it like this. First of all, once you've converted to this form, then the next thing is just finding the z value from that and finding the probability from the table. That's something that we have done already. Once you've converted it to normal like this, find the z value from this. That will give you something like this, and then you convert it to the standard form, z less than positive, using the methods that we've discussed earlier. Find the probability from the table, and you get that result. Now, how exactly do you do this? This is called continuity correction. What we're doing here. Let's do some examples of that. So one thing that you have to do is you have to find the mean of this distribution and the standard deviation. These are two things that you have to do. But then, how do you do this continuity correction? Let's do that in a bit more detail. Consider that same example, greater than or equal to 47. Now you get the idea, why do we need to do that? But now what's the process that you would follow to figure out what number we are going to have here? For example, if you have x greater than or equal to 47, if you have something like this, what you would do would be, you would consider three numbers. One, that same number, 47, one number bigger than that, one number smaller than that. So 46, 47, 48. And you think about these numbers, is 46 going to be included in this greater than or equal to 47? Does that satisfy this condition? No, 46 does not satisfy the condition. Does 47 satisfy the condition? Yes. 48, yes. Now, wherever the decision is changing, included and not included, between cross and tick, this is where you break. This is where you split these numbers and you say, okay, in normal distribution, we would say, we consider the midpoint of this, 46 and 47. So in normal, it will become greater than 46.5. The midpoint of those two numbers, that's 46.5. Now in normal distribution, it doesn't matter if you put the equal to sign there or not, or don't do that. We talked about that in the beginning. So that does not matter. But we choose the midpoint here of 46 and 47. So it becomes 46.5. If you had this, x greater than 47, what would you do in this case? Again, you think of those three numbers. Is 46 included? No. 47? No. 48? Yes. So it's changing between 47 and 48. You use the midpoint of them. That's 47.5. So in normal distribution, it will become greater than 47.5. That will be the probability that you find from the table after converting into z. If you had x less than 93, again, you think of these three numbers. One number less than that, one number greater than that, and one number itself. 92, is that included? Yes. 93, is that included? No. 94, no. So between tick and cross, you've got 92.5. You say this is x less than 92.5. And then finally, if you have x less than or equal to 145, again, you think of those three numbers. 144, is that included? Yes. 145, yes. 146, no. Decision changes between 45 and 46. So you choose the midpoint of them. 145.5. That's what you do in normal distribution after continuity correction. Okay, so that's how you would be converting something to normal distribution. Sometimes you have to figure it out yourself. So in this question, for example, calculating these probabilities, there were so many calculations, like 47, 48, 49. There were too much calculation that was not feasible to do it manually. So we converted it to normal distribution for that reason. Mostly they will tell you in the question, Mostly they will tell you in the question that you have to use this approximation. So whenever they say in a question, use an approximation, use a suitable approximation, there's only one type of approximation that you have in your syllabus, and that is binomial to normal approximation. So the word approximation in the question, that would tell you that the original distribution is binomial and you have to convert it to normal. And that's one of the easier questions that you would find on both binomial and normal distribution. Okay, so you convert it to mean, you find the mean and standard deviation for normal, do continuity correction, and find that probability. But there are some conditions. You cannot use this approximation every single time. There's some condition for this, and that condition is that the data should be large enough. Now, the criteria that we use for data being large is this. You need to memorize these conditions. N times P should be greater than 5, and N times Q should be greater than 5. N is the total number of values in binomial distribution, total number of repetitions. P is the probability of success, Q is the probability of failure. For a normal distribution, for an approximation from binomial to normal to be reliable, both of these conditions have to be satisfied. Both of these conditions have to be satisfied. If any of them is not satisfied, then we cannot use approximation. That is the result that we get from that is not going to be a good estimate. It's not going to be reliable. For example, in this case, N was 350. Probability of success was 1/7. So N times P is 50. 50 is greater than 5. That satisfies the condition. N times Q, that is 300. 300 is greater than 5. That satisfies the condition. Both conditions are satisfied here. So in this case, it is appropriate to use this approximation. If any of these numbers was less than 5, it would not be appropriate. Okay, so that's the cutoff point that we use in our syllabus to figure out if this approximation is valid or appropriate or not. Okay, all right. For example, this is one case. You have to use a normal approximation to find the probability of this. You can have a look at this example. You have P, N, Q. You have to find X less than 25. Do continuity correction. Find the mean and standard deviation. Find that probability. You get that result. Right? That's pretty straightforward. Now, in the second part, they say give a reason why the use of normal approximation is justified. You would have to find these two values. You would find N times P. N times P turns out to be 24. That is greater than 5. N times Q, that turns out to be 6. 6 is greater than 5. Both of these conditions are met. Since both of these conditions are met, that justifies the use of normal approximation. If any of those numbers was not greater than 5, we would not be able to use this approximation. The greater these numbers are, the better your approximation is going to be. If these numbers are smaller, then the approximation is not going to be as good. But that's the cutoff that we will be using. If they're equal to 5, the condition is greater than 5. So you will not get a question in which it's equal to 5. But according to this criteria that we use in Cambridge, if it's exactly equal to 5, we will not do that. It has to be greater than 5. Okay, greater than 5 is the condition. Okay, let's have a look at some examples now. A few simpler ones, and then we'll look at the more difficult ones. Let's say we've got daily minimum temperatures in degrees in a particular city, and we've got the normal distribution such that the mean of that distribution is minus 15.1, and the standard deviation, the variance is 62. Standard deviation would be square root of 62. We have to find the probability that a randomly chosen day in January in Ottawa has a minimum temperature above 0 degrees Celsius. So what's the probability of the temperature being above 0 degrees Celsius? That means probability of X greater than 0. That's what you have to figure out. How do you do that? You first of all convert it to Z using this formula. Z is X minus mu over sigma. So it becomes Z greater than this using the formula. Right? You get Z greater than 1.918. Again, you think of the normal distribution curve. This is not the standard form. You do 1 minus the area to the left of this to convert it to standard form. Find this from the table and you get the result. Right? So sometimes you have very simple problems like this. You have one part of normal distribution question that is fairly straightforward, simple normal distribution. You have the data given, you have to find the probability from that. The next part is inverse normal. That's going to be generally the more complicated part. In this case, that's also straightforward, but sometimes this is the more complicated part. Let's have a look at this. In another city, the temperature is a random variable with this distribution. Mean mu, variance 40. Do not say that standard deviation is 40. That's a very common error. This number represents variance. Okay, so standard deviation would be square root of that. We are given that the probability of the temperature being above 0 is 0.888 in this case. Find the value of mean. How do we think about this? We say probability of x greater than 0 is this. Convert that to z. Z greater than some value is negative. Some value is 0.888. Figure out whether z is negative or positive. We know that area to the right here is supposed to be bigger. If the area to the right is bigger, that means z is supposed to be a negative value. So this area is 0.888. You flip that. When you flip that, you can say the area to the left of the positive z value, that's also going to be 0.888. Find that value from the table. Make that negative because it was supposed to be a negative value. Put that in the formula, and you get the result from that. Okay, so that's a relatively simple problem that you see on inverse normal. Let's have a look at another example. Okay, so just a minute. My pencil is running out of battery. I will just resume in 1 minute. Okay, since that charges a little, then we resume. No, it's I think first generation. It's not Pro. It's the one before that. It's been some time. I think it's 3 years old now, so it's battery is not very good. But it did not get charged at night. I forgot to put it on charging, so that's why I think it just ran out of battery. That happens sometimes. Okay, let's resume. Okay, so sometimes they ask you to give examples like this of a normal distribution variable. Remember, normal distribution is used for any continuous variable. So any variable that you can think of that can take any decimal value. You can use that, for example, height, weight, temperature, mass, length, anything that can take any decimal value. Okay. So you can write any of them, any one of them. These are just, multiple examples. You can choose any of them. The second part is inverse normal. We will skip that. That's standard part. Now, sometimes they want you to find expected value of something. For example, they're saying if 300 observations are taken at random from the distribution in this part two, estimate how many of these would be greater than 22. Now, how do you approach these problems? You would find the probability of one observation being greater than 22, first of all. Find the probability of one observation being greater than 22. So you'll find that using simple normal distribution, probability of x greater than 22, convert that to z, find that probability. That's the probability of one observation being greater than 22. But then, how many out of 300 observations would you expect to be greater than 22? This is the probability of one being greater than 22. You multiply this by the number of observations. That's 300, 300 into that. This is what you would expect. This is turning out to be a decimal value. When you talk about number of observations, that has to be an integer. So you round this off. This rounds off to 7. You would write 7 as the final result. Always round it off to an integer. Decimal value is not going to be acceptable when they talk about number of something. It has to be an integer at the end. The answer has to be an integer, otherwise we'll lose 1 mark. Okay, so when they ask you to find expected value of something or estimate how many times out of a certain number you would expect something to be true, you find the probability for one, and then you multiply that by that number to get that expected number. Okay, now sometimes they ask you to find probabilities and they don't give you numbers, but they ask you to do it in terms of mu and sigma like this. Now, don't get scared by that, because when you start working, when you start inputting values in the formula, you will figure out that these unknowns will start canceling out. For example, they have told us that a distribution has mean mu and standard deviation sigma. Now, then they've not given us any numbers here. And they're saying, how many of them would you expect? So if 800 observations are taken, how many would you expect to be between mu minus sigma and mu plus sigma? Let's first of all find the probability for one observation being between this interval, being within this interval. For one observation, you can say probability of x between mu minus sigma and mu plus sigma. Okay, that's what we're looking for. Now use the formula z is equal to x minus mu over sigma to convert it to z. When you convert it to z, you see what happens. Mu and mu get cancelled, and then the sigma and sigma, they also get cancelled. And you get z between -1 and 1. That's the final result that you get from this. Now, these are numbers, z between -1 and 1. You can find that if it's between -1 and 1, one way of doing this would be, you can say on the normal distribution curve, this is -1, this is +1. Since the curve is symmetric, whatever is the area on the left side of the mean in this case, since both of these numbers are the same, right, in terms of their magnitude, they are the same distance away from 0. Whatever is the area on this side, that's going to be the same as the area on this side. So you can find any one of those areas and multiply that by 2. So what I've done here is I've said probability of z being between -1 and 1. That's the same thing as saying 2 times probability of z between 0 and 1. How do you find between 0 and 1? Find the area to the left of 1, this area, subtract from that this area, that's the 0.5, right? Area to the left of the mean, and that will give you the result. You find use the table for this. That's 0.8413, and then just input that. You get the result. That's 0.6826. That's the probability. And then what's the expected value then? For the expected value, what you would do would be you would multiply this by 800. You would say 800 times 0.6826, and you would get some value from that. That will be in decimals. You have to write an integer value for that. Okay, write an integer value, and that will be your final result. Okay, so if you have something like this, don't just leave it as it is, as in don't think it's very difficult. Just input in the formula and things will start canceling out themselves. Okay, all right, let's move on. We've talked about this already. It's a repetition. Okay, there's a variable x, and we're given that it follows normally distributed, follows normal distribution with mean mu and variance sigma square. It's given that probability of x greater than 30 is equal to this. Probability of x greater than 20.9, that is equal to 0.6228. So you're given two separate pieces of information, and you want to find the value for mean and standard deviation. Mu and sigma, that's what we're looking for. We're looking for mean and sigma, right? Okay, so we were here. So now in this case, they say the random variable x is the length of time that this person takes to mend a bicycle puncture. X follows normal distribution with mean mu and variance this, and they've given us two pieces of information. Probability that x is greater than 30, that is equal to 0.1480, and the probability that x is greater than 20.9, that is equal to 0.6228. Now, we've got probability values given for both of them. We have to find mu and sigma. So this is inverse normal, right? Probability is given, and we have to find mean and sigma. Now, these are two separate equations that were given. What we do is we apply the inverse normal method on both of them separately, on this separately, on this separately. We get two equations from them. One this equation and not this equation. And then we solve those two equations simultaneously, right? Solve this and this simultaneously, and that will give you the value for mean and sigma. So that's something that can also happen sometimes, that they give you two pieces of information, you make two equations from them, and then you solve them simultaneously to get the result, right? For each of them, it's the standard inverse normal problem. You make two equations from them, and then you solve them simultaneously. Okay, so that's something that could also happen sometimes. Okay, let's have a look at this example. The time spent, let's call that x, by people visiting a certain dentist are independent and normally distributed. So we've got normal distribution here again. The mean of this distribution is 8.2. 79% of people who visit this dentist have visits lasting less than 10 minutes. So we are given the probability that a visit lasting less than 10 minutes, the probability of that is 0.79, right? 79% is 0.79. Find the standard deviation of the time spent by people visiting this dentist. We've got the mean given, and we have to find the standard deviation. That's what we're looking for. Okay, so this is standard inverse normal problem. Convert it to Z, figure out whether Z value is positive or negative, convert it to standard form, use the table, put that in the formula, you get the value that we were looking for. Now, second part is what I want to focus on. It says, find the probability that the time spent visiting this dentist deviates from the mean by more than 1 minute. How do you understand that? Deviates from the mean by more than 1 minute. Now, what's the mean? Mean is 8.2. Mean is 8.2. If it deviates from the mean by more than 1 minute, what that means is, if you've got 8.2 here in the middle, 1 minute on this side is going to take us to 9.2. 1 minute on the other side is going to take us to 7.2. It deviates more than 1 minute. So that means we are either in this region to the left of 7.2 or in this region to the right of 9.2. These are two regions that we have that satisfy that condition. So we say the probability that we're looking for is probability of x being less than 7.2 and the probability of x being greater than 9.2. We have to find these two probabilities, and that's going to give us the result. Okay, so something happened to this normal distribution curve that I had here, but it would look like this. So this is the normal distribution curve. This is what it would look like. What you're looking for is, you've got Z value on the left side somewhere. This is minus 0.448. You've got Z value on the right side, 0.448. You're looking for these two regions and you have to add them up together. Area to the left side here, area to this side here, and area to the right side here. You're looking for both of these regions. So you convert it to Z value. That gives you this and this. Now, if you think about it, these are both the same, right? Because the curve is symmetric, this area and this area, they're both the same. So we can just try and find one of them. Finding it for the positive value, it's easier. You just do that calculation, and then you say the other one is also going to be the same because of the symmetry of the curve, and that gives you the final probability. Okay. So deviate by more than 1 minute. In this case, what does that mean? To the right of 9.2 and to the left of 7.2. Okay. All right. Then it says, find the probability that of 6 randomly chosen people, more than 2 have visits lasting longer than 10 minutes. Now, this is where they have two distributions. Remember, in binomial distribution, we talked about when you have two binomial distributions, one binomial inside another binomial. In normal distribution, that can happen as well, that you have one binomial distribution. And to find the probability of success for that, you have to use a normal distribution. So look at this example. 6 randomly chosen people, more than 2 have visits lasting more than 10 minutes. Now we're talking about people. That's a discrete variable, number of people, right? That's discrete. So that cannot be normal distribution. This is binomial distribution with n being equal to 6. And the criteria for success is that the visit lasts longer than 10 minutes. So this is a binomial distribution where this is the criteria for success. Now, what's the probability for success? They've given that in the question. 79% have visits lasting less than 10 minutes. This is longer than 10 minutes. If less than 10 minutes is 0.79, longer than 10 minutes would be 1 minus 0.79, that's 0.21. This is the probability for success. So this is a binomial distribution now with n equal to 6, probability of success 0.21, failure 0.79. Find the probability that x is greater than 2, more than 2 successes, and that will give you the result using binomial distribution. Okay. Then it says, find the probability that of 35 randomly chosen people, fewer than 16 have visits lasting less than 8.2 minutes. Again, how do you think about this? 35 randomly chosen people, 35 people. That's a discrete variable, right? A number of people. Fewer than 16 have visits lasting less than 8.2 minutes. N is 35. This is the criteria for success. Visit lasts less than 8.2 minutes. How do you find the probability of this? Visit lasts less than 8.2 minutes. You have to use normal distribution for that. Now, in this case, it's easier because you knew that the mean is 8.2. If the mean is 8.2, then less than 8.2, probability of that would just be 0.5 in this case. But if it was some other number, we would first have to find that probability using normal distribution, and that would become the probability of success for this binomial. So it looks like this. It's a binomial distribution with n35, probability of success 0.5, probability of failure 0.5. Okay. And now what you're looking for is probability of having less than 16 successes, less than 16 successes. That's what they want, right? Fewer than 16 successes, less than 16 successes. Now, what does that mean? Now, you see in the question, they have not talked about any approximation or anything, but you know that this is binomial distribution and you have to find probability of x less than 16. Now, how do you do that? Less than 16 means x equals 0, 1, 2, 3, 4, 5, 6, all the way up to 15. That's a lot of calculation. On the other hand, if you do 1 minus the remaining probabilities, that will also be too much. 16, 17, 18, all the way up to 35. That's too much calculation if you try to do it directly. So you have to figure it out yourself that you have to use normal approximation here. Convert it to normal distribution, find the mean standard deviation, do continuity correction, and solve it as a normal distribution. That gives you the result. You can check that the conditions are satisfied. NP and NQ. NP, you can see that's greater than 5. NQ is greater than 5. Both of those conditions are met. So you can use approximation. So that's what you do here. Okay. It says visits lasting less than 8.2 minutes. This has to be found from the normal distribution, right? Now, if it was any other number, for example, if it was x less than 8.9, for instance, we would have to use normal distribution first of all, because times were normally distributed to find that probability. But in this case, they've made it easier. They've said x less than 8.2. 8.2 is the mean value. We know the curve is symmetric. So if it's 8.2, then to the left of 8.2, the area is 0.5, right? To the left of the mean is 0.5, to the right of mean is 0.5. So the probability of success directly comes out to be 0.5 in this case, because we're talking about area on one side of the mean. If it was anything else apart from 8.2, we would have had to do that calculation ourselves, first of all, using normal distribution. Okay, so that's one of the more complicated problems in which you have a binomial distribution and define the probability of success for that. You have to use normal distribution. Okay, let's have a look at this example. There's a normal distribution with mean 20 grams and 94% of the letters have weights within 12 grams of the mean. Okay, now how do you understand that? Mean is 20, 94% have means that have weights that are within 12 grams. 20 is the mean. Within 12 grams of the mean, you go 12 to the left, 12 to the right. It's between 8 and 32. Between 8 and 32. We are given probability of x being between 8 and 32. That is equal to 0.94. That's equal to 0.94. That's what we're given. Now, this is inverse normal. This is inverse normal. We have to find the standard deviation. Probability is given, we have to find standard deviation. Now, how do we do this? Think of the normal distribution curve. You can convert it to z first of all if you want, and then think of the normal distribution curve, or think of the curve first and then convert that to z. Both of them are okay. In this case, I've done it directly. 20 is in the middle, right? 8 is on the right, on the left side, 32 is on the right side. Now, think about it. We are talking about area between these two values to be 0.94. Now, the problem is in inverse normal, we did not cover what happens when you have an interval like this, two-sided interval. This is something that you have to figure out based on the question, because it varies across questions. Now, in this case, you have to somehow convert it to a single-sided interval. This is a two-sided interval between 8 and 32. You have to somehow convert it to single-sided intervals to be able to apply inverse normal. Now, how would you do that? Look at this curve. Between 8 and 32, the area is 0.94. Now, remember the curve is symmetric. The curve is symmetric. And both of these numbers are equal distance from the mean on both sides. If the area in the middle is 0.94, what's the area that's left? 0.06, 1 minus 0.94, that's the remaining area. That remaining area is divided equally on both sides. 0.03 on the left side, 0.03 on the right side. So we can say if the area between 8 and 32 is 0.94, then the total area to the left of 32, can we say anything about that? The total area to the left of 32, that is 0.94 plus 0.03, that is 0.97. So we could convert it to a single-sided interval like this. X less than 32, that probability is 0.97. And then it becomes a simple, that becomes a standard inverse normal problem from here onwards. You convert it to Z, write this in terms of Z, figure out whether Z is positive or negative, find the value of Z from the table, and put that in the formula, and you get that value for standard deviation. So if you have two-sided intervals in inverse normal like this, you have to somehow figure out a way to convert them to one-sided intervals. So that's what you could do in this case using the symmetry of the curve. We could say area to the left of 32, that is 0.97. And then we just do it afterwards, like normally do. Find the probability that a letter weighs more than 13 grams. That's simple, normal. That's fairly straightforward. You can look at this working. And the last part it says, find the probability that at least two of a random sample of 7 letters, have weights which are more than 12 grams above the mean. Now, how do you understand that? First of all, this is binomial, right? Because we're talking about a sample of 7 letters, number of letters, and we want at least two successes. That's binomial distribution. What's the criteria for success here? A letter having more than 12 grams, a letter having weight more than 12 grams above the mean. This is the criteria for success. Now, first of all, we can find the probability for success. More than 12 grams above the mean. How do you understand that? Mean is 20. Standard deviation is 0.38. In fact, we don't need to do any calculations here. If we think about it, we are given that information. Yeah, so we're given that information. We use that in the first part as well. More than 12 grams above the mean, what does that mean? More than 32. Probability of X being greater than 32. Now, using the symmetry of the curve in the first part already, we know area to the right of 32, how much is that? That's 0.03. Okay. If we did not know that, we would have to do that calculation using normal distribution, first of all, to find that probability. But we have done that work already using symmetry. We know that that area on the right side of 32, that is 0.03. So that's your criteria for success. Probability of success is 0.03, therefore. Failure, 0.97. And 7, find the probability of having equal to or more than 2 successes. Greater than or equal to 2 successes. Find that like you normally do. You reverse that because 2 to 7 is more probabilities as compared to just 0, 1. Subtract from 1, probability of X equals 0 and probability of X equals 1, and you get the result from that. Okay, so sometimes you can have binomial distribution and the probability of success of that is found using normal distribution like this. Okay, just a few more examples. No, yeah, just a couple more, I think. Let's have a look at the next one now. Okay. The time X hours for which students use a games machine on any given day is normally distributed with this mean and standard deviation. On how many days of the year would you expect a randomly chosen student to use the game machine for less than 4 hours? Find the probability for one student that he uses it for less than 4 hours, and then multiply that by 365. Okay, so for one student, it's this. Using simple normal distribution, multiply that by 365, you get this. And then you round that off to an integer. Rounding that off is necessary, and that will give you the result. Second part is just inverse normal. Probability of X greater than K is 0.2. And you can just find the value of K using inverse normal. right? We have done that multiple times. The last part is what I want to focus on in this. The last part says, find the number of hours for which a randomly chosen student uses the games machine in a day that is within 1.5 standard deviations of the mean. Within 1.5 standard deviations of the mean. Now, how do you think about this? One idea is that you think of it like this, that you say, okay, x is 3.24. 1.5 times the standard deviation, you find that. And you have to be between 1.5 times 0.96 plus this and 3.24 minus 1.5 times 0.96. X is going to be between these two values. Within 1.5 standard deviation, what does that mean? It could be 1.5 standard deviations above the mean or below the mean. So it has to be between these two values. Okay, between these two values. So you could do something like this. That's one idea. You say x is between 3.24 minus this or plus this, and that turns out to be this. And then you solve that like you normally do. However, there's a much more efficient way of doing this, and that is using that understanding of z that I told you about earlier. Z value represents the number of standard deviations you are away from the mean. Remember we talked about that in the very beginning. Z represents the number of standard deviations that you're above or below the mean. So when they talk about something like this, that a variable is within 1.5 standard deviations of the mean, what does that mean? If we think of the Z distribution directly, we can directly think about the Z. The mean of Z is 0. Within 1.5 standard deviations means minus 1.5 on the left side and 1.5 on the right side. In a Z distribution, standard deviation is 1, right? So for a Z distribution directly, we could say Z has to be between minus 1.5 and plus 1.5. Do not even think about X. Just directly use the Z value like this. You would say Z is between minus 1.5 and plus 1.5. Okay. You can skip all of this work where you write that in terms of X first of all, then convert it to Z. That's not required because we know already in terms of Z, we can write it like this. Find this probability. How do you do that? Using the methods that we've done earlier. You can look at this working. That's how it would work. Okay, let's take this example. Again, the first part is pretty straightforward. The second part asks you to do something very similar. You've got mean times, and you've got times taken by students to get up in the morning. They have normal distribution this and standard deviation this. Okay. The second part says very slow students are students whose time to get up is more than 1.645 standard deviations above the mean. What do you understand from that? More than 1.645 above the mean. Now, this is the mean, 26.4. So you'll say 26.4 plus 1.645 times 3.7, which is the standard deviation. X has to be greater than this. Okay. But a direct way of doing that is when they talk about standard deviations that you're away from the mean, you could do directly like this. You could say more than 1.645 above the mean. That's the same thing as saying probability of Z is greater than 1.645 directly. You do not even have to do this calculation. You can directly write Z greater than 1.645. Just directly write this. And then you find that probability. You see what that turns out to be. They're saying find the probability that fewer than 3 students from a random sample of 8 are very slow. That's binomial distribution now. N is 8. Success is being very slow, right? That's your ideal world in which being very slow is successful. So a random sample of 8 students, out of them, what's the probability of having less than 3 successes? You find the probability for being very slow, first of all. You would say that is probability of Z greater than 1.645. Find this from the normal distribution curve. And then you just use binomial distribution to find that probability that you had less than 3 successes with n equal to 8. P equal to 0.05 from there from the normal distribution and Q equal to 0.95. The probability of success is coming from normal distribution in this case. Okay, let's have a look at another example. Again, inverse normal in which you have two-sided interval. You've got tire pressures of a certain type of car. They follow normal distribution. Mean is 1.9, standard deviation is 0.15. We've got the mean and standard deviation given. Find the probability that all four tires on a car of this type have pressures between 1.82 and 1.92. Now, for one tire, can we find that? We can find this probability for one car. For one tire, find this probability x between 1.82 and 1.92. Do it using the normal method. Convert it to z first of all. Find this probability. And that probability turns out to be 0.2558, right? It's that case in which one z value is negative, the other is positive. We've discussed that before. You find this probability. Now they're saying probability that all four tires satisfy this condition. So this is the probability for one of them. For all four, what we can do is we can just multiply this by itself 4 times, 0.2558 into 0.2558 into 0.2558 4 times. So that becomes this power 4, and that gives you the required probability. In the second part, it says, safety regulations state that the pressures must be between 1.9 minus b and 1.9 plus b. It's known that 80% of the tires are within these safe limits. So you're given the probability. You need to find these safety limits. So you need to find the value for b here. And then you can write down the safety limits as well. So what do we know? Probability of x being between these two values. This is 0.8. 80%, that's 0.8. And we have to find the value for b somehow. This is inverse normal. We've got the mean, we've got the standard deviation, but this value is missing. We don't know what the value for b is. How do we think about this? What was the mean? Mean was 1.9 here. Mean was 1.9, right? So 1.9 minus b and 1.9 plus b, what does that mean? We've got 1.9 exactly in the middle. You've got 1.9 in the middle. Plus b means you go b units to the right. Minus b means you go b units to the left. Now, since the curve is symmetric, we know, first of all, they've given that this area in the middle is 0.8. If this area is 0.8, what's the remaining area? That's 0.2. That's going to be equally divided on both sides. 0.1 on the left side, 0.1 on the right side. So now we can convert it to a one-sided interval. We can say, if the middle region is 0.8, then the region on the left side of this value, 1.9 plus b, what's that total region? That total region is 0.1 plus 0.8, and that's 0.9. So we can convert it to a one-sided interval like this. Probability of x less than 1.9 plus b, that is equal to 0.9. And then you convert it to z. Write this in terms of z. Figure out whether z is positive or negative. Use the standard inverse normal method. Find the value of b from that. Once you have the value for b, you can write down the safety limits, 1.9 minus that and 1.9 plus that, and that gives you that safety limit. Okay, so when you have two-sided interval, in case of inverse normal, you have to find a way using the normal distribution curve to first of all convert that to a one-sided interval, and then you can just use that method for finding the method for inverse normal that we normally use. Okay, let's have a look at this now. So in this city, the heights are normally distributed with mean 176 and standard deviation 4.8. Find the probability that an adult has a height greater than 170. That's pretty straightforward. Let's look at the second part of this. In the second part, it says 60% have height between 170 and k. 60% of adults have heights between 170 and k. So what are we given? We're given probability of x being between 170 and k, that is equal to 0.6. That's what we're given. Probability of x being between 170 and k, that is 0.6. Where k is greater than 70, so it has to be some value greater than 70. Find the value for k, giving an answer greater to one decimal place. How do you think about this? Again, this is inverse normal. We have a two-sided interval. We can't work with two-sided intervals in inverse normal. We have to convert it to a simple normal. Okay. Now, how do we think about this? So we've got one value. So if we convert it to standard normal, you can do it directly or convert it to standard normal first of all. So in this case, what I've done is I've converted it to z first of all. 170 minus the mean was 176, standard deviation was 4.8. That gives me that z is between minus 1.25 and this value. Okay. Now you could do it in terms of x first and then convert it to this. Both are fine. In the previous examples, I did that directly. In this case, I've converted it to z first of all. Both are fine. They will work every time. So between 170 and k, or between these two values of z, we know that the area is 0.6. Now, first of all, we need to figure out whether this value, the other value, if that's positive or negative. That is going to be positive because we've got one negative value and the area between them is what? 0.6. If the area is 0.6, on the left side, the total area is only 0.5. So if it's 0.6, the other value has to be on the other side. It has to be on the positive side. So that's what we know for sure. Okay. Now the problem is we only know that this region, this yellow region is 0.6. That's what we are given. Okay, that's what we're given. How do you find the value for k? We know that this area is 0.6. Can we find the area to the left of minus 1.25 somehow? The area to the left of minus 1.25? We found that in the previous part of this question. In the previous part of the question, we found the probability corresponding to the z value of 1.25. 1.25 on the left side of that, we found in the first part, this area was 0.8944. If that's 0.8944, what I've done is, I've said, this small region here, that would be 1 minus that, and that's 0.106. So it's 1056. This area is 1.056, 0.1056. So here now, in this case, you could say, this area is 0.1056. If this is 0.1056, then what's the total area to the left of the z value? What's this total area? This total area is this plus 0.6, and that will give you 0.7056. And now what you can do is you can find the probability value corresponding to this, corresponding to 0.7056, and that will give you that z value. And you can find the z value from the table. Once you have that, you input that in the formula, x minus mu over sigma equals z, and that gives you that result, which turns out to be 178.6. So sometimes it can be something as complicated as this as well. Okay, you can have a look at this solution in your own time. This is pretty complicated. I think one of the most difficult questions that you find in normal distribution, because of it being an inverse normal problem, two-sided interval, converting it to one-sided interval is fairly complicated in this case. One last example. This is something that you'll see a lot in recent papers, problems like these. A farmer sells eggs. The weights in grams of these eggs can be modeled by a normal distribution with mean 80.5 and standard deviation 6.6. Eggs can be classified as small, medium, and large based on their weight. A small egg weighs less than 76 grams, and 40% of the eggs are classified as medium. Find the percentage of eggs that are classified as small. Now, the first part is pretty straightforward. We are given that a small egg is that weighs less than 76. Just find the probability for that. Now, the second part is find the least possible weight of an egg classified as large. Now, in the first part, what we have found is that 24.76% of the eggs are small. So this is 24.76%. They have told us in the question that 40% are medium. So these are 40%. So from that, we can figure out how many are large. 100% minus these other values That will give you the probability of an egg being large, and that turns out to be 35.24%. Now, you know the mean of this distribution. Mean is given to be 80.5, standard deviation is 6.6. You need to find that number. So it's like this basically. You've got 3 types of eggs: small, medium, and large. There'll be some value here. That's the cutoff point for small, and they've given us that this cutoff is 76. This point we do not know. Let's call this point A. To the right of A, we know that this probability is what? 0.3524. So we write it like this: probability of X being greater than A, that is 0.3524. That's the least possible weight of a large egg. We have to find the value for A. So you can think of it like this. This is an inverse normal problem now. Find the value of A from that. And that's the cutoff point for an egg being classified as large. Okay. So that's all a normal distribution. So there are 3 different cases that you would see. Number 1, you'll have the data given, and you have to find the probability. You'll have X, mu, and sigma given. You'll have to find probability. How do you do that? Convert X to Z using X minus mu or sigma. Convert that to standard form, Z less than a positive value, and then you use the table to find that probability. The second possibility is inverse normal. You have the probability given. You write that probability in terms of Z first of all, and you have to find missing information from the data, right? So something might be missing from this. You write that probability in terms of Z first of all, figure out whether Z is positive or negative, convert that to the standard form, and then use the table to find the value of Z corresponding to that probability value, assign the appropriate plus minus sign to that, and then use the formula to find any unknowns that we have. And then finally, we did binomial to normal approximation. We'll have NPQ, convert them to mu and sigma using the formulas, do continuity correction, and then find the probability using normal distribution. These are the conditions. NP should be greater than 5 and NQ should be greater than 5. And then we looked at a number of examples on this. I hope that makes sense. If you have any questions, you can let me know now.